Good morning, Professor Saad Maghrib.
Hello, good morning.
How are you? Fine?
I'm good. Alhamdulillah, good. You?
Yes. Fine, fine. You are in Australia or Malaysia?
I'm in Australia now, yeah.
Oh, yeah.
Yeah.
Good. Thank you very much for your engagement for the
Yeah,
previous
it's my
edition
pleasure.
of IRSEC.
So are we going to start? What time are we going to start?
At 9, 5 minutes to 9, I will open the webinar to attend this now.
Okay. Yeah.
Joseph, good morning.
Good morning.
Recording in progress.
تقدر الدار ست وشون
هذا ديال
راك انت جاك دوزيام تيجي واحد الغدا تيجي
راه تنشوف اصاحبي الا اختي غدا ما تبانليش ما يديرليش هاد لاباج هادي داخل
Good morning, Professor Mohamed Saidi, Dr. Mohamed Saad Mutahar, Dr. Saad Mekhlif, Dr. Nicola Watt. Are you ready?
Yes, we're ready. I think we still have 4 minutes to go.
Yes, it's just time to present Dr. Professor Saad Mikhlef. This session will be shared by Professor Mohammed Saidi and Professor Saad Mutahar. The Professor Saad Mohammed Saidi, the floor is yours.
Okay, thank you, Professor Zaz. As I said, we still have 3 minutes or 4 minutes to start this session. Probably we can just have a quick introduction. I don't know if we have all the speakers present with us, so just check.
Professor Said Ahzi will be replaced by Dr. Nicholas Bat.
Okay.
He sent us his presentation, and Dr. Nicholas Bat will answer questions.
Okay. Okay. Good.
As co-author of the presentation of this work, he will answer the questions.
Okay. Good. Hi, Professor Mikhlef. How are you doing?
Yeah, I'm good. Thank you. Hi. Good morning.
Maybe good afternoon or good evening at here in Malaysia.
Yeah, evening. Yeah, it's already 7 p.m.
Yeah. Okay. Wow.
Yeah.
He's from he's now in Australia.
Yeah,
Australia. Okay.
Yeah, in Melbourne.
In Melbourne. Okay. Okay. So it's a pleasure meeting you, Professor Saad.
Yeah. It's my pleasure too.
Thank you also for your support to the IRSEC through your keynote talk.
Yeah.
Good morning, Saad Mutahar. How are you doing?
Good morning, Professor Saidi. I'm fine. How about you?
Fine, thank you.
Good morning, Professor Saad Mikhlef.
Yeah, good morning.
Professor Zaz. How are you doing?
Nice to meeting you.
Nice to listen to.
Yeah.
Professor Saidi,
we still have 2 minutes to go. We're very punctual. Maybe I don't know how many people we have attendees with us. Okay. We can just, I think, start now. Okay, so good morning, good afternoon, and good evening, ladies and gentlemen, to this session on digital technologies in solar energy in framework of the 9th edition of the International Renewable and Sustainable Energy Conference, IRSEC'21. My name is Professor Saidi, and I will be chairing this session with my colleague, Professor Saad Mutahar. Both of us are from Morocco. So a quick introduction of our speaker. Let me just... So Professor Saad Mikhlef received the Bachelor of Engineering degree in Electrical Engineering from University of Steep in 1995 in Nigeria, and the Master of Engineering Science and PhD from University of Malaysia in 1998 and 2003, respectively. He is currently professor at the Department of Electrical Engineering, University of Malaya. Professor Saad is the author and co-author of more than 250 publications in international journals and proceedings. He is actively involved in industrial consultancy for major corporations in the power electronics projects. His research interests includes power conversion, techniques, control of power converters, renewable energy, and energy efficiency. Without further ado, Professor Saad, the floor is yours. Just share your presentation.
Thank you very much, Professor Mohammed, for the introduction. So also I would like to thank the organizing committee for inviting me for this conference. You know, it's a pleasure to see you all here. And I hope it will be useful and also beneficial for all the audience. Okay.
Okay,
Can you see my screen?
yes.
Yeah. Okay. The first things, I think the topic I propose is not in line with the theme of the discussion today. You know, so I was talking about the UPS system, but the title of it's about the solar technologies. You know, so I'm not sure. You know how it's going to go, but. You know, I do also work on solar PV systems, especially on the MPPT controllers and also on the inverters for grid-connected PV systems, and also we're forecasting. Okay, but today topics will be a bit different, which is on the transformerless UPS systems. You know, so this is also another important and interesting topics, which a lot of research is going on at the moment. Okay, so now currently I used to be in working in University of Malaya in Malaysia. So recently I've moved to Swinburne in Melbourne, Australia. But I'm still working also as an honorary professor at the Faculty of Engineering, University of Malaya. So we have a lab there, and we have quite a number of researchers working on various topics. So this is the outline of the. So I have 30 minutes, right, Professor Muhammad?
Yeah, you have 30 minutes, right?
Yeah. Okay. So I just like to keep the time. So okay. Okay. So looking into UPS systems. Okay. So what this is the outline of the presentations. So I have to skip. Just to give you some introductions. Okay. What is the UPS systems? Okay. UPS systems is a device. It's a power electronic device which consists of a battery and an inverter and a rectifier, and that is used to provide emergency power in case there is a failure of the utilities. Okay, and most of the time is used for critical loads. Okay, such as military equipment, data centers, medical equipment, communication devices, and nuclear power plants. So there is a variety of applications where this UPS systems is used, and it's becoming more critical and more important as we live now, because you can see most of our applications and our work is becoming online. So data centers, communication devices are becoming very important, you know, and they're becoming very crucial, you know, devices. So they require a continuous power supply. This is some statistics. You know, there are more than 3 million data centers around the world, and is increasing because we are moving into more what you call e-commerce, e-banking, e-learning, e-research. Everything is becoming online, and that requires a large amount of data centers. Universities and research centers are investing a lot of money on this, and they require to have this power supply. Okay, the power capacity of data centers is more than what I call around 30 gigawatts, which is huge. And I think the most recent we call nuclear disaster, which is the Fukushima nuclear disaster in 2011, which is estimated the loss almost $71 billion. And as you know, after the investigations been done, they found out actually the main reason for the Fukushima nuclear disasters is what they call the cooling system has not reacted on time, because the diesel generators require some time to come up, and that's actually where the reactor blown up, means the heater, because they need a huge amount of water pumps to cool up the reactors, and that is one of the reasons. Okay, and the data down times usually for internet companies is really in order of billions. You can imagine if Google, for example, or Tencent, or Alibaba, or Amazon, imagine they cut off for 1 or 2 minutes, millions of dollars of losses. So, and the power supply to these data centers, it has to be 100%. Okay, so that's why it is important to have high surety and a long pickup time of UPS systems, okay, to address these issues. So what are the existing types of UPS systems? You know, there are a few types, okay, we can classify them based on this. For example, okay, let me take the marker. Okay, so we have what we call the offline UPS systems. Okay, so what we have two modes of operations. Okay, where there is, when the grid is available, so we bypass the UPS systems. We bypass the inverter and the charger and everything, and then we supply the power directly to the load. Okay, where else during also in the same time we charge the batteries. This is the normal mode. Okay, this is what, and also at the same time we charge. When there is a blackout, when there is no power from the grid, then the pickup mode will take off from the battery. So this is why we call it offline. Means actually most of the time the system here is offline. Means it does not interact because the power is bypassed through the switch. All right. Second one is the line interactive UPS systems. Okay, where in these systems we have what we call a switch which is in series with the grid. Means all the time the power is supplied both to the inverters and also to the load in the same times. But also it does not go through the inverter system. During the pickup time, then the power is supplied from the battery systems. What else? The online UPS systems, because there are many ways on how to classify the topologies of UPS systems. Okay, the other classifications, which is during the normal operations, so we pass through the rectifier and also the inverter and then to the load during the normal operations. Okay, and during the pickup mode, then we pass from the battery to the inverter and to the load. So there are advantages and disadvantages of all these configurations. Okay, for example, in terms of power quality, in terms of what I call isolation, and so on and so forth. So also we can classify them in terms of isolations or transformerless topologies. Okay, if you look into here, also this is another way of how to classify the UPS systems. Okay, transformer-based. Transformer-based means we are using a transformer here. You can see there is a transformer here and there is another transformer here. But what is the disadvantage of this? This is a line frequency transformer. A line frequency transformer means we are talking about 50 hertz or 60 hertz transformer. Means, what does this mean? It means it's very bulky, it's very big in size, and it's very heavy. So this is one of the main issue. But it provides one of the advantages. It provides the isolations, and also it's very robust. Okay, but as I said just now, it's very bulky and also it's a cost effect. So this is based on transformer based. The second classification also, it's a transformer based. It's isolated, but in this case here, we use a high frequency transformer. So what we have here, we have the grid, and then we have a rectifier, and then from the rectifier, we have an inverter here to create the high frequency signals. And then these high frequency signals means, what does it mean? It means the size of transformers will significantly reduce, because as we increase the frequency, the size of the inductive components will become very, very small. Okay, so then we have the rectifier, and then we have a boost converter here, and then we have the inverter and then the load. Okay, so this is also provide the galvanic isolation. Okay, but the disadvantage of it, it's the complex control and the stages. You see, we have a rectifier, we have an inverter, we have a rectifier, a boost converter, and an inverter. A number of 5 stages of conversion. And you know, every 5 stages of conversion is the complexity of the control becoming a major issue. Okay. And then we have the last classification, which is the transformerless. Transformerless means there is no need of transformer, right, in the system. And you can see in this topology here, there is no transformers included in the system. Okay, what is the advantage? Advantages, yes, it's in terms of cost is low because we remove the transformers. In terms of size, it's small, okay, and also the efficiency is high. But the main issue is this: the isolation. There is no galvanic isolation. So if there is a fault, as the inputs here in the system, in the input, this fault will be transferred to the load, or from the load to the source. So these are the thing. And also what we need a high battery bank. Why we need a high battery bank? Because there is no transformers that we can use as a boost up or step up the voltage, you know. So the higher the battery bank size, it has to be huge. So this is the second way of classifying the UPS systems. Okay, so we put them in a table and we compare how they look like, you know, because we need to put all the parameters together in order for us to see how all the topologies looks like. You can see here we classify them based on transformer based, okay, high frequency transformer based, and then transformerless based. Okay, and what you can see from here, there are a few topologies which is presented in the literature. Okay, and also here we selected a number of topologies presented in the literature, and then here, and then we compare. We compare in terms of number of power stages, because this is also important, efficiency, power rating, power factor, system specification, battery bank, and then the weights. You know? If you look into here for transformer base, which is the line frequency transformers, usually the weight is very high. You can see, all right, quite high. All right, and then also in terms of efficiency, it's around 90, between 85 to 90% efficiency. Okay, so this is the efficiency of the systems. If we look into the high frequency transformers, okay, you can see the efficiency also almost similar, 90 peak efficiency. Okay, the good things about it is the battery size, it's a bit reduced, 48 volts. Okay, and then also in terms of size is reduced. If we look into the transformerless, okay, it has the highest efficiency, 96%, which is very good. It's among all of the systems, it's a high efficiency. Okay, in terms of size is smaller, but the issue is, you can see 192 volts supply. So this is the major concern. Means you need a large number of batteries in series to get the 192 volts, which is make the system bulky, you know, again. So that's why I say efficiency is one of the important criteria. And the second one is the battery size. And then we want to have a system with the highest efficiency and a lower battery bank. So this is the main objective of doing, or what I'm going to present today. Okay, so I have the highest efficiency, which is this. All right, but the problem here is the voltage is quite high. So I think this is also is quite important for UPS systems. So in the battery bank for series connection, we have the two configurations. Either we put them in series and in parallel. In terms of series, you can get the required voltage that you need. Okay, the batteries can be used efficiently. Okay, and then no need for boosting circuits. However, in case we have imbalanced batteries, for example, there is one battery state of charge is 80%, another one is 60%. So, you know, the imbalance between the batteries. During the charging also, you may overcharge them because the power is supplied to all in series, okay? And that's actually maybe lead to a destruction or shorten the lifespan of the battery systems. Okay, if we over discharge them, or this deep discharging can cause the battery cells to damage. Okay, and then most of these kind of series connections, usually we require BMS, battery management system, which is an additional cost. The same things, if we connect them in parallel, also there are quite a number of advantages and also less disadvantage. So the number of batteries is not restricted to the DC link of the voltage. So you can put what I call 5 or 6, but here you require an extra what I call DC-DC converters to push up the voltage. Okay, so no extra voltage balancing because all of the batteries, all right, and each batteries can be what I call treated equally, or can be removed without impacting the system in terms of in case of maintenance or repair. And then but in terms of efficiency is less efficient compared to series. And then this is the additional hardware that we need. We need a step up what I call circuit or boost converter to boost the voltage to the required, because when you put them in parallel, means the voltage will be the battery voltage. All right, and sometimes we need, for example, like we see just now, for example, we need 192 volt, we need 100 volt, whatever. So we need the boost converters. Okay, so what this is some of one of my PhD students work actually. So he will propose this topology. It's a transformerless, like for the title, from the title, and it is the objective, as I said just now, is to achieve a higher efficiency with a lower battery bank. Okay, so that's the proposed topology. So we can see it consists of boost rectifier here. Okay, we have the grid, and then we have the rectifier circuit here. We use the totem pole bridgeless rectifier. The second one is the battery charger, because we need the battery charger systems. Okay, and this charger, this is the circuit, and these are the battery here. The batteries are here, so this is the circuit. And then the last one, which is the H-bridge inverter, which is a normal topology, what I call half bridge, what I call 4-switch H-bridge topology for the inverter. Okay, so let's look into the operations. You know, the modes of operations of this topology. So this is what happened during the normal mode of operation. So what happened? The power will be supplied directly to the batteries here, and also to the load. Okay. So during the battery mode, so what we have, the same like other topologies. So the power will be from the batteries, which is, this is the battery here, the battery, and this is the charge and discharge circuit, and then goes to the phone. So let's look into the three components: the rectifier, the battery charging circuits, and also the inverter. You know? Okay, so this is a very common and well-known what I call totem pole bridgeless topology, which we used. Okay, we use reduced conduction losses because we want to improve the efficiency of the system, and also using the what I call the power factor corrections, because very important to do the power factor corrections, and almost reduced by almost 30% compared to the full bridge topologies. And both of the switches here, we have the two S1 and S2, are driven by the same gate signals, which make the control circuit very easy and what I call easy to implement. And then what we did, we simulated. Okay, so we did the simulation work of this topology, and you can see the waveforms. It looks very clean. The total harmonic distortion is very low, and less than 5%, and the power factor is 0.9, which is, and this is the experimental work. This is the hardware or the experimental work. So the rectifier circuits works perfectly. And then also we study the stability of we use small signal control to study the stability of the systems, and the system shows good stability with a positive phase margin. Okay, and also it shows good stability with the okay, for small signals for D and G, okay. And then we look into the bidirectional battery charger circuit. So the second one, I still have 9 minutes. So the battery charger and discharger. So we use different stages. One is the base circuit, and then the low voltage circuit, and then the clamping circuits. What are the features of this? So it has a high gain, okay, for both either working on a buck or in a boost mode, using less passive components, inductors and capacitors, and also use only 3 active switches. You can see here we have only 3 active switches: 1, 2, and 3. 1, 2, and 3. 3 active switches only. And also the interesting part of it, we are able to operate it at ZVS. Okay, so the soft switching is applied, and then that's actually give us a better performance in terms of losses. You know? And this is the modes. I'm not going to go through all of them. All the modes of operations of the battery charging, what happened from stage 1 up to stage 6. All right. And also we to calculate the voltage conversion ratio. Okay, we simulate for different values of the gain. Okay, to see actually where is the best, which is the best value. So the duty cycle and the gain. And also in the boost mode, also we analyze the circuit in the boost mode operations for different stages. And also we plot the what you call the gain versus the duty cycle and the different values of N. Okay, and this is the what you call the parameters of the battery charger. So the value, the voltage is around 360 volts for the DC link, but the battery voltage, you can see the battery voltage is very low, and the switching frequency we are using around 30 kilohertz. Okay. Okay. After we match the two, because the system works in both in a buck mode and the boost mode. So we found actually the best will be N equal to 3.5, which give us the best gain for both buck mode and also for boost mode, because we have a single converter which operates into modes. Okay, and also we study the stability inductors to control the transfer. We vary the value of the inductors and see the stability of the systems and in the closed loop system. The same thing goes for the inverter. The inverter, I think it's very simple one. It's very simple circuit, which is the Hitch bridge inverter, which is most commonly used. Used topology, very robust, very easy to implement. And these are the equations. What you call we use the slide mode control to control the inverter, and we perform the tests for the system. So you can see here from 0 to 100% load. So from 0 here, you can see there is a 0 load. Suddenly we apply a full load, and you can see the systems recovers and quite well. And also from 100 to 0 load. So you can see the systems actually, you can see the voltage remains okay, but the current goes to 0. And this is the total harmonic distortion, which is very low, which is around 1.5%. This is the control. I'm not going to go into detail of the control. All right, so this is the control that we use for the UPS systems. And this is the overall specifications, where we have the single, actually our system is a single phase. The output also is 220 volt, 50 hertz. The system is 1 kVA, we call size. And this result here, it shows the transition, because in the UPS systems, we have when the grid is present, all right, and then suddenly the grid goes off, then the UPS have to take over. All right, so this is the first scenario. The second scenario, when the UPS is running and then suddenly the grid comes back. So the UPS have to cut off and then the grid will supply the power. So we did the tests for both scenarios, okay? If you look into here, so this is the grid system. So the power is supplied from the grid at certain point of time, then there is a blackout, which is the input current and the input voltage becomes zero. And what you can see from the load side, from the output, you can see, yeah, this is here up to this point here, it's all supplied by the grid. But here, the UPS took over. So there is almost, is zero disturbance to the system, to the load. From the load point of view, doesn't see any changes. But actually, at this point of time here, we have switched from the grid to the UPS. Okay, so this is the first scenario, which is an important test, which is all UPS systems have to pass this test, and it should not disturb the load. And what else? Also here we test when there is a UPS system, okay, which running, the system is running on a UPS mode, okay. At certain point of time here, the grid come back. Okay, the grid come back. When the grid come back, okay, also we can see the changes on the UPS systems from the load side. It does not feel anything. Okay, so these are very important two scenarios which actually test the performance of the proposed UPS systems. Okay, the second important component, like I mentioned just now, the battery bank and also the efficiency. So we do the efficiency, we did the test of efficiency in two modes, the normal mode and the battery powered mode. Because we have the normal mode means the grid mode, means the power comes from the grid and goes to the load, and through the UPS, through the UPS system. Okay, and the second one when the power is from the battery only. Yeah, you can see here there is the peak efficiency on the battery mode. We almost 93.5. We reach almost 93.5. You may ask questions why in the normal mode the efficiency is lower. Yeah, the efficiency is lower because there is less conversion stages, because we don't have to do the rectification mode. Okay, the losses in the rectification side is almost zero because the power comes from the battery to the inverter and then to the load. Okay, all right, so this is in terms of efficiency. Then we did a comparison with what we have presented previously in the table, and then to see how our system performs. So this is our proposed system. Sorry, this is our proposed system. So we reach almost 93.5% efficiency. And the good thing is also, it's the battery size is only 24 volts. Yeah, you may ask questions if we have only 24 volts. Yeah, if you need more capacity, you can put more batteries in parallel. But the minimum requirement for this system to operate is just 24 volts compared to what is in the market, which is almost minimum 100 volts. Okay, so this is to show how the system. Then we developed the prototype. This is the prototype actually, which is already working, and this is during the test. So in conclusion, okay, I just have I think 1 minute left. So in conclusion, the transformerless UPS systems has been proposed and also tested, and the operation at 24 volts, which is suitable for parallel connections. The high efficiency bridgeless rectifier is used with the almost unity power factors, and the proposed systems usually our suggestion to be used for low power applications, which is the range of 1 kVA. And these are some of the papers that we publish in this from this work. And if you have any questions, thank you. I think I have kept my time to 30 minutes. Thank you very much.
Oh, okay, thank you so much, Professor Saad, for the very insightful and thought-provoking talk, and also for respecting the time dedicated to this keynote talk. We have discussions session just after the keynote talks, with the 3 keynote talks. So let's move now to our next speaker. Our next speaker is Professor Saeed Ahzi. He's a professor at Khalifa University, and we'll be talking about theoretical and computational analysis for the design of PV panels. So let's just present Professor Ahzi quickly. So the Professor Ahzi is a professor at Hamad bin Khalifa University in Qatar and acting research director of Qatar Environmental and Energy Research Institute. Prior to joining this institute, he held a distinguished professor position at the University of Strasbourg in France, where he also served as associate dean for the Professional Institute of Science and Technology, director of the Industrial Engineering Program, coordinator of the Master Program in Mechanics, and associate coordinator for the Master of Computational Engineering. He also served as the founding leader for the research group in materials processing and microstructure at the Institute of Mechanics of Fluids and Solids, CNRS. So without further ado, I leave the floor to Professor Ahzi. So please share your slides. Professor Ahzi, we cannot hear you. Probably there's some issue with the sound. Okay, you're playing video, okay.
Good morning, everyone. My name is Pamir Ali, and I'm currently working as a postdoc in DEWA R&D Dubai. Unfortunately, Dr. Saeed could not present today, so as collaborators to this work, me and Dr. Nicola will present and answer questions on his behalf. The title of the presentation is Theoretical and Computational Analysis for the Design of PV Panels. This work was carried out in Kiri, HPKU in Qatar. This is the presentation layout. In the introduction, I will go through the very basics of PV systems and then justify the need for such kind of numerical models in PV industry. Then I will go into the details of the different PV related models, their development and implementation along with various validations. And in the end, I will conclude with the main highlights of the presented work. We all know that solar energy consists of both light and heat, and we can generate electricity using solar energy via direct methods or the indirect methods. The direct methods such as PV use the light energy of the sun, whereas the indirect methods such as solar thermal, they use the heat energy of the sun. The solar irradiance incident on any receiver surface can be further subdivided into 3 main components, which are the beam or the direct irradiance, diffused or the indirect irradiance, and lastly we have the albedo or the reflected irradiance. Similarly, it can be measured as the GHI, that is the global horizontal irradiation on a flat surface, as POA, that is the plane of array irradiation on an inclined surface, and then we have the DNI or the direct normal irradiation on a normal surface. Each of these can be used to find the other using simple correlations. Although these are very basic and well-known terms, but I'm introducing them because they will be used quite often throughout the presentation. Some of the main advantages of solar energy are that, unlike other renewable energies, it is abundant and somewhat evenly distributed across the globe. Unlike other renewable energy sources, it can be employed both on small scale and large scale. Similarly, some of the main disadvantages are that it is an intermittent source of energy and can be harnessed during the daytime only. Its power production is greatly influenced by the weather conditions, and for commercial production, a large area of land is required. PV cells are the most fundamental building blocks of a PV system. They do not produce much useful power on their own, so they are either connected in series or in parallel. Common commercial PV technologies are crystalline silicon cells and the thin film cells. And the crystalline technology shares almost 95% of the total annual global production. PV modules are of further two types, the flat plates which use the GHI and the concentrators which use the DNI. Performance in simple terms can be defined as the power output derived by the system to the resources it used. For a PV system, the performance can be evaluated into four broader areas. The first one is the radiation and optical performance, which gives an estimate of the incident and the absorbed radiation by the PV module. The second one is the thermal performance, which is a measure of the working cell temperature of a PV module. The electrical performance is evaluated based on the power delivered and the corresponding efficiency of the PV module. And finally, we have the structural performance, which is basically used to measure the working life of a PV module. Together, all these performance metrics give the overall performance of a PV module. To evaluate these performances, we need mathematical models for each of these. And furthermore, each of these mathematical models is directly or indirectly connected to each other. So the input of one is basically the output of other, and so on and so forth. And as the physics behind each of these models is different and they are coupled to each other, so this requires a multi-physics coupling approach or the modeling approach. Basically, the motivation behind this study was to develop codes that are fast, reliable, and accurate. Accurate because the carryover from one model to the other will propagate and increase the aggregate error of the overall multi-physics model. The radiation model basically gives us the total available or incident irradiance, whereas the optical model estimates the total transmission, reflection, and absorption losses through the different layers of the PV module. And together they give us the total absorbed irradiation by the PV module or the PV cells. For estimating the available irradiance, we can either use the sky models, then we have the satellite derived data, or we can also use the on-site measured data. The on-site data is normally the most accurate for the location under study and its nearby vicinity. Similarly, for optical models, we can estimate the transmission losses either based on spectral response such as in the Markov's chain, or we can measure the accumulative losses using models such as IRSEC' convention. Unlike the IRSEC' model, which estimates the absorbed radiation based on many inputs, we propose to use the POA data with effective values of absorptance and average values of transmittance. We came up with this equation using similar equations from hybrid PVT systems. In this equation, alpha is the effective absorption for a silicon PV cell, it is approximately 0.93. While the average cumulative transmission losses can be calculated using this equation, which is a well-known equation for measuring reflective and refractive losses from the glass surface. To compare the IRSEC' and the proposed model, we took the ground measured irradiation data for a typical day in Qatar from the OTF of Kiri, and the comparison shows that the IRSEC' model estimates the absorbed irradiation during the early hours of the day and the late hours of the day even more than the incident POA, which is physically not possible. Whereas our proposed model estimates almost the same irradiation during the peak sunlight hours while estimating more realistic values during the early hours of the day and the late hours of the day. If the PO data is not available, then we can use this correlation to find it from the GHI values. The second model is the thermal model, whose main purpose is to find the PV cell's operating temperature, but it can also be used to find the temperature distribution within the PV module. In thermal model, we basically solve the heat equation. As each layer of the PV module is made up of different material, the material properties in this equation change accordingly. And the term Q in this is the heat generation term, which is only applicable to layers that produce heat. In case of PV module, it is mainly the PV cells and the glass layer. The heat equation can be solved using different techniques. It can be solved using analytical approaches, but to use this we often have to oversimplify the model, which then loses accuracy. There are also empirical equations, but since they are derived from experiments, they are very case specific. And due to the shape of the PV module and the boundary conditions that it is subjected to while under operation, the numerical approaches are the best to study the thermal behavior. In numerical models, we have the finite difference models and the finite element models. And going from 1D to 3D, we gain accuracy but at an expense of higher computational time. Based on the literature review, we realized that there is a need for a fully transient thermal model which includes all the important layers of the PV module with temperature gradient within the PV module to fully capture the temperature distribution under any field conditions. A total of 4 thermal models were developed both for comparison and validation purposes. The finite difference models described in this work are basically self-developed codes that we wrote in MATLAB, whereas for the finite element models we use the commercial finite element tool ANSYS. So basically, whenever the sunlight hits the surface of a PV module, about 2 to 5% of it is absorbed by the glass depending on the type and the constituents of the glass. This causes the heat generation QFG in the heat equation. The remaining that reaches the solar cells or the PV cells, part of which is converted into electricity based on the efficiency of the PV cells, and whereas the remaining is converted into heat given by QPV. Therefore, the higher the efficiency of the PV cells, lesser would be the PV module temperature. This is also one of the reasons that PV modules are coolest when they are operating at maximum power point, where the efficiency is the highest. Furthermore, this efficiency is also a function of temperature, and this efficiency decreases with temperature and vice versa. Thereafter, there are 3 modes of heat dissipation from a PV module. Heat dissipation within the module is due to conduction, whereas to the surroundings is via convection and radiation. For improving the existing thermal models, one of the most prominent features of our thermal model was to suggest and use a realistic heat dissipation approach. Here we showed that it is very necessary to take into account the heat loss to the sky and towards the ground via radiation as well as via convection. Whereas in the normal approaches, people normally assume that the heat is being lost to the ambient temperature both via conduction and radiation, but only towards the ambient. In the finite difference method, we basically convert the heat equation, which is a PDE, into algebraic equation. The entire solid domain is divided into smaller grids and the heat equation is then solved to find the temperature distribution within the module. From the 1D FD, we can only find the through thickness temperature distribution only. Once the thermal model is developed, we only need 3 inputs to find the temperature distribution or the temperature of the cell. And these 3 inputs are the POA radiation, the ambient temperature and the wind speed. And for validation, we took 1 day data from the OTF of Curie. Using the developed code, we then simulated the backsheet temperature of the PV module, which was then compared to the experimentally measured backsheet temperature. It can clearly be seen from the results that using our proposed thermal network, the results improved a lot, even for 1D model. This clearly demonstrates the need for using more realistic thermal network while modeling the thermal behavior of the PV modules. Similarly, we simulated different weather conditions like sunny day clear sky, sunny day cloudy sky, rainy day overcast sky, and then we also simulated 2 consecutive sunny days. The results show that even under the worst weather condition, the model still performs adequately well. These days that we chose here are the ones that the PV module were cleaned a day before, as to avoid any soiling effects. The 2D FD also has similar approach as that of 1D FD, except that it can also find the cross-sectional temperature distribution of the PV module. To further validate the developed FD models, we compared them to the finite element models, which have been developed in the commercial software ANSYS. The finite element methods are also numerical models and convert ODEs and PDEs into algebraic equations. However, finite element models are much better for complex shapes as compared to the FD models. In finite element models, we developed the 2D FE and the 3D FE. Both steady state, that is the NOCT, and the transient, that is the experimental analysis, showed that the results were very similar to those predicted by the finite difference models, but with a slightly better accuracy. And for the 2D FT, we solved only half model, and for the 3D FE, we solved quarter model because of the symmetry of the shape and the symmetry of the geometry and the symmetry of the boundary conditions. The comparison between these 4 developed models shows that the 3D FE is the most accurate, but obviously very slow. And then the 1D FT in comparison is least accurate, but not far away from the 3D FE in estimating the backheat temperature, because the root mean square error of 3D FE is 0.7 almost, and for 1D FT it's 0.9, so the difference is not that much. So in summary, we can conclude that if we want to find the PV cell temperature only, then we can use the 1D models, and if we want to find the temperature distribution within the PV module, then we can either go for the 2D models or the 3D models depending on the case. The third model and the most important model for a PV system is the electrical model, as it helps to estimate the electrical yield of the PV modules. To make this estimate, the model needs the PV cell temperature that we find from the thermal model, and then it needs the absorbed irradiation, which we get from the radiation model. The two most common approaches to estimate the power output is either through simple correlations or through detailed electrical models. We can find many correlations in the literature to estimate the power output of the PV module. These correlations, however, only provide us with the total power only, and they do not give us the corresponding IV characteristics of that power point. For finding the IV characteristics, we need to use the detailed electrical models. One such widely used model is the one diode electric circuit, which basically represents the PV module with this equivalent circuit. The equation for this circuit has 5 unknown parameters, which are the light current, the diode saturation current, series and shunt resistance, and the ideality factor of the diode. Since the equation is non-linear, we either have to solve them via iterative methods or optimization techniques to find these 5 parameters. De Soto's model is also based on the one diode circuit and is often used for comparison. This model has 5 parameters. Actually, this model finds these 5 parameters at the STC condition, and then uses these translating equations to find the value of these 5 parameters at other operating conditions. You would note from these translating equations is that the light current is assumed to vary both with the irradiation and the temperature. The shunt resistance or the diode saturation current and the ideality factor are assumed to vary only with the PV cell temperature. The shunt resistance is assumed to vary only with the irradiation, whereas series resistance is assumed to not change at all. And from physics point of view, these assumptions are not entirely correct, as the value of each of these 5 parameters changes both with the irradiation and the temperature. To overcome the shortcomings of the De Soto's model, we developed a new methodology which can capture the variation of each of these 5 parameters with varying irradiation and varying temperature. We call it the shift factors equation. The way to use this model is that we find the 5 parameters from multiple IV curves rather than just using the STC curve. Then instead of using the translating equations of the De Soto's model, we just plug these values into this algebraic equation to find the variation of each of the 5 parameters with varying irradiation and the PV cell temperature. Here P in this equation is only a representation and can be any of these 5 parameters. For comparison, here we have demonstrated that how each of these 5 parameters is changing with varying irradiation and varying temperature using our model and the De Soto's model. Just as an example, the De Soto's model shows that the series resistance is fixed even at changing irradiation and the changing temperature. However, our model shows that the series resistance increases with the increasing cell temperature and it decreases with increasing irradiation. One more observation that we can get from is that the irradiation has a more pronounced effect on the value of the series resistance as compared to the cell temperature. Both of these phenomena are in accordance with the PV device theory. Therefore, such comparisons over a longer period of time can be used for PV modules diagnostics, and they can help us in preventive and corrective maintenance of the PV module. The datasheet validation of the PV module under study shows that the proposed model is able to capture the IV characteristics at various operating conditions almost perfectly, whereas the de Soto's model only performs well near the STC, but it does not perform well for the other conditions which are far away from the STC, and we can also see that the accuracy starts decreasing when we move further away from the STC condition in de Soto's case. We also did the experimental validation of the proposed model by taking the field measured IV data from OTF at Kiri for an entire day. The results show that the proposed model has less root mean square error compared to the de Soto's model when we calculate the overall power delivered by the PV modules. Lastly, a structural model is used to estimate the working life of a PV module under operation. While in service, a PV panel is subjected to 4 types of loading: mechanical loads, radiation loads, chemical loads, and the thermal loads. And in this work, we only considered the effect of thermal loads on the life of a PV module. If we look at the structure of the PV module, we notice that it consists of different layers stacked upon each other. The layers are bonded to each other by a polymer such as EVA, and as each of these layers is made up of different materials, so the layers have different coefficient of thermal expansion. Due to daily and seasonal variation of temperatures, each layer expands and contracts differently. This uneven expansion and contraction develops thermal stresses within these layers. Although the magnitude of these stresses is not huge, but their cyclic nature causes fatigue. And due to their small size, the copper interconnects are the most vulnerable to this fatigue analysis or the fatigue failure. And the literature shows that after corrosion, the failure of the PV module is due to the failure of the copper interconnects. Although the 3D FE approach is the most accurate but computationally very heavy, so this is not a practical approach. The main purpose of the finite element analysis is to study the stress strain distribution and variation within the solid domain of the PV module. To reduce the computational requirements, we first developed a 2D FE global model for the PV panel's cross-section. Under thermal expansion, the deformed shape of the PV panel shows that the maximum stress and strain is experienced by the portion of the copper interconnect in the middle. Then we use a 3D FE local model for the middle of the copper interconnect only in between the middle cells. So basically with this 2D plus 3D approach, we can get the best of both worlds. That is, we have low computational requirements of a 2D model and a higher accuracy of a 3D model. To make the simulations more reliable, near exact material models have been used for each layer of the PV module. The glass, Tedlar, and silicon were assumed to be linear elastic within the typical operating range of the PV module. The copper interconnects were modeled as bilinear elastic plastic with kinematic hardening. The kinematic hardening was used to capture the cyclic behavior of the copper. EVA, on the other hand, was modeled as viscoelastic. Using the aforementioned material models, we simulated the lamination process where the PV laminate is first heated to a temperature of 150 degrees Celsius and then it is cooled down to a room temperature of about 23 degrees Celsius. The simulated results show that the copper interconnect actually underwent plastic deformation, which is backed by the literature too. This is because the yield stress of copper at room temperature is almost 94 megapascal, while that generated in the copper interconnect under the lamination process is almost double this limit, that is 160. And also in this study, 150 degrees Celsius was taken as the stress-free temperature of the copper interconnect. Fatigue failure is caused by the cyclic loading, and if this failure occurs in less than 10,000 cycles, it's called low cyclic fatigue, and if it happens in more than 10,000 cycles, it's called high cyclic fatigue. Copper, which when plastically deformed is considered a case of low cyclic fatigue. And for low cyclic fatigue cases, the simplest model to estimate the number of fatigue cycles is the Kaufman-Manson rule. This model uses the plastic strain amplitude to calculate the fatigue cycles. And before using the 3D FE model for the fatigue analysis, we import the pre-stresses that were developed due to the lamination process as to mimic a real PV module with pre-stressed copper interconnects. To study the stress strain variation and to predict the fatigue life of the PV module, we chose 2 typical days of the year in Doha, Qatar, where the PV module under study has been deployed. The first chosen day is in the month of June, which is the hottest month of the year. The second chosen day is in the month of January, which is the coldest month of the year. And these 2 figures in the first column, they show the maximum temperature variation within the PV module for these 2 chosen days. And based on each of these days, we do the stress strain analysis for 25 cycles, as a minimum of 20 cycles are recommended to make the plastic strain converge adequately. Once the plastic strain amplitude converges, we can use it to find the fatigue life of from the Kaufman-Manson formula. And one more thing that we can notice is that during the middle part of the day, when the temperature of the module rises, there is some stress relaxation within the copper interconnects. This is because we took 150 degrees Celsius as stress-free temperature. For both these chosen days, the fatigue cycles were found to be less than 10,000. This further confirms our choice for the use of simple Kaufman-Manson rule to estimate the fatigue life. The fatigue life of the PV module under study was estimated to be around 23 years for the month of January, and it was found to be around 12 years for the month of June. And based on these, just these 2 days, which are the 2 extreme representations of typical days in Qatar, the average life of PV module in Doha was found to be around 17.5 years. It should be noted that this estimated fatigue life is not the actual fatigue failure, but rather the time of nucleation, which eventually expedites the failure rate. So in summary, we basically developed all 4 performance models of the PV module. It was shown how these models can be used to accurately estimate the yield and working life of a PV module. This work was done on the monofacial crystalline silicon PV modules, but can be extended to other technologies too. In the end, I would like to thank you all for your attention, and you can have now we can have the questions and answers.
Okay, thank you so much for the very thought-provoking and very insightful talk, and also for respecting the time dedicated to this presentation. Now we move to the discussion session, because the third presentation unfortunately will not be presented owing to a last-minute issue with the third speaker. So we can just move to the Q&A if we have any questions from the audience to the 2 speakers in this first session today. Check the. So you can either post your questions in the chat box or the Q&A box, or you can also raise your hand. You have the raise hand icon in the bottom of the screen you can use. Well, probably I can break the ice and ask one question to the first speaker, Professor Saad. Thank you again for the very interesting presentation. I would like to know what about the intelligent UPS. What's the this is maybe the is it a new trend within the UPS technologies and the paradigms, or what's the exactly the probably the I know you didn't cover this aspect in your presentation, but probably since we are in the digital era, and also the session is supposed to cover some digital techniques in the framework of PV technology. What would be the impact or the added value of the any intelligence that could be included in the for UPS monitoring or control?
Yeah, thank you very much, Professor Mohammed. So I think as all the areas of applications is moving towards intelligence, remote monitoring, remote control, autonomous operations, and so on and so forth. So I think UPS systems also, as a part of this, there are a lot of ongoing work on how to do the fault detection. We call online fault detections. Okay. Also, especially on the battery systems, especially the state of health of the battery systems, how long these battery systems will remain, or what is the lifespan that remains of the battery systems. So there's actually quite a number of works actually on the side of, beside the power electronics part, which is the rectifier, the inverters. In the battery systems, there's a lot of research on what will be the battery systems that can last longer and light in weight, and also the health of the battery systems, especially now, like we can see in the electric vehicles where there is a lot of battery systems including what will be the best systems that to manage this energy inside the batteries. So yes, I agree, there is quite a number of what you call research on artificial intelligence. These artificial techniques can be used actually in every areas or every domain.
Yeah.
And the main objective is to make it more autonomous, more online, and also cheaper in cost. Thank you.
Okay, thank you so much. Thank you so much for input. We have a few questions in the Q&A box. So we'll start with the first one by Dieter Meissner. Well, the question is addressed to the last talk, so the second talk. The predicted lifetime is much less than the guaranteed one. Is there any evidence from experience that this is really the case? I don't know if we have with us.
Yes.
Yeah, Nicolas,
I will answer the. Yeah, I will take the questions related to this presentation as co-author.
Yeah.
So yeah, the predicted the prediction here relates to the failure of the ribbons, and what we observed in field is not early failure on the ribbons like it is simulated here, but we took drastic simulation parameters in order to simulate what happens with a very simple fatigue model. So the probable more realistic approach of simulating more accurately the thermal load within the PV panels will probably enhance the simulation results toward a more realistic ones, which would be or not the crossing of the warranty period. The crossing of this warranty period is not established by firm standards for the climate of harsh climates of Doha. So it's an area of investigation for us.
Okay, thank you, Nicolas. Let's move to the second question. I think it's also for the second talk. What is the physical meaning of the RS variation you found for irradiance and temperature variations?
So yes, using the five parameter single diode model this way, the single diode model is used as a way to represent what happens on the IV curves of PV devices, and the shunt resistance, which is the RS parameter, would mean that there is a loss of the electric power from the device in this way. So it could happen also to what is interesting with this kind of approach. So the resistance is not a real one in anywhere of the device, But the way to look at this shunt resistance over time is a way to diagnostic what happens with the device, and could help to have early maintenance, for instance, of PV devices.
Okay. The third question from Mr. Ahmed Hanashi asks, how did you measure the PV panels temperature distributions? I think this is also your question. Yeah.
Correct. So the temperature experiments, they are thermocouples at the rear of PV modules. The experiments themselves consist of several PV modules, and this so simple array for experimental needs. There is one thermocouple at the rear side of the PV modules, one thermocouple per module, and they are located approximately towards the center of the module. So here we had comparisons of the finite difference method against the finite element method, but there was one single experimental point in the middle of the panel. And this is where the comparison was established. Okay.
Okay, thank you. Thank you. So once again, thank you for your talks. And now we'll move. That was the last question we had in this Q&A box. So now let's move to the next.
I think Professor Dieter raising his hand.
Okay, sorry, I didn't see that. So please, Professor Dieter, the floor is yours.
Thank you very much. I'm still wondering about the predicted lifetime, because in the field, this is a mechanical failure actually, which limits the lifetime of the module. So isn't the wind load a much bigger factor limiting the lifetime than the thermal stress, which you modeled? Can you model actually the wind load also, which is very important in the field?
Yeah, so the modeling here is for simple rack-mounted modules at 2 meter high. The mounting is fixed, so there is no like tracker or whatever. I know that for the trackers, the PV panels would be much higher, for instance, could be than 2 meters, and then subject to wind loads. Depending on the area also on Earth, you may have stronger winds in some regions compared to the Gulf region here. But the mechanical loading is, of course, something you can superimpose to the thermal load. So here we had the sun, and during the night, the PV module temperature is also cooler. So the cycle we have during the day, very hot in Doha, and the night is what was used to model what was the mechanical load inside. But of course, superimposing the wind loads, we could have predictions also dedicated to this kind of loading parameters. And the predicted lifetime, okay, the models used for the mechanical approach are so simple, even if the thermal load and the thermal conditions are very well established and compared to experiments. The mechanical model and constitutive laws could be refined also to a proper realistic evaluation of the lifetime of the PV modules. And see this PV module's lifetime as something that is average over a large amount of samples, and something you can be used also to compare one type of condition, one scenario against one other towards having the less critical mechanical loads of the panel.
Thank you very much. Excellent paper. Thank you.
Thank you. Thank you very much for your questions.
Thank you. Maybe we can pick another question. We still have another question here in the Q&A box. So Mr. Jawad Dweeby is asking, well, he's saying first that the transient PV thermal model you developed seems to be interesting. Do you think that this method could be extrapolated to study the dynamic performance of PV thermal PVT module for control purposes?
So again, the thermal modeling is here with the conditions under sun irradiation, and we don't have an active cooling of the panel here. The boundary conditions we use for the thermal model are very simple. They are based on the properties of air in contact to the different surfaces, so rear surface and the front surface. And with an adaptation of these boundary conditions toward a realistic modeling, thermal modeling approach of the PV thermal, yes, this could be adapted, and the efficiency also could be established.
Okay, thank you so much, Nicolas. Thank you so much. Professor Said Azdi, and I also like to extend my warmest thanks to Professor Saad Mihlif for the wonderful keynote talk session and discussion. Now we'll move to the 5 minutes. Sorry?
Before going to the 5 minutes presentations, if there is from panelists, if you have other questions, if you have questions,
yeah.
Dr. Baghdadi or Professor Baghdadi or Professor Saad Mutahar. Please activate your mic, Professor.
Yes. Yeah. Good morning. Good morning, everybody. I think Professor Mutahar is really specialist in this topic, and he could have some question or some comments or remarks about this session. From my side, I don't have any question for the moment. Thank you.
Thank you, Sir. Thank you.
Maybe Professor Mutahar, because he did so much works, so much studies in this topic, in this field, and I don't know whether he is here or not, but in any case, he is one of the specialists in the topic, and he could have some questions or some remarks or some comments on the presentations of this session.
Okay. Okay.
Yes.
Other questions, probably we can go with the rest of the program, and we can just move to the 5 minutes presentation session. We have here already several papers programmed in this session, and this session will be chaired by Professor Saad Mutahar.
The first presentation will be presented by Vinicius Marson from Sao Paulo State University, Brazil. ID 129.
Hi everyone, my name is Vinicius Marson, and I'm here to present you my research work called Theoretical and Numerical Analysis of a Passive Cooling System for a Commercial Photovoltaic Model. Besides me, the work has been done by Domisley Dutra Silva, João Batista Campos Silva, and Elaine Maria Cardoso. In this presentation, we will talk about the following topics: Introduction and Motivation, Energy Efficiency, Objectives, Materials and Methods, Experimental Apparatus, Thermal Analysis without the Passive Cooling System and with the Passive Cooling System, the Numerical Procedure, Results, Conclusions, and Acknowledgements. Here we have some facts about the solar PV energy production, which is free of pollutant emissions, has low operation and maintenance costs, positive social and economic impacts, and generates about 90% of mini and micro energy generation. As you can see in the image, in Brazil, the solar energy production have only 1.7% of the total, but this number has been growing a lot. As shown in the following equations, the temperature of the panel has a direct influence on its efficiency and power. The higher the temperature, the lower its efficiency, so we have an inversely proportional relationship. For the panel that we have, these are the constants. Tref is equal to 25 degrees Celsius, beta is equal to 0.44% per degree Celsius, and the maximum efficiency is 16.5%. The objective of this work is to analyze the generation of an stellar photovoltaic model and performs a theoretical and a numerical study for the system's thermal behavior, depending on the experimental conditions, including the impact of adding extension surface on the average model temperature. For experimental apparatus, we have one polycrystalline silicon model with 60 polycrystalline high-efficient cells. It has an uniaxial tracking system that follows the daily solar movement from east to west, as shown in this image, and the fins are positioned on the back of the panel in the red area as shown in this figure. The thermal analysis without the passive cooling system was made by the energy conservation principle, considering sky, ambient and ground temperatures, direct and indirect radiation coming to the panel, and energy leaving in the top and in the bottom of the panel by convection and radiation. In the right image, we can see the thermal resistance diagram from this case. For the thermal analysis with the passive cooling system, we have same analysis done previously, but now adding the fins at the bottom of the panel. In the image, you can see how the fins are positioned. The numerical analysis was made by using the mechanical tool present at ANSI software, and here we show the mesh independence study without and with the presence of the passive cooling system. As you can see, the computational temperature does not change too much by increasing the number of mesh elements, proving that the results has no influence by the mesh. For the results, we collected data for 2 sunny days, the 22nd and the 24th day of August of 2019. We have here the instantaneous output power for these 2 days. In this graph, we can see the average temperature of the panel along the day. From the top to the bottom, we have the experimental data written in blue, numerical in red, theoretical in yellow, all those without the presence of the passive cooling system, and the theoretical and numerical temperature with the presence of the passive cooling system written in blue and green. And for reference, we have the ambient temperature in light blue. We can see the same graph here, but now for the 24th day of August. It's important to note the small difference between the 3 curves without the presence of the passive cooling system. We can say the theoretical and numerical model without the presence of fins was validated. Therefore, we have reasons to believe that the model with the passive cooling system will predict the temperature successfully too, reaching our goal, since the temperature decreases about 7.2 and 6.5 degrees Celsius by adding the cooling system for the first and second analyzed days. As conclusions, we have that theoretical and numerical model without the presence of the fins was validated, and proposed passive cooling system decreased the operational temperature of the model, as we already said. And it's worth mentioning that the next stage of this project is to verify the passive cooling system thermal performance experimentally. We'd like to thank for the opportunity and your attention. Our emails for contact is here. Thank you all.
The next presentation will be given by Sajib Ahmed from Kuala Lumpur, Malaysia. The paper ID 135. The co-author also is Professor Saad Maghlif.
Welcome to everyone for the presentation. Myself, Sajib Mohammed, researcher from University Malaya, Malaysia. On behalf of my co-authors, I would like to present to a topic, comparative analysis of conventional and modified P&O MPPT controllers under partial shading conditions. These are the objectives of my presentation: design and implementation of conventional P&O algorithm, find out the drawbacks of conventional P&O algorithm, design and implementation of 3 different modified P&O algorithms to mitigate the major drawbacks of conventional P&O algorithm, comparison of the performances of the algorithms based on simulation results. Drawback of conventional P&O algorithm is as under: oscillates at steady state condition, unable to track the GMPP in case of partial shading conditions. The range of tracking is local search space only. In case of indirect control method, need to tune the PI parameters. To mitigate the major drawbacks of conventional P&O algorithms, 3 modified P&O algorithms are designed here, which are able to improve the performances of conventional P&O algorithm at different aspects. Name of the algorithms I am going to discuss in this presentation is conventional P&O algorithm and 3 different modified P&O algorithm, namely different step size method, scanning method, and trapezium method. This is the flowchart diagram of conventional P&O algorithm. Its operation is based on perturbation of the voltage and observation of the power. If power increase by increasing voltage, duty cycle requires to decrease. If power increase by decreasing voltage, duty cycles requires to increase. Alternatively, if power decrease by increasing voltage, duty cycle required to increase, and if power decrease by decreasing voltage, duty cycle required to decrease. This diagram is for different step size method. This method is same as conventional P&O algorithm. Exception is the duty cycle step size. Algorithm uses large step of duty cycle during convergence to the peak and small step size of duty cycle at steady state conditions. This diagram is for scanning method. In this method, algorithm starts scanning from middle of the PV curve towards the right direction until satisfying of an end criteria, and after that scans from right to left direction until satisfying of an end criteria. During scanning process, array voltage is continuously sampled and corresponding voltage and current are recorded. At any instances, if power is greater than previous maximum power, then corresponding power and voltage are updated. At end of the scanning process, reference voltage is bring at voltage corresponding to maximum power, and conventional P&O algorithm is applied to track the GMPP. This is the flowchart diagram of trapezium method. The working procedure of this method is similar to scanning method. The main exception is the end criteria of scanning at both left and right direction. This is the PV curve for partial shading pattern. We used 4 modules, so they have 4 peaks. Among the 4 peaks, one is global maximum peak and other 3 are local maximum peak. This is the output power, voltage, current, and duty cycle curve from the simulation result. In case of conventional P&O algorithm, we can see here that the algorithm failed to track the GMPP and trapped at LMPP, and tracking time is 0.016 seconds. These are output curves for different step size method. Like the conventional P&O algorithm, this algorithm also trapped at LMPP, but tracking time and steady state oscillations are improved comparing to conventional P&O algorithm. This curves is for scanning method. In this case, the algorithm successfully tracked the GMPP at a tracking speed of 0.175 seconds. Tracking speed is higher than conventional algorithm because this method needs to scan the whole PV curve to find the GMPP. This curves is for trapezium method. Like the scanning method, this method also successfully tracked the GMPP with a tracking speed of 0.125 seconds, which is less than the scanning method. Now I'll draw the conclusion of my presentation. From the simulation results, it has been found that modified P&O algorithms have improved the performance of conventional P&O algorithm on different aspects, whereas different step size method have improved the steady state oscillation and tracking time comparing to conventional P&O algorithm, but still unable to track the GMPP. The scanning method and the trapezium method track the GMPP at all the partial shading patterns, but tracking time and steady state oscillation is higher than conventional P&O algorithm, which is the shortcoming of these methods. The trapezium method outperformed the scanning method based on tracking time. Please don't hesitate to ask if you have any questions.
The next presentation the presenter Ravi Kiran Hermat from Mangalore, Malaysia, will present two papers, IDs. The first one, ID 184 and 185.
Good morning to all dignitaries. I am Ravi Kiran Hiremat from National Institute of Technology, Karnataka, India. On the request of the IRSEC team, I am merging the presentation contents of my paper IDs 184 and 185. My paper titles are Performance of DFIG Wind Turbine Generator System for LVRT Enhancement using Proportion Resonant Controller and Comparative Analysis of Different Controllers for Enhancing the LVRT of DFIG System. The contents of my presentation are introduction, literature, modeling of DFIG, LVRT analysis, resultant discussions, and conclusion. So in the introduction slide, maximum power is extracted from the wind is given by half rho Cp lambda comma beta AV infinity 4. If speed ratio versus power coefficient graph is drawn and is shown in the figure. Continuous operation of the DFIG system during faults like voltage dip and voltage swell is named as LVRT. During different countries, grid codes are shown in the figure. WFED induction generator based wind turbine is used in wind energy conversion system. It has rotor side converter, grid side converter, and capacitor between them. DFIG is very sensitive to the grid fault. The DFIG has been modeled using the given equations of DQ reference frame. Electromagnetic torque, stator real power, and reactive power are also given. So coming to the literature side, the author Tang, Das, and Zhu in 2018, they have worked on the transient rotor current and transient compensation and the speed of the generator. In the 2019, the Zhu again in the 18, Shahi, Bhattacharjee, and Vijay Priya, they worked on the DC-link voltage suppression and its control. In the year 2016, Mohammadi, he worked on the fast transient response. Coming to the drawbacks, the certain operating conditions leads to instability of the stator dynamics. Stator current is restricted and crowbar circuit to be turned off, increasing the rotor resistance and mismatch between the actual and reference values. So in this slide, controllers are key factors during LVRT. Different controllers such as PI, PID, and PR controllers are used for the LVRT enhancement. Performance of the PR controller is compared with the PI and PID controller. So here in active power control, PS and PS star difference generate the error and it is made as 0 using PI, PID, and PR controller. In the same way, IQR current is controlled. In the reactive power control, QS and QS star difference generate the error and it is made as 0 by PI, PID, and PR controller. And IDR current is controlled in the same way. Coming to the stability analysis, we can come to know that PR controller provides least variations. IQR, IDR currents are used to control the active and reactive power. The transfer functions are given for active and reactive power control. Gains of PID and PR controllers can be seen here. So in the result and discussion slide, simulation results of PI and PR controllers are compared. Rotor current, active power, reactive power, and DC-link voltage are shown here. Red line indicates the effect of PR controller. Dotted blue line indicates the effect of PI controller. We can see the performance of PR controller is better than the PI controller. So here, simulation results of PI and PID controllers are compared. Machine parameters such as rotor current, active power, reactive power, and DC-link voltage are shown. Red line indicates the PID effect. Dotted blue line indicates the effect of PI control. Coming to the complexities, the listed complexities are RS is unable to reduce the rotor inrush current for a short duration of 150 milliseconds under severe faults. Control gains doesn't respond adequately to three-phase fault. Different controllers of the DFIG system are complex to build. We have made some observations such as gains of the PI, PID and PR controllers are vary according to the severity of the fault. PR controller is better than the PI and PID. PR controller provides the proper uniformity under severe faults. Coming to the conclusion, both papers proposed the PR controller for the DFIG system under fault conditions. Results of the PR controller is compared with the PI and PID controllers. Stability analysis of the PR and PID controllers bring the effectiveness in the system performance. Simulation results indicate the improved transient response and elevative enhancement is achieved under the fault conditions. These are the references. Thank you. Thank you all the members and organizing committee of the IRSEC 2020.
The next presentation will be presented by Hisham Oufetoul from Mohammed School of Engineers, Rabat, Morocco. Paper ID 166.
Good morning, everybody. I am glad to be a part of this scientific workshop. First of all, I am Oufetoul Hisham, a PhD student at the Mohammedia School of Engineering in Rabat. This examination is named under the subject of the MPPT techniques investigation in photovoltaic systems. To clearly present this study, I hope to follow this outline. First of all, starting by a general introduction. Then, a quick overview about solar cell equivalent model and DC-DC converter. Afterward, we treat each MPPT algorithms techniques used in this study. Then, we discover the obtained results and we discuss them. Finally, we summarize this investigation with a small conclusion. Why MPPT techniques require? As known, the operating point of each system is the intersection between curves, source and load. So, in the absence of the MPPT stage, this voltage and its released current will be extracted, and it's clear from the figure that it's far from the MPP. Whereas MPP system with MPPT stage, the load could persuade the MPP thanks to DC-DC converter and control system. Concerning solar cell equivalent model and DC-DC converter, we used in this subpart the mathematical equation for modeling the PV cell either in MATLAB and Proteus. We used also buck-boost converter since it's strongly recommended by numerous papers in the literature. Now we dive in the MPPT algorithms. Now with enhanced P&O algorithm, P&O is considered most frequently used. As a result, we select it in order to enhance and compare. Its principle consists of perturbing dirty cycle in a certain direction by analyzing, of course, power and voltage. In this study, we use the large dirty cycle in order to achieve quickly the MPP. Then it comes the rule of small dirty cycle in order to reduce the oscillation around the MPP. About enhanced incremental conductance, it follows the same principle of P&O, while the incremental conductance addresses some P&O weaknesses like when the sudden change in climate. Concerning phasor logic, it's among the most effective methods used in the literature. This algorithm mimics the human reaction strategy and exhibits multiple advantages. The process of phasor logic follows these three steps: falsification, inference, and falsification. We used in our phasor logic model a variation of power and variation of current as the inputs of systems. However, several papers used variation of error and error as the inputs of systems. Here are some membership function of the inputs and outputs. We used Proteus software to be close to the real-world implementation. Here is the PV model connected to the load via buck-boost converter. The microcontroller works under the management of one of the algorithms that previously mentioned to interface transistor via this driver. About the results and discussion, here we have the enhanced P&O, enhanced incremental conductance, and fuzzy logic. So the figure depicted in black, it belongs to MATLAB software, while the results displayed in green, it belongs to Proteus software. So about P&O results, we mentioned here that there is some sort of the oscillation in the beginning. Also here we have the oscillation in the beginning, but it's not clearly visible, but it exists. Also in MATLAB results, we mentioned that there is some kind of slowness which translates by this slight curvature in order to achieve this MPP. About the enhanced incremental conductance, it has similar results as enhanced P&O algorithms, slight curvature, and the oscillation in the beginning. About fuzzy logic results, all it writes is fast, just needs some millisecond to reach the MPPT. There is no curvature here like incremental and P&O. Also, we have here some sort of the oscillation, but it's small according to the other algorithms. As a result, this work has examined 3 algorithms where fuzzy logic approach accomplish its function in terms of fast and the pursuit. This is one hand. On the other hand, further enhancement to P&O and incremental conductance make them more efficient. And thank you very much for your attention.
Recording in progress.
The next presentation will be given by Dai Han Phan from Hanoi, Vietnam. Paper ID 76.
Hello everyone, my name is Duy Phạm. I'm lecturer at University of Science and Technology of Hanoi, Vietnam. Today I would like to present my working title, Modeling and Simulation of Photovoltaic Pumping System used for integration. My presentation consists of 4 sections: Introduction, Modeling of Photovoltaic Pumping System, Simulation Result, and Conclusions. My study will focus on photovoltaic pumping system in remote area. As you know, crop integration presents a major problem in remote area where there is not enough rain. One solution is by pumping the groundwater into storage tank. Then the water will be used for integration as domestic. And this solution requires the electricity which is used to run the pumping system. In remote area, the photovoltaic system is a good solution to supply the electricity for pumping system. There are 2 configurations of photovoltaic pumping system. The first one is a photovoltaic pumping system with direct connection of the PV array. This configuration is simple, cheap, and not efficient under the variation of external connection. The second configuration is photovoltaic pumping system with MPPT connection of PV array. This configuration is efficient under the variation of external connection because we can extract the maximum power from the PV array, and the MPPT algorithm play an important role in this configuration of photovoltaic pumping system. That is why my working will concentrate on the photovoltaic pumping system which uses a permanent DC motor driving a centrifugal pump. One input photosynergic MPPT algorithm is used to regulate the duty cycle of the DC-DC converter. Figure 5 shows the model of PV array. Figure 6 shows the model of permanent manual DC motor in MATLAB and Simulink. Now we will design a one-input fuzzy logic controller for maximum power point checking. In the literature, there are several MPPT methods, and fuzzy logic controller have shown a lot of advantages. However, there are only two inputs in a MPPT fuzzy logic controller. This causes some complications when designing the rule of fuzzy logic controller. One input fuzzy logic will be presented and applied in photovoltaic pumping system. Its advantages is simple structure, fast response time. As a result, we will achieve the maximum water flow to save for irrigation and domestic purposes. The one-input MPPT fuzzy logic controller is developed from perturbation and observation method. In perturbation and observation method, the perturbation step of duty cycle is kept in constant, but in the proposed method, the perturbation step of duty cycle is variable and depends on operation point, so that we can improve the response time and exactly achieve the MPPT point. This is a model of one-input MPPT fuzzy logic controller in MATLAB and Simulink. Figure A shows the model of photovoltaic pumping system with direct connection of PV array, and Figure 9 shows the model of photovoltaic pumping system with MPPT connection of the PV array. The simulation results show the good operation of one-input MPPT fuzzy logic controller under the variation of solar irradiance. MPPT controller well regulated the duty cycle of boost converter to achieve the maximum power from the PV array, so that we have the maximum water flow to supply for storage tank. Figure 13 shows the water flow comparison between MPPT connection and direct connection. The amount of pumped water is increased a lot compared to direct connection system. Conclusion: in this working, the MATLAB Simulink model of photovoltaic pumping system has been implemented, and the simulation results show the good function of photovoltaic pumping system with MPPT connection of the PV array. Thank you very much for your attention.
The next presentation will be given by Adil Shahat from West Lafayette, USA. The paper ID 68.
Hello everybody. This new paper about experimental project for bicycle generation station for portable DC charging. The team is includes Nicholas Carson, Aubrey Lee from Georgia Southern University, Department of Electrical and Computer Engineering, and myself, Adil El Shahat. I'm within School of Engineering and Technology, Purdue University. The outline of this presentation will be abstract methodology of the proposed system implementation, outcome of implemented system, conclusion, and reference. The main goal for this paper is to design and construct a bicycle generation station that can be used to charge the batteries for small electronics devices such as a cell phone. The station the team is constructing would be built on a mobile platform for easy transportation and for demonstration. The project is designed and inspired to be used for students to charge their cell phone while exercising in campus. The concept of those stations can be implemented into the recreation activity center on campus and outside other buildings on Georgia Southern, and the station will be constructed from a bicycle and pre-manufactured stand with a DC generator that is implemented with battery for storage. After electrical energy is stored, the power will be converted from 12-volt DC to 5 DC to be suitable to the cell phone, for example, and 12 volt to 120 VAC as alternating current to be suitable for other AC loads. The AC power generated by the stand will be used to power small AC devices such as a clock, or supplied back into the Georgia Southern Power if we have it on mass production or more than one station. Also to help in the power consumption in the university. The project also incorporate other electrical components used for safety and monitoring of the bicycle generation station. And also one of the benefits for this project is the exercising and its effect on human life. So the methodology of this one, this is a block diagram to illustrate the mechanical and electrical components in connection with each other to be implemented. Before we started, we designed it in a video and we examined it using different softwares like Multisim and MATLAB before we start building or implementing it. This is also another block diagram with more details about the DC-DC converter and DC-AC inverter and the switch between them to switch between the battery storage devices which can supply the AC or the DC based on the converter which we are using to elevate or to decrease, to decrease the level of the DC voltage, or to switch from DC into AC to be suitable for AC loads. The system implementations, various or different steps, starting from unpack the medium density fiber boards, and then start to screw down to outside the fiber board as seen here and highlighted here. And also for the step number 3 here, we start managing this board and unpacked it while trying to build the stand completely and also attach the main components for the charging for the bicycle stand before embed the bicycle and embed the other controller and inverters and DC-DC converter and batteries as well in this board. Here it is. This is just a photo shot for the converter voltmeter for the cell phone charging and the outcomes of the implemented system. And this is while the cell phone charging. However, one of the team was exercising using this bicycle. So this bicycle generation station is designed to power and charge the smallest scale DC loads by storing the renewable energy created into 12 volt, which is clean and for free by exercising, so it can help you in your health, plus giving you some power, some free of a charge power while you are in exercise. Also here, after the user attaches their own personal bicycle to the system, attach the appropriate wire connections and then begins pedaling. Clean energy is produced to power the devices and to the battery for the future use. Or you can store the excess of the power in the battery. All throughout the design and implementation of this one, as a conclusion, all the professional components topic we have addressed, and the station doesn't produce any electronic waste, and also it doesn't have any harmful environmental concern. Also, the cost for this one is very cheap to handle this work. These are the list of our reference, and thank you so much.
Now we switch to the discussions. Professor Saad Mutahar. Professor Saad. Please switch on your mic.
Did you call me?
Saad Mutahar. Yes, Saad Mutahar. If there are from panelists questions to authors about their papers or their presentations. Yes, yes, Professor Dieter.
Thank you very much for the interesting papers. I actually have a question concerning the Hanoi paper, comparing the control of the pumping system, photovoltaic pumping system. Somehow I missed the final conclusion. Can you give us the final results in terms of how much water is pumped in direct coupling and how much water would be pumped using your control system?
Yes, thank you for your nice question. Could you hear me, Professor?
Yes.
Yes.
Yes, so your question is about the MPPT. Yeah, because I propose the two configurations. The first one is is a direct connection, which means that the PV panel will supply the power directly to the pump without the DC-DC converter and MPPT algorithm. And this configuration is not efficient. And the second configuration is using the MPPT algorithm. And in this case, I use one input fuzzy logic MPPT controller to regulate the duty cycle of converter and the simulation results. So thus we can extract the maximum from the PV array, and so that we can get the maximum water flow to supply for the domestic and integration.
Yeah, but how much more can you pump if you use your control system?
How much pump? I use only one pump. One pump is centrifugal pump. Centrifugal pump is the permanent minus DC motor. We were inside the centrifugal pump.
I understand this, but the user, of course, is not interested in how much power is converted or whatever theoretical physicists may be interested in. He is interested in how much water is pumped. Okay, so if you compare two systems, I think the final result should be given in terms of how much water is pumped, actually, isn't it?
How much water pump? Because in the comparison, I saw only the water flow comparison between two systems. I saw you in the I think in figure in this, I don't remember the slide, but in the comparisons between two systems, you can see that the amount of water flow in the MPPT is bigger a lot than the direct connection. But the number, how much pump, I don't have any idea.
Thank you. And also I have a question concerning the Purdue paper, actually. How long do you have to cycle to charge a mobile phone, actually, on your system?
I think the author is not online. Adil Shahat is not online.
Okay, too bad. Thank you very much.
Dr. Saad Mutahar, you are online?
Maybe I have a question. I have a question for paper 166.
Go ahead.
Is Mr. Hisham is there?
Hisham, paper ID?
166.
The co-author Hisham Saad Mutahari is there. Dr. Saad.
Okay, okay. If there's the authors are not around, maybe you can. All right.
So there is a question asked by Ahmed Hannashi. He don't specify the authors, and he asked for, I did not get how the passive cooling is applied. Mr. Ahmed, you can talk, please, to give more information about your question.
Other other questions from keynote speakers. Nicolas, Professor Dr. Nicolas, if you have questions to authors.
I'm sorry, can I disturb you?
Yes, yes, yes.
Yes, I understand the question. Professor, he asked me about how much the power pumps. So my answer is the power pump is 3 kilowatt. I'm sorry, because maybe I misunderstand the question. The power pump is a 3 kilowatt. So I check in my simulation.
Thank you very much. But my question was how much water is pumped. The comparison of systems should be given, in my opinion, in terms of what is really the improvement in water pumping if you add your electronics. Because every electronics added, of course, also lowers the resilience of the system. So it's not straightforward that you want to optimize really the power. It's more important how much you really win by adding an additional system, which may fail at one point.
Yes, thank you. But here I comparison the water flow only. I don't calculate the total water we can get from the pump. So I compare the water flow only.
Yeah, and in terms of water flow, what is the difference? How much, what is the percentage of improvement?
As a percent, yes. Okay, so for the percent, I have to recalculate it because okay, yeah. I have to recalculate to show the efficiency, how much a percent we can improve. Yes, thank you for my questions.
Thank you.
There is a question from Zuhair Nui. He asks Mr. Vinicius, how to cool the PV panel with a small heat sink. On the backside, you are utilized the air for cooling and their properties. Thermophysicals are less than water and nanofluid. The question is for Vinicius.
Hey,
Yes, I am utilizing the air, né? So, and air don't have the properties of water or nanofluid, but it can cool the PV as shown in the graphs, né? You have the advantage that we can use the airflow that we already have, the natural airflow, right?
Okay, thank you. Other questions from panelists or from attendees? Professor Saad Mekhlif, you have questions to authors?
I have no questions, sir. I have no questions.
Thank you very much for your interventions, your talks, your keynote talks, Professor Saad Mekhlif and Professor Said Hazi, and moderated by Dr. Nicholas Batz. Thanks also for Professor Dieter Messner for joining us in this discussion. Thanks also for all authors presenting their papers in this session. Thanks for attendees. I think it is time to close this session. And if you have words before closing this session, the floor is yours. Professor Saad Mekhlif.
Thank you very much. I think it was a very interesting and good session. So I would like to congratulate all the authors for their excellent work. Also the organizers for the very excellent conference. So we hope to see you in the future. Thank you.
Thank you very much.
Thank you.
Dr. Nicholas. I think thank you very much, and see you in the next session of green hydrogen in few minutes. See you. Bye-bye. Good morning.
Good morning again.
Hello, good morning.
Mr. Jimrani, Ibrahim, are with us?
Yes, good morning, everybody. Happy to join.
Okay. Before giving you the floor, I'll give a brief presentation of Professor Mr. Abdurrahim Jumrani. Mr. Abdurrahim Jumrani is the engineering director of Mazen Electrical Energy Specialist. It has been active in energy sector for more than 30 years. Head of multidisciplinary engineering team, Mr. Jumrani has to identify the appropriate renewable energy project to be developed in order to respond Moroccan electrical demand. He is also in charge of the facility studies of renewable energy products and to elaborate the technical terms of reference. During the procurement phase, the engineering team managed the technical part of the tender until the financial closing. The managed project's investment reached more than $3 billion during the last 7 years. Prior to Mazen, he has the energy director for CMH Group, a fuel oil supplier, actually Winkso. He served as procurement director for the National Electric Utility (ONE), where he worked beyond other on fossil fuel hedging, coal, gas and oil, and wind parks. The yearly activity of ONE procurement direction was $1.5 billion per year. Mr. Jumrani participated actively in the legal, financial, and technical structuring of the Moroccan General Rural Electrification Program, PERG, in the implementation of the program. The rural electrification rate in Morocco reached 99% recently, while it was less than 15% by 1994. Mr. Jumar has a degree in engineering from INPEC, Grenoble, France, and the MBA from NPC, École Nationale des Ponts et Chaussées, Paris, France. Having received in 2001 the National Merit Wissam of Excellency by His Majesty the King Mohammed VI, God assist him. Mr. Jumrani was finalist in the 2019 Industry Lifetime Achievement Award of the African Utility Week. He received in 2001 the IEC 19/6 Award for the contribution in the development of international technical standards. Mr. Jumrani, the floor is yours.
Thank you very much, dear friend Yusuf, and really happy to retrieve this panel and this great scientist to discuss today the perspectives of hydrogen development. Let me first just say that hydrogen and let's say green hydrogen now can be produced at a cost that can be competitive to blue hydrogen. The issues are not only in production, and that is important to know. We should also analyze the uses and storage of hydrogen in order to be able to be sure that hydrogen can compete in the future years or future days. During the today panel, we will have honorable scientists that will discuss all these points, and I hope we will try to analyze how should be done during the next years in order to be sure that hydrogen is developed in our country, Morocco, but also in the continent, in Africa, and globally on the best way. So I will not be long, and I will just call my colleague, Mrs. Sonia Kalnan, to make the first presentation. Mrs. Sonia Kalnan is a research group leader at the Competence Center Photovoltaics Berlin Institute in the Helmholtz Zentrum Berlin. She investigates how renewable energy sources such as photovoltaics can be integrated with electrochemical reactions for low net carbon fuels. Since 2009, Sonia has led and contributed to several international and national projects focusing on technology transfer as well as research and innovation in the field of renewable energy. She has a PhD in electronic and electrical engineering from Loughborough University in the United Kingdom and the Master of Business Administration from Leicester University of United Kingdom. She will talk us about the scientific and technological progress in green hydrogen based on solar power water electrolysis. So Sonia, the floor is yours. Thank you.
Yes, thank you very much for the introduction, and thanks very much to the organizers for inviting me to this conference, and also thank you and welcome to the audience for to this talk. So as already mentioned, I'm Sonia Kalnan, and I'm here to represent the results of European Commission funded project that ended in December 2020, and that project was called the PEXIS. And in that, there was the focus was really to look at different, let's say, innovative technologies to achieve green hydrogen production using solar energy. Okay, so I have to put a disclaimer that the information and presented here is only the opinions of the project consortium and not of the European Commission. So now a fact sheet about this PEXIS project that we had. This project started in January 2017 and ended in December 2020. And the title was to demonstrate a system for solar-driven hydrogen production on an area exceeding 10 meters squared. And there were several targets at the beginning of the project, and one of them was the exceeding a hydrogen production rate of 16 grams per hour. And then another one was to have to demonstrate a solar hydrogen efficiency exceeding 6%. And then to show that the device could be stable such that after half a year of operation outdoors, the efficiency would not have reduced by more than 10% from the initial value. And then there was also a cost target of the levelized cost of hydrogen production, which was supposed to be less than €5 per kilogram. So all these targets were looking at things such as the yield, efficiency, and service life, which in the end would lead towards showing the economic feasibility of this technology. I am from Helmholtz Center Berlin, one of the partners of this consortium, and I was also the coordinator of the project. The other partners were Forschungszentrum Jülich, also in Germany, a public research center, Uppsala Universitet, a university in Sweden, the CNR, a national research center in Italy, Enel Green Power, a utility, an electric and gas utility company based in Italy, but also headquartered in Italy, but also represented in several European and I think South American countries. And then Solibro was a company that was owned by Hanergy, and this was the research center in Uppsala in Sweden. But their contribution was only until the end of October 2019. Nevertheless, there are some results which where they contributed. So the motivation of this project was to really scale up and prove the technical feasibility of directly coupled photovoltaic electrolysis. And another motivation was to understand and better understand the effect of variable solar irradiation and thermal management of the systems used for direct solar hydrogen production. And we approached the task by, in some cases, reducing and or simplifying the balance of plant, especially on the electrolyzer part, to permit modularity of these units and therefore also reduce costs. We also eliminated the power regulating electronics by carefully matching the voltage output of the photovoltaic modules to the electrolyzer so as to enhance the solar to hydrogen conversion efficiencies by minimizing the losses via coupling. And then in some cases, as I will show later on, we used thermal integration of both the PV and the electrolyzer. So there was a heat exchange between the two to benefit from the opposing temperature response. In this, I mean that usually when it gets too hot, the output voltage of the PV modules goes down, whereas in the electrolyzer side, when the temperature of operation of the electrolyzer increases, the voltage needed to drive a particular amount of current through the electrolyzer is reduced. And therefore, by cooling the PV module and using that excess heat to heat up the electrolyzer, you eventually boost the overall efficiency of the system. So the whole point was to exclusively use the incident solar energy to provide both heat and electricity to the electrolyzer, thus enhancing the solar to hydrogen efficiency while maintaining a near zero carbon footprint. I mean near zero because, of course, up to now, most of the components used for the electrolyzer and photovoltaic modules are anyway made in factories where the electricity is powered by the normal mix. And of course, in this mix, there is carbon, there's some sources that emit carbon dioxide. So going back to the project details, here I just like to describe briefly the concept that was used in the project. And this was the concept of directly coupled photovoltaic electrolysis. So here you see a schematic where you have the photovoltaic cell, which is directly connected to an electrochemical cell or stack. So usually if you hear of these large grid systems, there's always some sort of power electronics managing the voltage levels, managing the power coming from the PV modules to the electrolyzer. In our case, we eliminated this so that we could reduce just the costs of the system. And if you look on the right-hand side, you can see the current density versus voltage curves, and the red one shows the characteristic curve of an electrolyzer, while the blue one shows the characteristic curve of a photovoltaic module. So where these two cross is the operating point of the coupled device. And of course, there are some losses which have to be reduced, and this is done by either improving the type of materials you're using or by improving like the engineering of your system. Just for those who want to know, the solar to hydrogen conversion efficiency is given either by the current at this operating point multiplied by the voltage required for water splitting, multiplied by the Faradaic efficiency, divided by the power of the incident light. In another way, you can also calculate this using the amount of hydrogen produced divided by the total energy incident on the the PV module. So under standard conditions, a minimum reversible voltage is required to run the overall reaction of splitting the hydrogen into the water into hydrogen and oxygen. However, practical photoelectrolysis requires voltages higher than 1.23 volts because you have parasitic loads somewhere and you also have some connecting cables. And also the system never really operates at 25 degrees. So there's always some differences caused by the prevailing atmospheric environmental conditions. So for this reason, the photovoltaic modules must be sized so that the photovoltage over a wide range of operating conditions is sufficient for driving the electrolyzer without the need for a power supply from elsewhere. So we use two configurations for direct coupling of the photovoltaics to the electrolyzers. In one case, we have the photovoltaic electrolysis. Here you have the photovoltaic cell and one side of it is connected directly to the electrolyte and one of the electrodes and to provide the water splitting. So for this case, of course, since part of the PV cell is also seeing the electrolyzer, you can imagine that one has to have protection against corrosion. And this is really one of the research priorities because at the moment, the lifetime of these devices is quite limited. Another research priority, of course, is to increase the current density. Then for the wired photovoltaic electrolysis, this is basically like the common, you have photovoltaic cell and then an electrolyzer, and then you eliminate the power electronics, and then you have very short wires. So in this case, of course, the photovoltaics are separated from the electrolyte, so you have a reasonably longer service life of several months, even years. However, research priorities also include reducing the ohmic losses for this connection because you have a significant connection, cable length of maybe even just a meter or less, but that's still something affects the amount of power that you're able to transfer between the two components. And also, as I already mentioned before, another thing is to match the power output of the PV to the electrolyzer in all conditions. So the first prototype was based on a thin film silicon photovoltaic device. And this was a wireless monolithic design. So the back of the PV cell actually also was in contact with the electrolyte. And so they started with a small cell with electrode areas of 0.5 centimeters squared. And you can see that a solar to hydrogen efficiency of around 6.5% was achieved for this cell. But after some time, the output reduced because there were problems with corrosion. Nevertheless, with some different type of engineering, a bigger device was made, and you can see the different parts of it. And this was not a single cell, but actually a module. So each stripe corresponding to a different cell. And then at the back of it were the electrodes also for the electrolyzer, for the electrolysis part. And for this system, a solar to hydrogen efficiency of 4.5% could be found. But unfortunately, after some time also, this started to die down because of the attack by the electrolyte on the back of the PV module. So those who want to have more information, the details are in this paper. Excuse me. In another prototype that was made in Sweden, in this case, they had also a photovoltaic cell stuck to an electrolysis cell, but in this case, the photovoltaic cell is protected from the electrolysis cell by the nickel plate. However, the two of them are in thermal contact. So the photovoltaic cell in this case was using silver doped copper indium gallium selenide, and the electrolyzer was using nickel form electrodes with potassium hydroxide. And over the course of time, different catalysts were used, and this led to improvements in the solar to hydrogen efficiency from 9.1 and to the end of the project at 13.4% maximum. And then when they ran the system for several hours, it reduced to around 11.3. Since the solar collection area was relatively the same, of 100 centimeters squared, you can see that by increasing the solar to hydrogen efficiency, also the output of the device increased. The output production capacity, let's say, of the device increased. If you want some more details, there is this paper which was published. All the papers that I mentioned here that were published by the project are open access. So if you can find them, you can easily download them and read them. No need to subscribe to a journal. Then in another system, which was developed at the Helmholtz Center Berlin in my group, we used silicon heterojunction photovoltaic modules and nickel alloys with other transition metals as catalysts in potassium hydroxide. This whole approach was really to reduce the cost as low as possible. So in a first prototype, which you can see here, you have the photovoltaic module on top, and it's directly stuck onto the electrochemical cell. And this was tested outdoors and under different conditions. And if you look here, you see a graph of irradiance as a function of temperature of the photovoltaic cell module. And on this side, the hydrogen flow going from purple to red. Red is the highest hydrogen flow in grams per hours per meter squared. And similar here, you have the solar to hydrogen efficiency and going from purple to red, and red is the highest. So in this paper here, we could see that actually the device works best at when you have a high irradiance, but low temperatures. So this is around this part. When it gets too hot, unfortunately, we're not able to fully cool the PV device to achieve the high efficiencies. However, later we scaled up, we changed the device and included sort of heat exchanging part where the electrolyte was allowed to run behind the photovoltaic modules before entering the electrolyzer. And you can compare this. This is the size of the new system with an area of 2,600 centimeters squared. And with it, you can see that under laboratory conditions of 1,000 watts per meter squared, this smaller system had an efficiency of 3.5%, but the larger one was later improved to even reach 6.1%. And outdoors, it does reach efficiencies, average efficiencies around 10%, but that work was then done after the project ended. If you want more information, you can find it in these papers. They're also online and open access. This is the second last last approach that was developed. And in this case, this was done by the colleagues in Italy in conjunction with the colleagues from Jülich, who provided them with PEM electrolyzer. So here they had a silicon heterojunction PV module, which is bifacial. I think you can see, if you can see carefully, that there is, the module is semi-transparent. So which means that any light from the back of the PV module can also be used to generate electricity. If you look here at the current voltage curves, the black one represents one where you wouldn't have, where the back of the module would be blocked from receiving light. And the blue one shows the bifacial one, where you're also collecting light from the back. And the green curve shows the polarization curve of an electrolyzer. And you can see that the electrolyzer crosses the bifacial module at a higher current than the one of the monofacial module. And therefore, this means since current directly translates into hydrogen produced, this translates into a higher hydrogen production. And this you can see here on this plot of irradiance and solar flux as a function of time on a given day. And you can see that the bifacial module provided more power to the electrolyzer and therefore led to a higher amount of hydrogen than the monofacial module. And similarly, the solar to hydrogen efficiency was higher for the bifacial module than the monofacial module. So in this case, they used the 30% albedo effect by this concrete background, but basically you could also put white paint and further enhance the albedo effect. And this device showed a stable operation for around 55 hours in Sicily. The details can be found in this paper, which is listed here. It's also open access. Then the last one was the demonstrator, which was on an area bigger than 10 meters squared, as was required by the project. And in this case, we had commercial size photovoltaic modules. In the foreground, you can see silicon heterojunction modules from Enel Green Power. And in the background, you can see copper indium gallium diselenide modules from Solibro. And at the back of each of these modules, there is a PEM electrolyzer that is hung directly. So there's really no power electronics between the two. And behind each module, each solar module is an electrolyzer stack. So this way you have different, you can have basically a set. Just the two of them together is a set, and that's a whole plant. And then if you want to extend the capacity on your roof, you can just buy another one, and then it's flexible to the sizing. Your, let's say, array is flexible. So in this case, there was also a simplified balance of plant, and there was only water feed through the cathode, and no pumps were used. The electrolyzer was neither heated nor cooled. And as I already mentioned before, there are no power electronics. So if we look at this table and look at other systems where they also had photovoltaic cells directly coupled to PEM electrolyzers, you can see here one that was demonstrated in Saudi Arabia and another one in Japan. The one in the Pexis, the one that was demonstrated in Pexis operated for over 6 months. And over that time, it had an average solar to hydrogen efficiency of 10%. And the hydrogen production rate was also higher than the other systems. The other systems were operated for 10 hours and 20 hours respectively. So basically, this plant achieved better efficiency and longer operation than had already been reported in the literature. So just to summarize, there was various types of photovoltaic electrolyzers that were developed in this project. The first three were actually of a lower technology readiness level, but in that case, they were really trying to look at the next level using low-cost materials. In all cases, the catalysts were really transition metal-based, and in this way, we were using alkaline electrolyzers. So this is the monolithic PV one. This is the copper indium gallium based one, and this is the silicon heterojunction based one. And you can see also that by the time we got to this stage, we had really increased the size of the system. Then on the other hand, we had the let's say, more advanced systems where really both the electrolyzer and the photovoltaic cell are already really quite advanced, and there is less degree of integration, and so the temperatures of both devices are more or less independent of each other. And in this case, they used PEM electrolyzers, which were using platinum and iridium catalysts. But nevertheless, here we were able to show really high capacity, especially here. So each of these modules, especially of the silicon cells, were 2 meters squared. And just by combining the whole lot, we got an area of more than 10 meters squared. So one would like to know then, where do we lie in comparison to the literature? So here is a graph of solar to hydrogen conversion efficiency as a function of the solar collection area in centimeters squared. The blue points are for systems where the electrolyzer used non-platinum group catalysts, whereas the red ones are for platinum group catalysts. And the empty symbols are without thermal integration, and the filled symbols are for thermal integration. If you look at this graph, basically everybody would like to be with the highest efficiency on the largest device. And you can see that all the devices that were developed in the PEXIS project are really on the right-hand side, and we were really moving towards this corner here. But generally, you can see that, of course, better performance is always with the platinum group catalysts. And I can't, because of lack of space, you can't really tell what materials are behind these solar cells. But if you look at this paper, the cells, the absorbers that contain silver and indium always give better efficiencies. And as already said, corrosion resistant materials are needed for those photoabsorbers that are in contact with the electrolyte. And as I mentioned before, the advancement in the PEC was that in the PEXIS project was that we're able to push the scale and the solar to hydrogen efficiency. And as I said before, we showed among the best efficiencies in class for different sizes and sizes of solar collection area. So one would wonder, what could this technology be used for? So there are two possible uses. For example, decentralized and off-grid. This could be small capacity, a few kilowatts, maybe for local, for housing units, or maybe small hotels. And this could be used for heat and electricity generation, and also storing excess electricity from, for example, PV modules. And then the other one would be a distributed option, distributed hydrogen production, let's say at the source, where at the point where the hydrogen will be used. And for example, in this case, by industrial users who would then maybe produce chemicals, fuels, or use it to heat their steel, or to process their steel, or to produce fertilizers. And such a system would be maybe a few megawatts in size. And then there is also an option that, okay, you could put a switch, a simple switch, not power electronics, so inverters, but really just a switch to switch between providing electricity for the grid services or providing electricity to the PEM electrolyzers. So now, of course, this is the next stage of the project, and one of our partners is looking for ways to finance this. So in conclusion, I showed that several directly coupled photovoltaic electrolysis approaches were investigated, and these were spanning different levels of technological maturity and component integration. And thermal integration does boost the efficiency and the hydrogen production per unit area. And of course, the approaches also showed among the best efficiency and capacity in class for each approach. And of course, in the future, there is need to scale up all these other concepts to reach a higher technical maturity so that they become more commercially feasible. And of course, the durability of the electrolyzers needs to match that of photovoltaic cells, which is at least 25 years. At the moment, electrolyzers reach maybe 10 years or a little bit more. And then, of course, for the monolithic photovoltaic electrolyzer, where the absorber is in contact with the electrolyte, there's more research needed to either get, especially to find more corrosion resistance materials. Of course, we always want to close the gap between the theoretical and practical solar to hydrogen efficiency. And then there's need to look at studies that optimize both the location and size of such a system while considering the socio-economic, technical, and economic environmental factors. Thank you very much for your attention, and we acknowledge the funding from the European community for this project.
Thank you very much, Dr. Kalnan, for this presentation. It was really rich, and I think that there is a lot of questions about the presentations. But if you allow me, we will let the question at the end of the 3 presentations. So I will now call Mrs. Oroza Eraon. I hope that I am spelling it well. Who is a lawyer and energy analyst who has worked in the United Kingdom and Nigerian energy sectors. Her work cuts across providing support to stakeholders and governments toward electricity market design, monitoring, and evaluating energy access and the strategy implementation of net zero transition and decarbonization systems. She has a degree in law from the University of Derby and a master's degree in law from Nottingham Law School in June 2021. Ogoza was recognized as the INI Africa Woman in Energy. She has worked in the Institute of Energy Systems, University of Edinburgh, and a member of Women in Green Hydrogen Network. Mrs. Oroza will talk us about the role of green hydrogen in energy transition for Africa. So, Mrs. Ogoza, the table is the floor is yours.
Thank you. Thank you, everyone. Good morning. I'm just trying to get this off and let me know if you can see my screen. Okay. Right. Thank you so much. Good morning, everyone. Thank you so much for the organizers and for the panelists and have spoken before me, as well as the audience on ground. So just a quick introduction. My name is Owosai Rahan, and it's Miss and not a doctor either. And I do have a legal background. I'm a qualified lawyer in Nigeria, and my experience does span across the electricity market as introduced. Also doing a great job with the Women in Green Hydrogen, trying to set a network in for African nations. So if you're interested in joining, please just leave me a note or you can connect with me on LinkedIn as well. So I'll just get straight into that. So today I'm going to be talking about a few things. The first is going to be the Africans' role in the energy transition through green hydrogen. It's a pretty mundane conversation, but as well, maybe not as technical as the panelists before me, but I'll try to break this down as much as possible in the socioeconomic and as well as financing areas. So maybe just a quick brief as to the global CO2 emissions category and why we're actually having this conversation about decarbonization and as well as the energy transition. Over the last 100 years, more like, we have experienced an increase in CO2 emissions from fossil in the industries and as well as in cement production or steel production. As you can see from this graph, there's been an incremental increase over the last few years. In fact, we're currently at the highest point of CO2 emissions globally, and this particular graph from our World in Data is last recorded in 2020. So it really just shows you the peak we've had. A lot of people speculate that the peak fell down during the pandemic year, earlier this year and a good part of last year. But again, that's really difficult to evidence because the world is picking up again and there are more activities going on. So globally, we have to have a strong hold on the increase of CO2 emissions in the atmosphere in order to avoid an exponential increase in the next 100 years, if that's the case. So what role does the green hydrogen actually play in the energy transition? So hydrogen is expected to actually meet close to 15 to 20% of the global net zero energy mix. There's actually been conversations, and I'm sure the technical discussions prior to mine have proven to this, which have enabled and which are currently enabling for hydrogen to be introduced in the energy transition. This is true, commonly known as the gray and blue hydrogen transition. However, the green hydrogen is actually the one that proves the most efficiently for low carbon emissions. Also, green hydrogen accelerates the energy transition, as I mentioned just now, through clean energy technology. So Dr. Sonia did a fantastic work just now showing us the different technologies that have been approved and are currently doing amazing, transferring radiation from the sun into producing cleaner energy that can be used for other sources. Green hydrogen plays a very important role in carbon-free, in climate neutrality, which is the Global Climate Neutrality Fund for 2050, which is getting towards the net zero capacity globally. And on financing, the clean hydrogen markets could potentially reach an average of 10 trillion by 2050, and that's enormously going to affect the GDPs of a lot of nations across the world. So the green hydrogen transition in energy, in the energy transition can be seen through a lot of field of different hosts. Currently, there's been speculation about whether or not green hydrogen can be used for industrial heat. I guess I'll leave that for a different part of the conversation. But at the moment, hydrogen is being tested for investment to accelerate cleaner mobility. And hydrogen power stations are actually abreast in the Saudi Arabia and America, as well as the Oceania countries like Australia. The application for hydrogen are very diverse, and as you can see here, it's currently being used for different transportation lines, even synthetic fuels, as well as aviation industries. There are a lot of conversations about using green hydrogen as well to reduce the emissions from the normal electricity access provisions. And then there's also on the far right being used for feedstock in the chemical manufacturing and as well as plastics industries. The steel production industry has been using hydrogen since the beginning of time almost, but there's now an opportunity to find cleaner, true green hydrogen processes for actually heating or cooling metals and cement industries as well. So how does Africa, how are African countries actually taking a part into the global hydrogen demand? From this particular graph, which is by Global Data, they predicted actually that by the 2030 mark, we're not going to be seeing a significant increase in the global green hydrogen demand, because as you've experienced, the technology is quite new, and there are a lot of regulatories, which I'll go and talk about in a bit, that have to be in process. However, by the mark, which is the net zero carbon mark 2050, we're expected to see a significant increase of over 50% in the use for refining, power to X, transport, buildings, industry, as well as synthetic production and ammonia. So the key considerations when expanding the horizon for green hydrogen from an African perspective is that the first thing is it presents an opportunities for African nations to actually build resources for the net zero energy transition. For a very long time, African countries are the biggest impact to climate change and the global warming impacts through flooding, high sea level risings, and then drought as well. And this opportunity from green hydrogen actually allows African nations to maybe take a bigger share into the net zero energy transition economy. Green hydrogen also presents an increase in sustainable economic development across Africa. Investment in green hydrogen will increase the chances of more jobs, opportunities for advancement, as well as infrastructure increase. It also creates an opportunity for the African nations to increase their trade, knowledge sharing, and transfer of resources, which I will go to speak further about later. And one very big dilemma that a lot of people have given feedback regarding green hydrogen is the impact it has on the continent's energy access. So the global demand for green hydrogen actually has an important complementary role in the sense that it feeds into providing energy for the continent while creating an economic prospect for the continent as well. So I generally refer to this particular atlas, which has been produced by the H2 Disclaimer Atlas, which focuses on the importance and the prospects for green hydrogen in West African countries. It doesn't really reach out to a lot of other countries at the moment. From what I understand, it's currently being inbuilt, which is exciting. But what this atlas actually does is create a futuristic idea of what's currently on ground for green hydrogen prospects in West Africa. So at the moment, with what's signified on the far right, at the bottom right here, we can obviously see countries like Nigeria dispersively have a large impact to actually produce green hydrogen. However, when you look at the Mali and Niger, the country, you're also experiencing an absolute increase and potential for green hydrogen as well as influx. But then things like water, wind availability also play a massive role as well. So the green hydrogen prospects in Africa are actually enormous. I'm going to be sharing a few case studies in a bit as well. But prior to that, I just always try to remember the particular needs that Africa does have. So powering industries through green hydrogen, even if Africa is going to thrive and wanting to declare particular investments into the fossil fuel industries, green hydrogen provides a cleaner way of refining particular fossil fuel industries. So there are studies that have been carried out about how green hydrogen can be used actually in refineries to actually make processes for fossil-based fuels a bit cleaner. Hydrogen does provide a good feedstock for chemical industries, as well as a possible decarbonization alternative for large industries heat users. And then one that I find particularly very interesting for the prospects in Africa for green hydrogen is the availability of platinum group metals. So Africa is currently enriched with the largest amount of platinum and palladium metals, which are a key component to the production of electrolyzers, which are used in the process for electrolyzing in green hydrogen to production. And then lastly, the infrastructure opportunity is vast. Once Africa is able to tap into the potential for green hydrogen and receive a lot of investment, either from the private or government angles, we're going to see an absolute turnover in the amount of the jobs available, companies offsetting, as well as emerging technologies. So my first case study is on South Africa. As mentioned just now, South Africa has actually been on the forefront of green hydrogen, following Morocco nonetheless, green hydrogen in Africa. The Hydrogen South Africa Council is focusing on R&D across the continent, not only
We lost you. We can't hear you anymore. Maybe you're muted.
Mrs. Ogoza, we cannot hear you. I hope that you can hear me. If Mrs. Ogoza is disconnected or have any issue, we will try to continue our presentations and come back to Mrs. Ogoza when she will be connected. If you allow me, and if my friend Dr. Samir Rashidi is ready, we can give him the floor. So he is ready, like always. Welcome, Samir. Let me just give a little view of my friend Samir. Samir is an R&D director within IRSEC'21, in charge of solar thermal systems and power to X. With his team, they are developing research projects and demonstration activities focusing on power to X green chemistry, energy storage, concentrated solar CSP, and hybridization of solar and bioenergy. Prior to his current position, Samir served as an R&D program manager at Mazen. His role consisted in catalyzing national R&D efforts in the solar energy field, building international R&D project partnership and collaborations in the area of solar applications, as well as helping in defining strategic R&D orientation to help unleash a Moroccan industrial potential in the solar sector in the future. Previously, he held the position as an R&D engineer in a startup company named IRSEC' Innovation in Sofia, Antipolis, France. Samir achieved in 2011 a PhD in the field of hydrogen PEM fuel cells, carried out in collaboration between the CEA of Grenoble and CNRS Institute of P' in Poitiers, both in France. Samir holds a double degree Master of Science and Engineering in Chemical, Environmental, and Energy Engineering obtained from Saint-Etienne. In addition, Samir is
Excuse me, Miss Ogoza is now is back.
Okay,
I'm so sorry for that. I'm almost done, so maybe I'll just round off.
So the floor is yours. We'll come back to Samir after.
Okay. So I probably just go straight into my next case study. So the next case study focusing on Africa is the case study of Namibia. So Namibia is currently taking up a huge sponge as being one of the countries focused on achieving large-scale cost renewable energy development. They have actually set up a particular scale which allows for a request for funding that have come up through the government. So that's been super exciting in the continent. Namibia is also classed as being a world-class solar and wind resources, giving it a long-term competition advantage in producing green ammonia. So this is just a graph detailing like where, and this is the particular Southern Corridor Development Initiative that has been set through by the government at the moment. And what this initiative has actually done to set up is identify key regions and states in Namibia. And from this particular image, we can obviously see the way that the landscape has been expected to go. There's going to be potential to fund foreign direct investments to up to 6 billion. And this is infrastructure investments as well as producing 2 million tons of ammonia. And in the excess funding that's actually required goes into electrifying the national grid as well. So Namibia is really up for having collaborations. And I believe last month there was a cooperation agreement that was signed between Namibia and the government, the German government. Namibia has also demonstrated that it's poised to become the renewable energy hub in Africa. There's already outlook into looking at what the distribution of solar potential is for the country as a whole, and then particular interest taken into what the solar and wind radiation would be. So from this graph from ARENA, they have identified the annual generation per PV capacity. And Namibia, working through their population, and the last mass is actually expected to increase up to 2,000 kilowatt power per year. And the wind potential is also expected to increase alongside as well. So one major thing that I spend a lot of time trying to deflate is what green hydrogen access would look like for the continent through government intervention as well as private sector intervention. Governments have certain initiatives at the moment, so seen in Morocco, for instance, South Africa and Namibia, towards the transition through enforcing mechanism, either through roadmaps or frameworks, to overcome the initial economic skill and truly become competitive. And for the private sector, there's been willingness to invest into green hydrogen as well, through the increase in renewable energy solutions, which also feed into the production of green hydrogen, either for local domestic use or exports. So the outlook and challenges that are very key to explore further are, the first, which are the factors, which include water supply and the cost of the electricity, as well as transport and storage. The markets also play a very huge role into how profitable and competitive green hydrogen would be. And these include the off-takers, either the demand and supply, abatement costs, which generally involves identifying sectors that will play key roles in the hydrogen economy, as well as the electricity cost. On the policy side, which most times plays into the government and the private sector, it's important that the outlook and challenges presented include things like the quality of the hydrogen gas that would be used for different facility, either for feedstock or for refining purposes, the standard of hydrogen gas that would actually be transported and stored in different intensities, as well as certifications for green hydrogen production. There's also the need for technical knowledge and know-hows, and this also involves raising awareness for the new emerging jobs in emerging markets for green hydrogen. And so this involves things like, if, for example, the fuel cell systems are being introduced through green hydrogen, they would need to be upscaling into introducing either new trainings or capacity development for the particular economy to meet that demand. So the next steps for a host of application of hydrogen roadmaps or frameworks. This is really vital because although this doesn't automatically give a green flag to go forward with green hydrogen for their national capacity, it's important that countries learning from Morocco, Namibia, also Africa, learn or understand the impact of having a hydrogen roadmap and framework for the future. There's also the need for funding for green hydrogen infrastructure in African countries. And again, like mentioned, this can either come from private or government avenues as well. Increasing energy access to renewable solution in large scale is essentially vital for the prospects and the potential for green hydrogen in Africa. This means that the 70% of Africans still living without access to reliable electricity do have a chance to actually upscale in that regard if there's more investment into energy access for renewables, but also feeding into the green hydrogen economy. Like I mentioned before, so raising awareness through research and development, as well as knowledge sharing across African nations is really important, because while hydrogen might not be the new oil, it is important that African nations do learn from previous lessons and mistakes towards going into the hydrogen economy. So green hydrogen is on a solid path to becoming the most economic choice in the future, coupled with low-cost renewable power. While the world tries to reach a net zero capacity through decarbonization by 2050, Africa contributes to low carbon flows while increasing its energy access. So I believe this is a win-win for Africa. And again, all my thoughts have, been mine and not mine of my employees. Thank you so much.
Thank you very much, Mrs.
Thank you.
Ogosha. It was a pleasure to hear you, and sorry for this interruption, but well, anyway, that's technologies. Just to add that you are absolutely right, because Africa from ourselves also is the future of the majority of increase of energy demand. So to catch such increase from now will be very interesting. I think that there are some questions, but I will let them at the end to allow me. And
thank you.
As if you have something to add, no problem. Okay, so if you have nothing to add, I will just, if you allow me, complete the presentation of my friend Samir, because I will not repeat it from the beginning. Anyway, Samir is very well known, so no problem. I will just add that Samir is lecturing at University Mohammed VI Polytechnic, UM6 Polytechnic, and Central Casablanca Engineering School. He has been also recently elected as the General Secretary of Moroccan Cluster of Green Hydrogen, and he is leading the Green Hydrogen task for the Green Economy Commission within CGEM in Morocco. Mr. Rashidi will talk us about innovation and R&D, a key to a competitive green hydrogen economy. Samir, floor is yours.
Thank you very much, Saad Rahim. Thank you very much for the kind words and the kind invitation. Thanks again for the organizers for inviting me for this small talk about the developments of innovation in order to reduce the cost of green hydrogen. I will just try to upload the presentation that I have just here. And please tell me if everything is working fine from your end. Okay, perfect. So I will move on to my talk. So the idea is really to focus a little bit on the road of R&D in terms of reducing the cost for the deployment of large-scale hydrogen economy. And as Ogosa has also, apologized, it's not really a very technical or scientific talk. Rather more, let's say, high level and holistic. And sorry about that. Hopefully that will also be useful to the audience. So just 2 words on my organization I am working in. So this is IRSEC'21. This is a Center for Research in Solar Energy and New Energies. It's a center that was created by 2011, and for now, yeah, we have celebrated 10 years last February, and we are under the leadership of the Ministry of Energy, and our role was also to keep up with the national energy strategy of Morocco, and also to enhance and somehow to catalyze research and innovation in this field. We have two main roles. We are a funding agency, but I mean, having calls for proposals, but also we are deploying R&D and a national network or regional network of R&D research facilities that I will be speaking about in the few minutes. So these are the research centers that are deployed or in the progress of being deployed. Introduction has been done. I won't go back. So this is the outline of my presentation. Three main axes is somehow the R&D and innovation pathways for green hydrogen value chain. I will give focus then on three examples. I won't be long of promising innovations that I think it's also interesting to investigate, or at least to be interested in. And at the end, I will present some, modestly, some initiatives that we have taken within IRSN with the support of key stakeholders and partners here in Morocco in terms of R&D and innovation in what we call Power to X or green hydrogen economy. Also, some reference for readings. As I said, always, I'm not inventing things. I'm just reporting some readings for the audience. So I have taken some important insights from the latest mission innovation letter that was, disclosed and disseminated during the COP26, and very interesting reports also that was, mentioned by Cédric's presentation yesterday of the IEA net zero by 2050, and the other reports that you can see here from IRENA and the World Energy Council. So about the hydrogen value chain. First of all, this is a slide that I have taken directly from this report of the IEA, which is really for us as a community of researchers very fulfilling, but also very scary, because what we see on this slide is that the net zero emission strategy or targets or objectives are relying on technologies that are not in the market yet, or even worse, that are under development or not yet available, especially for the 2050 target of net zero emissions. So this is really huge, which really mean that innovation will be at the heart of the energy transition, and will be at the heart of the fight against climate change. And this is something that is fulfilling for researchers like us, but also making lots of responsibility on which technologies and pathways we need to develop, etc., in order to accelerate the energy transition and also to accelerate the fight against climate change. So I won't go very deeply. This is a slide that I have tried to develop somehow in order to situate the value chain of green hydrogen. We are speaking about green hydrogen, but we are speaking about a lot and mainly different types of industries that are involved inside. So we can go from the renewables, electricity production, desalination, which is really key, hydrogen production, so electrolysis mainly, probably in the future, photocatalytic hydrogen, hopefully, and then a very important part of the value chain, which is the infrastructure and the logistics. So this is really very important. Afterwards, you have let's say the mid or the conversion, let's say middle stream part of it. So this is heavy chemistry, chemical industry, etc. And then we have the applications, and the applications are really varied and multiple. So it can touch many aspects of our economy. And you have, I think, seen much more information from the esteemed speakers previously for this session, or even for the whole conference for the whole IRSEC conference. So I won't be very long on this slide. But let's say, in terms of, if I have to summarize it a little bit, we have, if we'd like to innovate in this value chain, we need also to innovate in each part of this value chain. So it's not about hydrogen production, but we need also to innovate for storage, to innovate for transporting this hydrogen, for converting it, because it's not easy conversion, because we will depend on variable electricity. So we will need to operate 24/7 chemical processes that are run continuously during the day with a variable electricity. So these are very huge challenges, especially for operating and maintaining those kind of plants, and of course for the diverse panel of the applications of green hydrogen. Some examples. So for the production, we need to focus about electrolysis, still some challenges, water splitting, which is really beginning. And I really thank Ogosa. I have many questions for her. No, Ogosa, but sorry, Sonia, for her a very comprehensive talk on water splitting. And she had also included some things we discussed yesterday. It's really impressive. Thank you very much for that. For the storage, we have also some challenges in terms of having high compressed, high pressures for the hydrogen. Metallic hydrates could be also very nice, let's say, candidates for transporting. We have a variety: liquid hydrogen, pipeline, LOHC. Conversion, we need also to adapt the Haber-Bosch, the methanol, methanol production processes. Power to liquid, we need also probably to innovate in the part of CO2 capture, because this is also key in terms of power to liquid. And for the applications, there are of course fuel cells that need also to be always enhanced in terms of efficiency, and also the use of new molecules such as ammonia or even methanol as a fuel in ships, for example, or heavy duty vehicles. So we can also separate those or aggregate those into, let's say, main streams: the production of hydrogen, the storage and distribution, which we could also call like handling of hydrogen, and then the large spectrum of the utilization of hydrogen. And if we look also, this is very interesting that was pointed out also by the mission innovation paper I was speaking about in the beginning, is that we have really witnessed a very big increase in terms of publications, but also in terms of numbers of patents relatively to the green hydrogen economy. Or the hydrogen economy in general, because sometimes we have the same area. The green is just for the renewable part of it, and sometimes it depends. We see that mainly probably the biggest interest by year, you have 2010, 2015, and 2020. Each year, production in terms of literature, publications, but also patents is quite higher, let's say, in terms of scientific and technical productivity, in terms of IP. Then it's followed by the utilization, and then storage and distribution. So industrials, researchers are also innovating also through the whole value chain of power to X or green hydrogen economy. So this is also important to point out. It's not about electrolysis, hydrogen production, but it's about a complete value chain. So as I told you, really some examples, and it's not like very, let's say, detailed or objectively chosen. That was really some, as we say in French, coup de cœur from my side, but really there is no judgment about that from the objective point of view or scientific point of view. Please be indulgent about that. So for the production, what I really see as a promising technology, especially for a country like Morocco or any other sun-belt country, is solid oxide, high temperature electrolysis, because this is a technology. I won't go into the details. Certainly, you have already had during this conference some even more esteemed or high-level keynotes that were explaining very well, better than me, this technology. But the idea is really to focus on this technology because it's high temperature electrolysis. We have higher efficiencies So the temperature is around 700 to up to 800, 850 degrees Celsius. We have also lower capex. It's a less complex system because we have one phase. We have a vapor, not water plus gas or liquid and or many species. For the alkaline, for example, we have also a liquid electrolyte. So this is even complex. So less O&M for the system and the ability to reverse it. For the same capex, you can use it as a fuel cell, but and also as electrolyzer. And also it's a drawbacks, but also it's an opportunity for countries like us. It's less mature in terms of scale, and as you see, of course, there are some companies, especially in Europe and the US as well, that are also betting on this technology and trying to make it very quickly to be upscaled. Especially, I can mention the Genvia startup that has been formed recently. It's a JV between Schlumberger, CA, and also another company I don't remember. And this is somehow very promising. However, we are still, generally in a lower TRS. So for a country like Morocco or a developing country, let's say, we can, if we do research in this, and we can be very quickly, not at the same level to as advanced countries or laboratories, but we could get into the train or onto the train very quickly. And the most important thing for me is that it could also be coupled with also probably a not very well understood technology, and we can discuss about this later on. But I think we could really do the hybridization between CSP, not the electricity part of it. The production we can discuss. It could be good, or not good, but for the electrolyzer, in order to gain even more in terms of efficiencies, but also in terms of availability. So I think there are something to investigate, and some demonstration units to have, or pilot scale unit to have, in order to further develop this. But I'm quite thrilled about this idea. And as you see, SOIC is not really well developed if you compare, for example, PEM and alkaline, in terms of you have here the cumulative, let's say, projects or the projects that were developed by phase or by period, and you see that SOIC has just started in the last era between 2015 and 2019. This is probably things have changed recently, but it's still a very young technology that is trying to be on the market, especially at a low scale. As per the storage, I have chosen to speak. It's really complicated when you see the details. This is a slide that I took also from the World Energy Council report, where you see somehow a little bit detailed the pathways that we need to consider when we will speak about storing or transporting hydrogen. It's really complicated. If you take, you have, for example, the liquefaction, liquid hydrogen pathway. You have the compressed, you have the LOHC, you have ammonia production, but you have also PTL synthesis, methanol, and other fuels. So it's a complicated, and for each pathway you have also some challenges. And this is what was also, especially for the midstream, the handling, the storage, etc. You have here an excellent, let's say, slide that is also speaking about what is the status of innovation, of the maturity of each pathway, liquid hydrogen, LOHC, etc. And we see that still now in 2020, 2021, we still need to upscale and to prove some path or some elements of the supply chain, of the value chain of hydrogen, and this is not very easy. So it's lots of efforts in order to get to the very low cost of hydrogen. And one of the promising technologies, I think, besides ammonia, of course, that is well known now and is taken a lot in reports and also studies, and also some demonstration projects that are ongoing. LOHC is also very, very promising pathway in terms of transporting and handling. The hydrogen, it's mainly having low capex. We can, the principle is quite simple. It's like you have a liquid mattress that you fill with hydrogen, and you dehydrate, and from which you could take out, or you could take away your hydrogen through hydrogenation and dehydrogenation process of the dibenzyl toluene mainly, but there are other candidates, but this is the main, let's say, candidate for this, or vector for green hydrogen for this technology, LOHC. I have taken the slide from the promotional, let's say, a brochure of a startup, German startup between Germany, I think, and Switzerland, called Hydrogenius, with also some Japanese and other shareholders in the capital of the company. So it's quite a transparent liquid, very well, I mean, very widely used in the petrochemical apparently I mean sector, that can and so the supply chain is already there, and we could just plug into this supply chain to transport hydrogen. And with ammonia, these are the two, I mean, very competitive or technical economic optimals for transporting hydrogen. Now for the utilization, I have found also a very innovative and really promising technology called, or let's say promoted by a startup in Netherlands called iron fuel. And this is the idea is really quite simple, and I think also very old. But the idea is really to try to take iron powder as an entrant, and then to burn it, to oxidate it. So we'll have an oxide, an iron oxide, and then we will regenerate iron through the reduction, but not from with coal, but only with hydrogen, because hydrogen can reduce the oxide, the iron oxide to a metallic iron, and then we can repeat the process. So for example, we can imagine that oxides of iron come out from us to us, for example, in Morocco, in Africa, any African country, from Europe, and then we have some plants producing hydrogen. Then we make the reduction, and then the same ships or different ships could take back the powder that is reduced, the pure iron, let's say metallic iron, and go back to Europe to produce energy. So this is kind of a storing energy through hydrogen, thanks to hydrogen. So nice application, still low TRL, but very promising, I think. As per Morocco, and I don't want to be really long, sorry about the time, we have started somehow in the 2018 with some studies, different studies done by with some stakeholders that I mean that have resulted in a third, let's say, study about the roadmap, about how Morocco thinks about involving or developing hydrogen economy within its territory. We had also the creation of a national commission on green hydrogen, and also many MOUs that were signed between Morocco and key countries of hydrogen. We had the roadmap has been published on the website of the ministry last week, and I think by this Morocco officially it has been also published in a shorter version in August. And Morocco is this way the first, to my knowledge, the first country in Africa and also the region, the MEA countries, that has published officially his roadmap for 2050 in terms of green hydrogen adoption. We have lots of activities and recommendations, and we had already started in developing this kind of holistic I mean landscape, with public institution bodies, with industry, with capacity building, R&D innovation. Commission Nationale of Green Hydrogen is the institutional part of it. Green Hydrogen Cluster was also created to gather the industry, but also the research and academia. And Green H2A, I will be speaking about it just in seconds, is a kind of R&D platform that would like to emphasize on R&D innovation, but also on capacity building and training for local qualified human capital for these technologies. So this is somehow a layout, high-level layout of the platform with some indicative ideas. So mainly consisting of outdoor platform in order to scale, try to scale a little bit the technologies, of course, electrolysis, but also we are looking at the whole value chain of it, and we hope that we could leverage, funding through also H2020 projects and also collaboration with the friends. With allies and friends of Morocco in terms of research and international cooperation. So the idea is really to try to bridge the gap, the famous Death Valley gap between the industry or the market and knowledge creation in the universities. And this is how it should look like. This is a previous platform we have already finished in 2017. It's already working. Next year it will be 5 years of deployment of green energy park, focusing mainly on solar, photovoltaic, but also thermal solar, and also applications with buildings. Building for indoor labs, but also mainly outdoor pilot units and upscales. This is the second platform that was developed between IRSN and its partners, University of Mohammed VI Polytechnic and OCP as well. And this is where we hope this, it's no more hope, alhamdulillah, it's already done. Yesterday we had some nice meetings, and we will during the next PTX summit next week we will publish something very interesting. And this is an industrial site of OCP, one of the biggest sites of producing fertilizers in the world, and the Green H2A will be hosted inside this industrial site, which is really good for research to be done with the industrial, for the industry, but with the industry as well. We have also nice infrastructure here with the exporting harbor, and also some steel and coal power plant in order to have CO2. Sorry, Si Abdurrahim, I will finish with these 2 slides. And last but not least, some pilot project. This is the first project that will be hosted in Green H2A, and also we have nice news to announce next week about the development of this project and the deployment of a real scale pilot unit to produce photons per day of green ammonia with 2 megawatt PEM and 2 megawatt alkaline. And this is a project also that will be the second project on PTL, focusing mainly on CO2 capture, direct air capture technology, but also the idea is, as for the first project, to upscale and to see the possibilities for upscaling for other partners in the country. Sorry about being long, Si Abdurrahim, and I hope that was useful, even if it was not that technical. Thank you very much.
Thank you very much, Samir. Thank you also for Mrs. Kalnan and Mrs. Ogusa. I think we had very interesting presentations this noon, let's say, in Morocco at least. We talked about the science and technologies, how it is evolving and how it can help to reduce costs. With Mrs. Kalnan, we had also with Mrs. Ogosa a presentation about the role of hydrogen in Africa, and which can be very important, very interesting in the future. And finally, the innovations that can be, let's say, uploaded, that was presented by Samir. I think there are some questions. Let's say I would like to give first the floor to questions, and then after we'll continue discussion. The floor is open for any question we can have on this way. And if you allow me, I will read the 3 questions we received and Q&R of the system. The first is from Mrs. Tassoult Huda. Do you think that green hydrogen will be the leader competitive in future in Africa? I think it is a question for Mrs. Ogosa.
Thank you so much for the question. So do I think green hydrogen will be competitive for Africa in the future? That is a question that nobody has the answer to. I can imagine when solar came, about 15, 20, almost 30 years ago, people didn't think the price of solar was going to obviously get to this point at the moment. So the competitiveness of green hydrogen will really depend on the demand for decarbonization globally. And again, as much as COP26 and then the international Paris Agreement have responded to the decarbonization processes, it's only a matter of time. So I cannot 100% say it is going to be competitive or not. But with the way things are looking now and looking at the economies of scale, we do expect the green hydrogen to become competitive as more countries get on the bandwagon for more decarbonized processes in the energy sector. I hope that answered your question.
Thank you very much. I will have a question for Mrs. Kalnan. In your presentation, I let's say, noted that it was interesting to see, how can I tell it, a production of decentralized hydrogen with little capacities for households or for little industry, from some kilowatts to some megawatts. Could you elaborate more on taking into account the results of the analysis that has been done during the last years?
Yes, thank you. Actually, at the moment, these are all demonstrations, but before we can really go to the next level of, let's say, technology readiness, we really need to test them in the, at the moment we're testing them in the technical environment, which is outdoors, but the real environment to check the commercial readiness is really in the final applications, let's say in those households or in those small hotels or small industrial areas. But the thing is that right now this is not possible because we don't have the regulations. So first of all, the safety, we need guidance on what the safety should be in order to really show this. And of course, eventually the costs still have to come down. A lot of these things are not yet available. Apart from the solar cells, a lot of the components for the electrolysis part are not available on a large scale and on costs that are affordable for these small users. And so this is really research to show to the policymakers that, okay, technically it's possible, but we need also the regulations, things like to help with safety and permits and so on. Otherwise, they cannot be implemented because we know that hydrogen does have some danger associated with it, like any other fuel. And this cannot just be put in the public. So it depends on the regulatory frameworks.
Thank you very much, Mrs. Sonia. I think that Mr. Dieter has a question. The floor is yours, Mr. Dieter.
Thank you very much. I have a lot of questions, of course, but I have to restrict myself. Maybe I start with a general remark. If we talk about Africa, it's about empowering Africa and making Africa more independent. This was actually an aspect which I missed a little bit in the presentation. So it has to be, Africa has to become independent of Europe but in the future, even more so from China. China is taking over the role of Europe in Africa very much. So independence will be very important. And this means to produce in Africa final products. So I'm very happy with Samir's approach of thinking about directly going to products like ammonia or even better steel. What is missing in his presentation, and we discussed this already before, is concrete. Actually, concrete is a very important product needed a lot in Africa, of course, and one of the key issues for reducing CO2 emissions, of course. So making green concrete is another very important goal to follow. My question concerned mainly the talk about the direct electrolysis. We had already a talk in which systems for water pumping were compared with and without electronics. Basically, the direct electrolysis aimed at in this very large project you managed, Dr. Kalnan, was to avoid the electronics. Now, of course, do you have an idea how much the price will really be reduced if you do this direct coupling, especially since even for a small system you are aiming at, and this was the final point of your talk, you want a fueling station in a house or something. Of course, the hydrogen you produce in your system is not ready for putting it into a car. It has to be dried, it has to be purified from oxygen and so on. If you would put the hydrogen coming from your system direct into a car, your car would stop working very soon, of course. So the whole system is more complicated than you demonstrated, actually, which of course also will finally reduce the overall efficiency of the system. And I really have doubts that it helps avoiding the electronics.
If I may answer, actually follow-up work on the project. When I was asked to present, I was asked to present what happened in the project, and what I showed is what was shown in the project. What I didn't show for issues of also there's some proprietary information and also time restrictions is the economic analysis. And there we considered everything from making the solar cells, mining the solar cells, up to a pressure output of 25 bar. So that was including the drying and the compression to compensate for the atmospheric output. And there we found that if you're located in a hot region, definitely the costs come down very close to these 5 euros per kilogram. But again, the calculation depends on being able to reach megawatt scale, and we cannot reach this yet. And so the comparisons we make with this $2 per kilogram of hydrogen, this is on a system which is several megawatts big. We're not yet there. And so to achieve these values, you need to get bigger. And so the aim of this project was really to show the first steps of moving away from the lab. Previous to this, all these things were shown mainly on small scale, and then we are really moving towards at least something which is similar to the size of a PV module, and then which can be replicated, like PV modules are replicated on the roof, to achieve some reasonable size. But it's not so straightforward to compare the costs. But I can tell you that when we calculate the costs, we consider drying and compression to 25 bar, because 25 bar is around the pressure at which it comes out of the steam methanol reforming. And that is the standard for costs. That's the standard against which the cost of hydrogen production is used.
Thank you very much, Sonia. I have a question from the floor from Mr. Samir. Then after I will let the floor for Mr. Cedric, who is raising hand. For Samir first, I will read the question. At which scale we can say that the green hydrogen strategy is a competitive technology regarding the cost, the efficiency, the scientific knowledge? Great question.
Sorry, I was trying.
I think you have it on PNR.
Yeah. I have seen it. Which scale? Yeah, I know it would be really pretentious to have an answer for this question. What we can say or at least what I can say from what I have read or seen from experts is that this decade is kind of market activation for green hydrogen. This is my opinion, and this is also what I have read. We can easily the megawatt scale, I think, is already, we can consider already behind us, especially if we speak about the brick of electrolysis, of hydrogen production. And we need to start, I mean, projects of the scale from 10 to 100 megawatts should start now. Because this is the right timing, and we need also to work in collaboration among the scales in order to have the data, and also to have inputs for upscaling. So I think 10 to 20 megawatt is doable in the next few years, very soon, even 100 megawatts, because we will be probably multiplying blocks of 10 or 20 megawatts. So this is the idea. The costs are also progressing, especially from the PEM point of view. We are, I think, some industries now are suggesting 75% for PEM electrolyzers for now at a commercial size or level, which is quite good. Knowledge. This is why we are trying to strive and to be somehow very pushy to start in knowledge now. Knowledge is already there, because this is not a subject that was created today or last year or 3 years ago. It's a subject that is about chemistry, about optics, about chemical industry, electrochemistry. These are subjects that are here for literally probably a century or even more. So this is not new. What is new now is really to adopt it and to have it in a way or in a perspective of industrialization and production. So this is why we are trying to disseminate knowledge here, at least in Morocco, from our side, and also to to construct those kinds of curricula or platform that could host also the scientists, but also technicians, engineers that will work in this plant. So I don't know if I have answered the question, but at least this is my opinion for the moment about that.
Thank you very much, Samir. Mr. Cedric Philibert. You are mute, Cedric.
Yes. Thank you, Abderrahim. Yeah, it was an interesting conversation, but I'm afraid I heard too many illusory claims, and I want to warn you against this. To me, it's clear and clear every day that hydrogen lobbyists want to have hydrogen everywhere. They have a hammer and they're looking for nails. But for climate and energy analysts, we're having a few nails for which we are lacking a hammer, and these nails are reduction of iron ores, current uses of hydrogen, that is ammonia making, methanol making, and refining, aviation fuels, long-distance maritime fuels. We have no solution for that except through hydrogen. And in the long term, long-duration storage in 100% renewable electric systems. Maybe in the shorter term in isolated grids, but basically that's in the long term for the main grids. And many other proposed applications won't work. And this brings us back to the discussion on competitiveness. I think it doesn't make sense to say, well, yeah, hydrogen, green hydrogen will be competitive or not in general. It will be competitive over gray hydrogen if we give a value to carbon emissions, for sure, or even without that in some time as the price of renewables continues to collapse. But that doesn't mean green hydrogen will be competitive against green electricity, where green electricity applications will be 80% efficient, while the same hydrogen hydrogen application chain will have an efficiency of 20%. Then it will never be cost effective. And this is a case of low temperature heat in buildings. This is a case of fuel cell cars, probably the case of most ground transportation engines, and maybe also the case of high temperature heat in many places. We'll see. There might be cases where hydrogen might be needed there, but I don't expect there will be that many. In particular, because the hydrogen flame it has very low radiativity, so heat transfers won't be easy with that. Well, electric radiators, and they know that in the glass industry and others, they are very effective. They are radiative, so heat transfers are very effective. So we'll see. There might be cases. Maybe in the rotary kilns of cement, some hydrogen will help. I'm not even sure of that, but let's see. I mean, we are still looking for solutions for, I think, since 2015, when we understood that we have to go to net zero and not only to cut the global emissions by half. We are investing in new fields that were left aside previously because we thought that, yes, we could cut emissions by half with decarbonization of the power sector, energy efficiency, and a number of other measures. But now that we know we want to cut the emissions by factor 6, basically to be net zero globally, we have to make new efforts in other fields which cannot be that easily electrified. So that's how hydrogen came about. Now I would just first give you one reference. You will have it in the discussion. It's a paper I recently published, and which is called "After the Hydrogen Bubble Bursts." So we're plenty in the bubble. The bubble will burst, like all bubbles. But after that, there will remain some useful uses of hydrogen. So, and I'm trying to find what they are. You would have the same in the thing I showed yesterday, which I will very briefly show again, which is the hydrogen ladder of Michael Liebreich. There are a number of energy analysts now that have been able to, and they tend to agree globally on what is, where green hydrogen or blue hydrogen, by the way, that's another discussion we could have, will be useful, and where it won't be competitive and it won't be useful because we can do so much more with green electricity directly. And finally, I would like to ask a question to Madame Erharon, which is in her speech, she also had hydrogen to help to access to energy in Africa. And I just have difficulties understanding how hydrogen can help giving access to energy in Africa. But please, thank you very much.
Thank you. Is it okay if I take a question? Yeah. Thank you, Cedric. So the idea of green hydrogen, as all the experts and scientists actually understand, is it is generated from renewable capacity. So at the moment, and I completely agree with you that we can use green hydrogen we can use hydrogen for everything. We need to be very selective about the sectors and solutions that we want to use hydrogen for. The prospects of green hydrogen in African nations does mean there'll be more investments into renewable energy solutions. I understand from the technical point of things that there is a volume of green hydrogen that has to be produced to actually provide or then transcend to generating a similar amount of green hydrogen. For that to happen, there has to be a complementary increase in renewable energy access. Most of these technologies are going to be done in the rural areas of Africa, so not your city centers, not your urban areas, but areas that have high wind intensity or really, really high space or grounds for renewable systems. A lot of these areas are close to areas that are actually known for having very low access to electricity. So that's just the connection that we find rather interesting. If Africa is going to become more competitive on this green hydrogen platform or the economy, it does provide an opportunity for green energy solutions to be invested in and to provide more solutions for the energy access in African countries. I don't know if that helps, Cedric.
Yeah, it does. I think that, if I may, Abderrahim, just go on a minute on that. I think that's quite interesting. So it's not because people will have access to energy through hydrogen itself. It's because at the country level, and I think you gave the example of Namibia, which I happen to know a little bit because I was part of the studies that led to this decision. If Namibia develops green electricity to make green hydrogen, to make green ammonia, to send it to Europe, that's basically the plan, right? That will be so big compared to the Namibian grid that it will help a lot decarbonize the Namibian grid. I'm not sure it will help access itself, but it will also, because if the economic of the country improve, it will be easier to finance access to people. And maybe that's something that to prevent the curse of natural resources, I would say, to prevent the fact that an export, a very centralized export income is not well distributed throughout the country, which we have seen in a number of countries. I will name no one here. It could be part of the game of the contract from the beginning, that the investors together, while they invest in the main solar and wind capacities and electrolyzers and Haber-Bosch loops to make the exports and port facilities to make the exports, etc. At the same time, they do have to develop access for the people in the country that have no access, also based on renewables, because you have solar everywhere in the country, and lithium battery now are cheap enough, and you can plug that with electric pressure cookers. And that I think now the good solution, we had a workshop in 2019 in Morocco about that. The good solution now for access, access is problem of electricity, but also the problem of clean cooking. Of course, you know that better than me, I suppose. But now PV plus a small battery plus an electric pressure cooker can do a lot to reduce the amount of charcoal consumed and to reduce the fumes and improve the health of the people, etc. So all this could be part of a general investment in a country and prevent all type of risk, including the risks that was mentioned yesterday by our friend from Quebec, Moroccan living in Quebec, that that would be colonialism and steal the energy from the people of the country. We can exactly make it the opposite. That I understand that's what you had in mind, and I'm glad I gave you the opportunity to make this clear, because it wasn't exactly that clear. Thank you very much.
So maybe I'll just quickly add to that. I think that's why it's really important on the hydrogen roadmaps and frameworks to establish the process for increased energy electricity supply while getting into the green hydrogen market. So I'm definitely hoping that more African nations, while developing their hydrogen frameworks, understand that that is or that should be at the core center of their frameworks and the core center of the new market that we're getting into. That the end goal is to make African nations at the cornerstone of the decarbonization, but then also increase the economic and electricity capacity for African nations too. So it's important that those two are not treated as enemies, more like cousins or brother and sisters, if you like.
Friends,
but thank you so much.
Thank you very, very much. I would like to have more detailed discussion, but as you know, we have to manage time. You have just, I think, 2 minutes. I will ask the organizers to correct me if we have more time, but if it is just 2 minutes, I would like to.
We can add 5 minutes, no problem.
Okay, so I will give the floor for, let's say, 2 other minutes. If someone has something to add, I think Mr. Philibert, Cedric Philibert has.
No, I think I'm happy now that. But I would beg Madame Ehan not to let her readers or audience believe that she thinks people will get hydrogen at home to make all their cooking and all their heating and all their electricity needs, because that's probably not the best way of doing that. And avoid this confusion as much as you can. But no, I'm nothing else to add to it.
Samir?
Just also I wanted to add on what Cedric says. The idea is really, as we are seeing, it's a value chain. It's not one application on one source. So this is really a value chain, and we need to take into consideration the specificity or the specific requirement for each country. And this is, I think, where Cedric wanted to say it's not the solution for everything. It will depend on each country's specificity, potential, but also ecosystem. Because this is the idea. It may what is sure is that we need a very competitive electricity. This is something that everyone is okay about. But then what we do with the hydrogen, how we convert it, that would be really dependent on the partners that we have, but also, first of all, the specificity of each country. This is what I wanted to say. Thank you very much, Sadra.
Thank you very much. I would just like to add some points, and I am really happy to have participated to this discussion, and also Mr. Philibert for the points. I know he is passionate, and they know him passionate for other technologies, and I am happy to see that he is as passionate for these technologies that he is passionate now for hydrogen. I would like to say myself, when I make the first study on hydrogen, it was by the beginning of the 80s. And the first thing I had was the Zeppelin. I don't know if everybody knows the Zeppelin. And yeah, so the hydrogen was dangerous. That was the idea by the 80s. Let's say 5 years ago, I will not say 10 years ago, but 5 years ago, the cost of renewable energy was at least 10 cents of euros. And at 10 cents of euros, green hydrogen can never be competitive, even with CO2. So 5 years ago, we could not develop any hydrogen. The last 2 years or 3 years, there is a lot of strategies all around the world, and it is very interesting because the cost of renewables has been in regions like Morocco and Namibia, for example, just for example, because there is a lot of other countries when you have it between 2 and 3 cents, and it can continue to be reduced. But anyway, we are in the beginning of a new challenge. We cannot say, I think now, and the researches that has been presented here demonstrated it, that we know how we will produce hydrogen during the next 10 years, and how we will store it, and how we will transport it, and how we will use it. We have not the answers to all questions. It doesn't mean that we have to stop. No, we now can produce green hydrogen that can be competitive to blue hydrogen without any problem in a lot of regions in the world. And it is the first point to take this challenge and to go ahead. Now the technologies are evolving, and we could see it in the 3 presentations, and the strategies also are evolving, and we can see it in these presentations. And Africa, I believe in it, can be an area where hydrogen can be developed in large scale, because the needs of energy in Africa are so high that we need to develop new technologies for it. I am passionate also, anyway, not the same thing that Mr. Philibert, but I will never give any word for fossil fuels. I believe in renewables. I don't believe in fossil fuels. So green hydrogen and fossil fuels, I hope, will be the future for Africa and for the world. I think that we have 1 minute. I will let the floor for the panelists that has made presentations to give a final word. Let's say Ms. Dr. Sonia Kalnan, if you want to.
Yes.
Your last word.
Thank you very much. I just want to point out that actually this is just one of the projects that we're dealing in. And actually in the last, let's say, 5 years, the focus was really on green hydrogen. But now, if you look at the number of projects that are coming out for research and for demonstration, even Mr. Rashidi and Ms. Hahon showed, the projects are moving away from only hydrogen, but also looking at the next products that are coming from this green hydrogen. But nevertheless, one has to keep in mind that hydrogen is the main molecule, and you still need a lot of research to get the process more efficient and more cost effective. Thanks. So just because I showed something about hydrogen doesn't mean I'm ruling out other things. I'm also involved in some other projects that are working with ammonia and CO2 reduction.
Thank you very much, Mrs. Ogosa.
Yes, Dr. Sonia, yeah, you've obviously raised a really valid point. We're not, well, I'm not particularly just focused on hydrogen, but it is important that we understand that hydrogen isn't going to be technology for now. We're preparing for the future. You know, these are ground conversations that we have to have. These are the researches that Dr. Sonia is achieving that we have to have now while we plan for the future. It's just 2021. We have 9 more years to really perfect the science of things if you really get down to it. So thank you so much for being on the platform and maybe learning something from Mr. Cedric about my explanations for energy access. Absolutely appreciate that. So and thank you for the panelists as well. I really had a good time having this conversation. Thank you.
Thank you very much, Samir.
I think everything relevant was said. I just want to have an homage for Cedric because he was one of the, let's say, the lobbyists, or not lobbyists, but the people that brought consciousness, at least in my case, for Morocco, by disseminating the 2017 study of the IEA. I think that was led by himself and his team at that time. And he is a friend of Morocco by history, but he can speak about this later. And I really want to thank him, I mean, formally in this session for his contribution that has developed and created lots of entropy, as we say as a physicist. Thank you very much for that, Cedric. Thank you.
Thank you, Samir. I'm still alive. It's a bit early for an eulogy, but thank you very much.
Thank you, Samir. Of course, I join my voice to Samir for Mr. Philibert. I didn't know him only for hydrogen, but also for CSP and for renewables in general. So, and as a friend of Morocco. I think that we are just in time. We're a little bit late. So thank you very much all. I was really honored to participate with you to this panel. It was very interesting, and I hope that next year we will come back with more innovations and more technologies and strategies that will allow us to be sure about developing more this molecule in our countries and our regions. Thank you very much, and thank you for the organizers to allow us to have these discussions and to give us about 20 minutes more.
You still stay with us. You stay with us for PhD students presentations.
Sorry.
Stay with us. We still have 3 presentations of PhD student presentations.
Yeah, I know. So thank you very much, and we will continue with the other presentations now. The 3 other presentations now, but I apologize for the presenters. They have 20 minutes. They are 20 minutes late. I don't know who will make the next presentations. I will say who are the responsible, present the responsibles. Yasin Nasruddin, Hanan Aitu Saleh, Yusra Filali Baba, Abd Shafiq Harraq, Samir Rashidi. Yeah, you will find Samir another time. And Abd Samad Faiq. They will present us the screening of the most favorable metal oxide system for H2 production via solar thermochemical water splitting. The floor is yours.
Hello everyone, dear professors, dear participants. Today I'm going to present to you my recent work, which is entitled Screening of the Most Favorable Metal Oxide Systems for Hydrogen Production via Solar Thermochemical Water Splitting. This presentation will be conducted according to the following plan. Firstly, an introduction, then I will talk about the process of the thermodynamic study that we have carried out. After, I will present to you the results of our study, and I will end with a conclusion. So, as you know today, the use of fossil fuels as an energy source presents serious environmental challenges and economic impacts. For that, hydrogen represents a clean energy vector that could efficiently substitute the conventional fossil fuels, and this clean material that can be produced from green sources such as water and solar. So the thermochemical water splitting method is among the promising methods that produce green hydrogen, and this method involves the splitting of water via a repetitive and successive series of chemical reactions. In 2-step thermochemical cycles, a low valence mineral oxide is generated through reduction of a higher valence mineral oxide, where oxygen is produced, Then the reduced metal oxide reacts with steam during the oxidation reaction, and the hydrogen is generated. So many two-steps water splitting cycles that are based on redox metal oxides pairs have been studied, and more recently the efforts are directed to the development of materials that reveal low reduction temperature and which have the ability to provide water molecules splitting and have a good cycling stability. So the aim of this study is to make a general screening on different types of materials intended for two-step thermochemical water splitting that are compatible with the operational condition of the concentrated solar power. For that, a theoretical thermodynamic study was carried out to determine the feasibility of redox reactions and investigate the possibility of water splitting using steam or an oxidant reagent to promote the oxidation step. So the thermodynamic study was performed according to these following equations, and which allow to calculate the variation of Gibbs free energy in function of the temperature. I will start with pure metal oxide pair. Among the studied metal oxide, strontium oxide and antimony oxide involves the lowest reduction temperature, 390 degrees Celsius and 840 degrees Celsius. In the case of the oxidation step, the oxidation reaction by water of the studied materials showed the non-feasibility of the water splitting using these metal oxides. Therefore, a stronger oxidation agent such as sodium hydroxide should be substituted for the water. Besides, the oxidation investigation remains only interested in oxidation temperature in the case of antimony oxide, and which is 510 degrees Celsius, and it's the lowest found compared to the oxidation temperature of materials already studied for thermochemical water splitting. For the spinel metal oxides, the results obtained indicate that the thermal reduction reaction for cobalt trioxide occurs at temperature of 980 degrees Celsius, while the reduction of manganese oxide takes place at 870 degrees Celsius. The theoretical oxidation of the reduced cobalt and the manganese oxide is not possible with water. However, when a strong oxidant such as sodium hydroxide is used, this reaction becomes possible, and the results show that oxidation of the reduced cobalt and manganese occurs in temperatures of 600 and 930 degrees Celsius respectively. So to conclude, as I showed you in this study, a thermodynamic study of the redox properties of several types of metal oxides based materials for hydrogen production via two-step thermochemical process has been reported. However, the obtained results figured interesting redox properties of new redox pairs such as antimony and strontium oxides with attractive low reduction temperatures of 830 degrees Celsius and 390 degrees Celsius respectively, and further efforts are needed to improve the potential of these materials for use in the production of hydrogen by the thermochemical water splitting process. And thank you for your attention.
Thank you very much. I will give the floor for the second presentation from Mr. Mohammed Amin Babai, Mr. Mustafa Adar, and Mr. Mustafa Mabrouki. The subject is modeling of and simulation of OPEM FC fuel cell using three-dimensional multi-phase computational fluid dynamic model. The floor is yours.
Good morning, everyone. I'm Mohamed Ibn Babai, PhD student in renewable energy at University Sultan Moulay Slimane Bimlal. It's a pleasure to be with you at this conference, and I will thank you for this opportunity that you give me to present my work, modeling and simulation of PEM fuel cell using CFD model. Without delay, I will start by revealing to you my work plane, summary, introduction, modeling, simulation results, and conclusion. So the objective of this study is to numerical for three-dimensional non-isothermal computational fluid dynamics model of PEM fuel cell. Details analysis of the fuel cell performance under various operation conditions have been conducted and examined. As an introduction, energy issue currently cover two challenges. One is related to the risk of depletion of fossil and fossil resource. The other is environments. The source used today have finite reserve, both for fossil fuels like hydrocarbons, coals, and for fossil fuels, uranium. The fuel cell is therefore the missing link transforming chemical energy into electrical energy that can be handled with high efficiency. The fuel cell uses to redox reaction between hydrogen and oxygen to produce water, electricity, and heat. And we move to fundamentals of PEM fuel cell. Fuel cells are made of four major units like PEM, GDL, gas diffusion layer, catalyst layer, and bipolar plates. So the protons are conducted through the membrane to the cathode, but the electrons are forced to travel in external circuits because the membrane is electrically insulated. On the cathode catalyzed, oxygen molecule reacts with the electron and proton to form water, the only waste products in this type of fuel cell. The governing equation of the model. The main assumption adopted in the model are thermal equilibrium, membrane, catalyst layer. The mathematical model is composed of governing equation for the conservation of mass, momentum, species, energy, charge, and water transport into membrane. Condition. The GDL and the catalyst layer were surrounded by sided plates and the inlet and outlet plane. So the boundary condition at the inlets and outlets check the no-slip condition for the velocity and the no-permeable condition for the species mass fraction. The Dirichlet condition is used at the inlet of the cathodic and anodic channels for the species height and mass conservation equation. The mass flow rates are considered constants at each channel. The Newman conditions are employed for all parameters at the interface fluid, solid to non-slip condition, and zero species flow are considered. So for simulation results, forcible reaction gas and temperature distribution inside the fuel cell. It is figure 1, hydrogen molar fraction distribution into anode channel and GDL at base case condition. In the GDL, the hydrogen concentration under the solid parts of the bipolar plates is lower than that under the low parts channel. So we have two figure 1 and 2. As we said, the concentration of hydrogen into catalyst layer is balanced by the quantity of hydrogen received from the flow channel through to diffusion layer due to concentration gradient, which rewards the quantity of hydrogen consumed. The second figure hydrogen molar fraction distribution in 3 dimensions for the anode catalyst layer. The detailed distribution of molar concentration and hydrogen consumption are shown in figure 1 and 2. The hydrogen concentration decrease from 2 inlets to 2 outlets of the channel due to the consumption of reaction into catalyst layer. Distribution of hydrogen and oxygen. The molar oxygen concentration at catalyst layer is shown in figure 3 and 4. So at a low current density, the oxygen consumption rate is low enough not to cause diffusive limitation, whereas at high current density, the concentration of oxygen under the land area has already reached near zero value and cannot further decrease. The consumption field of oxygen and hydrogen are similar, except that the hydrogen consumption is twice as large as the oxygen consumption. The temperature distribution inside the fuel cell for this current density is shown in figure 5 and 6. The maximum temperature occurs where the electrochemical activity is high, which is near to cathode side inlet area. However, the temperature increase for low current density is small, only 1. Conclusion, this work presents a simulation study of a fuel cell, single cell, by analyzing the physical phenomenon into cell core. The transport of charge into electrode and of ions of the membrane represented by the conservation equation to cell voltage being as boundary condition. The gas transport into diffusion layer consists of Stephen-Maxwell diffusion, binary diffusion of the gas mixture, and convection due to pressure gradient. This model describes the reaction layer taking into account the dimension of the agglomerates that structure this layer. And thank you for attention.
Thank you very much. I think that Mr. Samir Rashidi left us. So I will let the floor for the last but not least presentation from Mr. Hakim Azouk, Mr. Hussein Bilmili, Mr. Bouazzaf Kek, and Mrs. or Miss Samia Haroni. The subject is new optimized sizing based techno-economic analysis of PV system with hybrid storage hydrogen battery. The floor is yours.
Hello everyone. I am Hakim Azouk, PhD student in renewable energy at University of Science and Technology, Houari Boumediene. In this presentation, I will represent my work, which is the new optimized sizing-based technico-economic analysis of PV system with hybrid storage S2 battery. The work plan is as follows. We start by an introduction, then we describe our system and storage units modeling. Thereafter, optimal energy management design, followed by results of simulation. We finish our work by conclusion and perspective. Solar energy for production of hydrogen is the object of intense research, particularly in small-scale applications and standalone system in remote areas. In this paper, we will study the new optimized sizing based on technico-economic analysis of PV system with hybrid storage S2 battery by taking the mismatch between the intermittent solar irradiation and the time-varying load demand into account. Detailed and accurate mathematical models are employed for the simulation for each subsystem to access to the performance of the integrated system. Thus, an optimal energy management strategy is proposed for the standalone PV S2 systems for maximum production of electricity and hydrogen to guarantee a permanent load, ensured by photovoltaic panels based on the optimal energy management, and the system sizing method is developed for achieving high energy efficiency with rational system cost. The configuration of the standalone PV S2 battery system considered in this paper is shown in Figure 1. This system includes both short-term and long-term energy storage. A battery bank is usually used for short-term energy storage due to its high round-trip efficiency, fast charging, discharging capacity for smoothing the fluctuations of both load and renewable energy sources. However, since the battery bank has low energy density, self-discharge, and leakage, it's not suitable for long-term energy storage. Therefore, the combinations of a battery bank with H2 storage bank can significantly improve the performance and the reliability of the standalone RES systems. The system description and storage units modeling is presented in this slide. The design analysis and optimization of such systems require the development of mathematical models for all individual components. The accuracy of modeling methods described in this paper is validated by experimental data issued by the manufacturers. The simulation results show good agreement with the experimental data. This slide shows the optimal energy management design. Talking now about optimal energy management design. The primary objective of choice of PV H2 system is to provide sufficient and reliable electricity to meet the end-use power demand and store the excess energy into the battery and H2. Figure 6 shows the corresponding diagram of energy flow within the standalone PV H2 system. The direct transmission, the battery bank for short-term energy storage, and H2 bank for long-term energy storage. Now we discuss the result of simulation. For designing of standalone PV-H2 system with required capacity, it is a must to properly size the system component. Based on the above optimal energy management strategy, a systematic system sizing method is developed. The sizes of the system component are figured out and listed in Table 1. The result of the simulation of the dynamic behavior of the standalone PV-H2 system are presented in Figure 8 and 10 through the power delivered by PV generator, the state of storage of the battery bank, and that of the hydrogen tank, respectively. Figure 9 shows the power consumed by the electrolyzer. The slide 7 shows the technical economic analysis. The economic assumption in terms of investment, operation, and maintenance and replacement of the different components considered in this paper. Figure 11 shows the breakdown of the component cost of the proposed PV-H2 battery system. And Figure 12 illustrates the cost structure of the PV-H2 system. This cost structure has been obtained considering all cost categories. We can observe on this figure that the capital cost is more inexpensive as the replacement cost. At the end, the work we carried out through the technical economic study of PV-H2 system enabled us to contribute to the development of simulation tools for the various components of the system. We also simulated the dynamic behavior of the system and the condition of the installation site in unique programming code. Thank you for your attention.
Thank you very much. It was our last presentation, and we could see during these three last presentations that we are talking about a large panel of H2 production, from production, of course, but also use, talking about fuel cells, and then a technical economic analysis of PV with hybrid system, with hybrid storage. Sorry, I will give another time the floor to participants if there are any questions. I will see myself if there are any questions on the panel. So, is there any question to our presenters? I cannot see. I cannot see any new question. We will try to conclude this. Yeah, sorry, Mr. Dieter, the floor is yours.
Thank you very much. Since there are no general questions, let me ask a very specific one concerning the first talk, actually, talking about oxidation processes. You mentioned that you consider sodium hydroxide an oxidizing agent. Of course, the oxidation potential is pH dependent, but I still think that in thermodynamics, we should not talk about an oxidizing agent if we talk about the pH. Thank you.
Okay, someone from the team to answer?
Yasin Nasruddin, the floor is yours. You can activate your mic.
Yasin, you can go ahead and answer Mr. Dieter.
Yasin, please activate your mic. Turn on your mic.
Hello, everybody. Am I in the right session? No.
It will depend. If you are looking for hydrogen, yes, but if you are looking for another technology, no.
Okay, but then I don't have the right link. Wait a second.
Okay.
Happy
to see you.
Professor Stefano,
yes.
Your
Yeah.
session will start in few minutes.
So I should stay here or should I go south?
Yeah, stay here, stay here.
Okay, very good.
You are welcome. So,
Okay.
Yasin, Hanan, or Yusra, anyone that can answer Mr. Dieter? Oh, I think that you will not have the answer, Mr. Dieter. I hope that our colleagues are continue to be connected. If there is no other question, we'll try to conclude. But I will ask my friend Samir to give you a written answer anyway, because I don't like to let this question without answer. So I will try to conclude and to give the floor to Mr. Yusuf another time. I would like first to thank the organizers. Thank you, Professor Yusuf Zaz, for the invitation. Thank you for allowing me to moderate such very interesting discussion, very interesting panel with a lot of people that I am respecting a lot, because I know them outside this panel, and I was really honored to have these 2 to 3 hours with them. I hope that the future of hydrogen will be developed with Africa now. I hope that for this technology, or let's say for it is not only a technology, it is really a change in humanity manner to use energy, and I hope that Africa will not be only a follower like during the last century, but from the future, I hope that we will be also able to lead and to work with our colleagues, of course, in Europe, America, and Asia, and to be part of this new revolution of energy that is being gone or being developed now in our region. Thank you very much for the invitation. The floor is yours, Mr. Zad.
Thank you very much, Mr. Abdurrahim Jamrani, for your for sharing, for moderating this session. Is really great. It's really nice, well organized. Thank you very much also for keynote speakers, Dr. Sonia Clay, Kalman, and Augusta Eragon, and Dr. Samir Rashidi. Thank you also for our really fantastic follower and supporter, the Professor Dieter Messner. He's always with us I think is I give him the floor to give word before Professor Dieter.
Yeah, thank you very much. It has been a very interesting meeting and a very nice discussion. Thank you very much. I appreciate very much. Thank you.
Thank you very much for all participants, for all attendees, for authors, for presenting their papers, and hope to see you soon. All participants can ask for attendance certificates. I will give them the link to ask for certificates. Dr. Cedric, you can give word before, no? Yes.
Well, no, I just wanted to thank the organizers for inviting me and for making this event happening. It was quite an interesting discussion yesterday and today, and yeah, I think things are moving with an explosion of ideas and concepts. They will not all survive, but some will and will help. Thank you very much.
Thank you very much. You are exactly in the time. Now is 3 p.m. GMT plus 1 Moroccan time. It's really the true time to finish this workshop. Thank you very much, Mr. Abdurrahim Germani, for really respecting the time of this workshop. Thank you very much.
Goodbye.
In few minutes, we switch to the next workshop about lithium batteries, advances in lithium-ion batteries and beyond. It will be chaired by, moderated by Dr. Amir Khalil. Let's join us in a few minutes to continue the next workshop. Bye-bye.
est-ce que sur le fond, vous pensez ce que vous avez dit? C'est-à-dire, est-ce que vous estimez que les propos d'Éric Zemmour sont aussi l'expression de son judaïsme? Est-ce que vous faites une équation entre il est juif, donc il est pour le respect?
Après qu'on m'ait reposé cette question, je me suis dit, voyons, moi, j'aime pas donner raison à ceux qui montrent du doigt comme ça, qui accusent, bon. Mais je me suis dit, enfin, ni au débarquement de Provence, jamais ils n'ont manqué à la France, alors que bon nombre de ceux qui leur font des leçons, eux, exactement incompréhensibles,
Khalil, your microphone is off.
Yes, hi, good morning, or good afternoon, I would say.
Good morning, Dr. Amin.
Excellent, excellent. So I can see that Stefano is here, and also Mohammed Shakir is here, the two main speakers. How are you, Stefano?
Pretty good, thank you.
Good, good. Looking good, huh?
Yeah.
The situation in Germany is no good, unfortunately.
It's snowing here, but
It's snowing. Okay, well, that make things worse with the COVID, I guess, when it gets cold.
yeah.
Very good. And I think Mohammed Shakir is also here, I assume. Yeah. Yes, I can see him. Yeah. Yeah. So how was the panel discussion yesterday? I'm really sorry I have to run to the airport so I can spend the Thanksgiving holiday with my family. So one thing she says, I think you have to pay attention to Thanksgiving holiday when you organize your conference. So usually November 25th, I guess, the week of November 25th is a big holiday in Canada and US. So very few people usually want to talk or attend meetings. So yeah, in the future, if you organize the next one next year, maybe you should stay away from this week.
Okay.
Yeah.
I will consider for the next edition.
Yeah. Otherwise, it will be very difficult to bring in folks from at least the US and Canada.
Thank you very much.
So we'll start maybe in Stefano, if you need a little more time, we can start maybe in a few minutes, and this you can have more than 35 minutes if you want.
Don't tell me this, when I start to talk, I never stop. So I will try to limit myself.
But I think maybe for the sake of the participant, I think let's just stick with the time. And if we go over, we have plenty of time. We are only two keynote speakers today. So the way it's going to work is you will have up to 30 minutes. I can allow for a little more if the presentation is very interesting. And then we'll entertain few questions, and after that we'll move to Shakir, do the same things, and then we'll have a panel discussion. So what I would like to invite is all the participants. We have about like 200 or so. If they have any questions related to these two topics, which are electrolyte, ionic liquid, and solid state, but also any general topics on battery in general. This is an opportunity to ask questions in front of these famous experts. They will give you an opportunity to learn more based on your questions. So that would be really, I expect we can get as much question as possible. I like to entertain questions, and it has to be anything related to battery. Either lithium-ion battery or beyond lithium-ion battery is fine too. I know that Stefano has worked on beyond lithium-ion battery. I have done quite a bit of work on that. I'm not sure if Gao is here. I know that Theo sent me an email. Unfortunately, he's not able to join because he has some urgent matter. But I think between four of us with Moad, we should be able to entertain any questions from the audience.
Yeah. Yep. We'll try to do our best.
Yes, that's the right answer. Maybe you can share your presentation, Stefano?
Yeah, I'm doing it. Is it okay?
Yes, we can see it
now. So you have the presentation mode.
Excellent. Yeah. So let's just wait a few minutes, and then we can start officially.
No problem. Ah, there is some self-animation.
Yeah.
So I would like to apologize for yesterday. I could not attend, but it was the kickoff meeting of a huge, large European project with, like, I don't know, about 65 partners.
Wow.
And I am the coordinator, and I just could not leave it. Okay, I'm very sorry.
Of course. No, it's okay. We understand.
Where are you, Cal? In the US? Or?
Yeah, I mean, you know, with the pandemic, I can't go anywhere. But I was in DC yesterday. You know, I had dinner with the Deputy Undersecretary of DOE for topics that I'm trying to do with Morocco, and then I had to fly. That's why I couldn't attend the panel session. So,
but
I'm home in Chicago now.
But the borders are open. I mean, 2, 3, or 4 of my students are actually flying to US tomorrow for the Boston meeting, the MRS.
Oh, yeah. So US is okay. I think we still have a number of cases, but by population rate, Germany is like 3 times higher than US.
Yeah. Germany is better.
Yeah.
I was in Italy last week, and I was almost considering to stay there a little longer.
Yeah.
Because in Italy, we are doing very well. I mean,
yeah, the Italian have done extremely well. You're right. Yeah. I know why Germany's suddenly station has degraded very, very quickly.
Because we are in the government transition. So there have been election. The old government, let's say the leading party, did not win this time, and then we are in the transition between the old and the new governments, and nobody wanted to take a decision like strict decisions. Okay, but now they finally managed to make a new government, so I guess very soon they will.
All right, we'll see. They really have to do something about it.
Yeah. It's
okay.
Okay.
All right, maybe we can start. Yeah. So first, thank you very much for staying late with us in Morocco. Today is Friday. It's the last day of the week, and it's the afternoon now. But we have a very interesting session. 2 outstanding speakers, Stefano Passarini that I will introduce soon, and also Mohammed Shakir from Renault. So we have one talk from the academia and another talk from the industry. So it'll be really interesting. And it's in very, very hot topics, which is electrolyte. As you know, the electrolyte basically can dictate the life and the safety of any batteries. So let's start with the first speaker. It gives me great pleasure to introduce Stefano Passarini. He's a professor at Carceri Institute of Technology. He's also the director of the Helmholtz Institute of Ulm that I visit. Is a very large institute. Is an internationally recognized pioneer in the field of ionic liquid and other field in the battery as well. He has authored over 600 papers with an H-index of 90, which is very impressive. He's also an editor-in-chief of the Journal of Power Source. So if you want to publish in Journal of Power Source, this be your man. And I hope he will give some favor to good papers from Morocco. And he won actually many awards. He's a fellow of the SCS and others through his career. So he will be talking about ionic liquid for the long-term cycling of lithium metal battery. Stefano, the floor is yours.
Well, thank you, Cal, for the kind invitation. And my first slide actually is about you again. You might remember the last ABA meeting, which was organized here in Ulm, thanks to you, that you gave us the honor, myself and Dr. Wolfram Merens, to organize. And this was one of the last meeting in person, actually. I managed to attend. And it was very exciting also because Professor Whittingham received his Nobel Prize, and he received the call from Stockholm right after his plenary lecture. Anyway, beside this, we also, out of this meeting, we also came up, and Carl obviously was involved, we also came up with this study about batteries. It's a joint study of the German Ministry for Education and Research, the DOE, the Japanese NEDO, the Chinese Academy of Science, and then ZSW and HIU. And I mean, in this study it's clearly shown that lithium batteries, lithium-ion batteries, and also maybe lithium metal batteries will definitely lead the EV market for the next 10, 15 years. And maybe the speaker after me will confirm this estimation if this forecast is correct. The reason of this, nonetheless, I mean, a huge expansion of the market is expected, and then we definitely need to work a little bit on improving the sustainability of both lithium-ion batteries and lithium metal batteries. Why is the market expansion, the forecast on the market expansion so, let's say, exciting? It's clear for this calculation. Okay, what you see here, it's a estimation of the or energy efficiency from renewable to actually usage in vehicles, and you see that practically there is not a comparison. I mean, battery-powered vehicles are extremely more efficient than hydrogen fuel cell vehicles if you consider as starting from renewable electricity, and even more than power to liquid. So using the renewable electricity to produce liquid fuels and then use the conventional vehicles we are using now. So that's the clear reason of this very optimistic forecast that somebody even claim is dramatic, which in Italian has a different meaning than in English. But anyway, you see that the demand for lithium-ion batteries in the next 10 years is really dramatic with the English meaning. And the number of batteries we will have to produce in the next 10 years, it's really huge. And at least in Europe, there is a blossoming of these gigafactories now, established or built by mostly by Asian, I have to say. LG and Samsung are already producing in Europe, and also some European activities are starting, as well as, for example, Tesla is building a gigafactory near Berlin. And CATL, I think we will have a panelist from CATL a little bit later. They are also working nearby. I mean, it's about an hour and a half. Nonetheless, and this will be extremely critical in Europe, I have to say, as I mentioned before, we need to make batteries more sustainable. In Europe, there would be a big problem as soon as the gigafactory will start opening. There will be a big problem about associated with the environmental concerns. I think already the foreign company establishing production in Europe, especially in Germany or the western part of Europe, are encountering serious problems associated with the sustainability of batteries. I mean, presently there are basically three approaches to make batteries more sustainable. The first one is actually the fabrication of the positive electrode using aqueous binders rather than fluorinated polymers, which require toxic solvents. The second point is, but this is addressed, I would say, worldwide, is development of cobalt-free cathodes. And the reason it is addressed worldwide is that not only cobalt is toxic and generates some political stress, let's say, but the cobalt is also rather scarce. So we need to move toward the other materials. I don't know outside of Europe, but in Europe, actually, there is now a strong consideration of organic active materials, although their real practical use needs to be demonstrated. It's not fully demonstrated yet. And a third point actually is to make recycling of electrode materials as such rather than burning. And in particular, I'm mentioning here graphite anodes, because right now the standard recycling of battery cell involve a thermal step at the beginning, which transform all the graphite in CO2. And this is twice a problem. First, because CO2 is generated. Second, because graphite is burned and then needs to be remade, which obviously generates even further CO2. Anyway, at HIU, I mean, we are touching all these subjects actually, but we are what I will present today is mostly development of cobalt-free cathodes. Okay, and also the use of these electrolyte, which based on ionic liquids, which are pretty stable. Okay, in fact, if we want to achieve the targets indicated, we need to go to very high voltages using, for example, oh, sorry, this animation is too fast, using these lithium-rich materials or nickel-rich materials, which have definitely high energy and which can give cells with very good performance needed to have driving ranges of 500 kilometers or more than this. Okay. As I mentioned before, there are serious concerns with cobalt, and this is the second reason why we are really trying to switch or to move toward cobalt-free electromaterials. Okay. Lithium in the past was actually assumed to be a problem. There were concerns about availability of lithium, but actually there is quite a lot of lithium worldwide. The real problem right now is really to get rid of cobalt. Okay. Anyway, so that's the interest of developing lithium-rich layered oxides, cobalt-free. You know, they are practically, they can be seen as a mixture of two different layered materials, the LiMO2, which are actually electrochemically active and can release and uptake the lithium in between the layers, and the monoclinic lithium manganese oxide, which is supposed to be an inactive material. Okay. However, when we combine them in a single material, so in a lithium-rich material, what happens is that during the first charge, there is actually a kind of decomposition of the inert material, which is releasing some additional lithium, and it's transforming into an active material. But what is the problem here? This is a very high performance material, very high capacity, but the real problem is that this change occurs at very high voltage, above 4.45 volts. There is reported also that some oxygen is actually evolving out of this reaction. Okay, but actually what is most likely occurring is the formation of peroxo bonds inside the active material. But this, as I mentioned, this activation problem, which occurs at 4.5 volts, is really stressful for the electrolyte. Okay, and as a matter of fact, if we look at, for example, a standard cell made employing this lithium-rich material, we see that in order to achieve the full capacity of the material, we need to go to very high voltage, but then the fading, it's really dramatic, and we can kind of lose substantial performance in a few cycles. Okay, so the advantages of this material I already mentioned are the high specific energy. They can very well be above 900 watt-hour per kilogram, relatively low cost because they don't contain cobalt. Okay, but still there are serious challenges, which are poor rate capability, low initial Coulombic efficiency, and what is really the most severe problem is actually the voltage and capacity fading, which occurs upon cycle. So this fading is actually due to the fact that during this activation, there is a migration of nickel inside the structure, and we go actually from a layered structure to a spinel-like structure, which then finally ends into a rock salt structure, which is inactive. And from the electrochemical point of view, from the charge-discharge cycles, you see this is the first activation cycle. Okay, these are the following cycles, but what we see is a continuous capacity fading occurring upon cycling. And even worse, we observe this voltage fading upon cycling, which is actually leading to lower energy efficiency and also capacity and energy in general. Okay. What it has been found is that this structural transformation is actually starting from the surface of the particle, okay? And then it's proceeding toward the bulk. And upon prolonged cycling, actually, most of this material ends up being inactivated. There have been different approaches to solve this problem. One is the lattice doping. So, for example, for the lithium-nickel, lithium 1.2, nickel 0.2, manganese 0.602 material. Iron doping, for example, it's definitely helpful in reducing this degradation. Okay, but considering what I said before, is that the degradation of the material starts from the interface of the particle with the electrolyte. We are actually focused on the development of a cathode electrolyte interface, which can protect this or avoid this degradation reaction for occurring. So our approach, it is actually to employ ionic liquid-based electrolyte, which can stand the high voltages and additionally can provide elements making inorganic compound reach CEI and then protecting the active material for degradation. So these are the building blocks of our electrolytes. So as I mentioned, are ionic liquid based. Most of you knows that ionic liquids are salts which are molten at room temperature, and this is usually occurring because of bulky cations, which have a high degree of freedom for rotation of the CH2 groups, and this prevents the crystallization. And also they are usually composed of these bis-fluoro or bis-sulfonylimides. So we have a nitrogen to sulfur for oxygens. This is very good for coordinating lithium. And then either a fluorine bound to the sulfur or, for example, a CF3 group bound to the sulfur. From now on, I will just use these codes, otherwise we stay here till tomorrow. Okay, these are the performance of these ionic liquid electrolytes. You see that they have conductivity which are not extremely excellent at room temperature, but anyway, they are in the order of 10 to the minus 3, the order of 1 to 2 millisiemens. Okay, they have viscosities which are not too high. Okay, this is actually inverse temperature here, sorry. No, it's correct. Okay, yeah, it's growing in this direction. And what I mentioned before, they are pretty stable at high potential. So they do not decompose. Here, what you see is the high potential decomposition investigation, the limit at high potential, and what we use here to exacerbate. So the reaction, instead of using like a nickel electrode or a platinum electrode, we actually use an electrode made only of super C, so high surface area carbon, which would definitely stimulates the oxidation of the electrolyte, and nonetheless we see that the electrolyte is stable, pretty stable, up to 4.7 volts. Okay, so in general, from what I mentioned, the advantages of this electrolyte are low flammability and low volatility. The two things are related, actually. They have a wide electrochemical stability window, but on the other hand, they have a little bit of problem related with conductivity and also cost. They are not produced on the large scale, so they are expensive. But the other great advantage they have, it is possible to cycle lithium metal to employ lithium metal electrodes with this electrolyte, and as you can see here, we can actually cycle a lithium cell for more than 1,000 hours, and we still get very reproducible performance during plating and stripping. Okay? And also relatively low over voltage. Okay, so synthesis of the material, nothing special. We do some ball milling, then we do a preheating, calcination, and then we obtain the lithium-rich material. So no cobalt, you see, only a little bit of nickel and 25% of nickel and 75% of manganese. So low cost, and we managed to get a pretty crystalline compound with interlayer of 4.71 angstrom. So it's a rather simple synthesis. We don't use any doping or coating of the material. Okay. And here you see the effect of the ionic liquid-based electrolyte. Okay, so what you see in orange, it is actually the same electrode in a lithium metal cell, okay, and nickel manganese cathode, okay, cycled with the ionic liquid electrolyte. We have somehow lower capacity at the beginning with respect to the conventional LP30 electrolyte, but on the long term, there is absolutely no comparison. The capacity is much more stable, and after 500 cycles, we still have more than 80% of the initial capacity. Okay. Here you see the rate performance on the other end, and immediately you can notice one of the problems I mentioned before for the ionic liquid-based electrolyte. It's the rate performance. Definitely at high rate, we cannot achieve very good performance still. Okay. But what is even more important, or the major benefit of the ionic liquid electrolyte, is actually the average voltage, which is even more important than the specific capacity, because you see that the average voltage of the electrode cycling in the conventional electrolyte, it's substantially lower and less stable than the average voltage of the electrode cycling in presence of the ionic liquid electrolyte. And you see it even better here, okay? Going from the third cycle to the 500 cycle, we have a very moderate decay of the voltage during upon cycling, while with the conventional electrolyte is much higher. Okay, so definitely we have improved cycling stability and mitigated voltage decay. Okay, and here you can see an even further extended cycling, where we go up actually to 2,000 cycles, and we still have 56% capacity retention. Consider that for a lithium-rich material, this is really a pretty good number. And the average voltage is also staying pretty high all along the 4,000 cycles, 2,000 cycles. Okay, so if we compare the performance of our lithium-rich electrode in ionic liquid electrolyte with all other studies in literature, so obviously good is in this direction, low voltage decay, low capacity decay. You see that the combination of the lithium-rich material we synthesized and the ionic liquid electrolyte is extremely good. And what is the reason of this improvement is what I said before. This is a structure of the pristine material. This is what happens upon cycling in LP30. You see that there is clear degradation of the material at the interface near the surface of the particle, with the formation of the rock salt phase. Why with the ionic liquid electrolyte we do not observe such a degradation? Okay, which is then telling us that the use of the ionic liquid electrolyte in some way is capable of maintaining the layered structure of the active material. And with the XPS investigation, actually we understood why is this, okay? So you see up here, this is the surface of the electrode cycled in the conventional electrolyte. This is the surface of the electrode cycled in the ionic liquid electrolyte. And what you can see is that we definitely have a strong excess of these lithium inorganic compounds okay, so which are definitely stabilizing the cathode electrolyte interface, preventing the further decomposition, while when we use the LP30, we have kind of intense or large presence of organic compounds on the surface, okay? Yeah, and even better, only in the case of the ionic liquid electrolyte, we have also the formation of this sulfate, sulfite, and sulfide components, which are definitely protecting the interface. Okay, so the use of the ionic liquid is really critical for the formation of the cathode electrolyte interface, which is then critical for the stability of the positive electrode material. Okay, so we also investigated, I mentioned at the beginning that during the activation of these lithium-rich materials, there is usually oxygen production occurring, and you can clearly see it here. You see, this is a peak of oxygen generated inside the cell during charge, okay? And actually, this is also, oxygen is also produced in the following cycles, while when we use the ionic liquid electrolyte, we have a much lower formation of oxygen in the first cycle, and we don't see any oxygen forming upon cycling, which is extremely important. Okay, so this is again a clear evidence that when the CEI, the cathode electrolyte interface, is established, then oxygen release does not occur anymore, and that means that the transformation to the rock salt phase is actually prevented. Yeah, we test the ionic liquid electrolyte also with the conventional anode material. Not graphite, but lithium titanium oxide. And in this case, actually, the performance are just unbelievable. We can get more than 5,000 cycles practically without any fading occurring upon cycling. So the ionic liquid-based electrolyte is extremely stable also with LTO. Okay. And here is a cell, for example, not using lithium metal, but using lithium titanium oxide as the anode. And you can see here that actually both the SCI and the charge transfer resistance in the presence of the ionic liquid electrolyte tend to increases a little bit in both cases, but tend to stabilize upon cycling, while for the conventional electrolyte, it keeps growing upon cycling, and this growth never ends. So definitely the ionic liquid electrolyte enables outstanding performance for high voltage lithium ion cells. Okay, we developed also other ionic liquid electrolytes for different purposes. For example, the phosphonium-based ionic liquid electrolyte have a great advantage. They are not extremely conductive, but they are extremely stable at high temperature. Okay, and you see that again, we have to work on the chemistry of the electrolyte. So we have to synthesize specific cations as well as specific anions. It's not that any anion works, but in order to get an ionic liquid electrolyte using a phosphonium cation, then we need to use this asymmetric imide anion. And then we get pretty good conductivity also at low temperature, okay? You see the differences, for example, in terms of thermal stability. So if we use the TFSI anion, then we have an extremely stable ionic liquid. IM14, so these asymmetric anion also offer pretty good stability. While, for example, FSI, which is very good for the pyrolydium-based ionic liquids, actually, it's definitely not performing well in terms of thermal stability. Yeah, so again, investigation of electrochemical stability window. Here you can clearly see what I stressed before, the importance of testing the high voltage stability of the electrolyte using a carbon electrode, so an electrode made out of super P, okay? And you see how much the real electrochemical stability window drops when you use such an electrode with respect to, for example, platinum or nickel. Okay, so it is really the best. It's using to use carbon composite electrode to measure the electrochemical stability window of electrolytes in general, not only for ionic liquids. Again, also this ionic liquid well perform with lithium metal. These are plating and stripping cycles with lithium metal, and you see that, however, at higher temperature, at higher currents is suffering, but at lower currents it's performing very well. Again, tests. Our standard reference electrolyte is always LP30. PIM is this phosphonium-based ionic liquid. Not much of a difference in the first cycle, except that there is less capacity, irreversible capacity in the first cycle. Okay, but again, on the long-term cycling, the ionic liquid electrolyte definitely outperform the conventional electrolyte once more, because the ionic liquid electrolyte is stable at high voltage and can form these very stable interfaces. Okay, you see here, for example, the evaluation of the ionic liquid electrolyte, based electrolyte at different positive voltages, and clearly at between 2.5 and 4.8, there is not much occurring in both cases, but when we go to like 5 volt or 5.2 volts, the LP30 gives up, let's say, dramatically, while the ionic liquid electrolyte can still manage to handle, I mean, stand these very high voltages. Okay, yeah, and as I mentioned, we developed this electrolyte based on the phosphonium cation, especially for the high temperature test. So if we need to make cells that have to work at high temperature, then you see that actually this phosphonium-based electrolyte can really stand high temperature, delivering decent performance even at 80 degrees centigrade. Okay, again, once more, the improvement in performance, I see that my time is almost over. The improvement of performance is actually associated to the formation of a protective layer over the active material particles. And you see that the fresh electrode, obviously we have these two big manganese peaks, okay? And in the presence of LP30 electrolyte, the peak completely disappear after long-term cycling, which means we get a very thick layer coating the electrode, while with the ionic liquid-based electrolyte, we still see the peaks even after very long term cycling, indicating that the CEI, sorry, over the active material, it's not too thick, but it's because it is pretty stable and it doesn't grow continuously. Okay, and again, comparison on the long-term cycling. Now here we are testing at 20 degrees C. We are no longer exploring the stability at 80 degrees C, and you see that actually the ionic liquid-based electrolyte has very stable cycling performance. There is not much of capacity fading occurring upon 200 cycles, while with the LP30 electrolyte, the capacity and voltage fading is extremely strong. Okay, and you can even see this better here in these SCM images, which are showing. Sorry, I forgot to mention. This is actually a commercial material from Korea. Okay, there is only a little bit of cobalt. This is a nickel-rich material, 0.88, 0.09, 0.03. And let me go back here. You see the performance of the ionic liquid electrolyte is much better. And the point is that actually the ionic liquid electrolyte is showing capable to avoid degradation of the secondary particle, while in presence of the LP30, there is a massive degradation of the secondary particle, which is due to the degradation of the primary particle surface. And in this case, we can, we actually use double anion in the ionic liquid electrolyte. This cell is a low loading cell, so only about 3 milligrams per square centimeter, but actually we demonstrated that this electrolyte is actually active also in pretty high areal loading. So these tests here, for example, are performed on a cell where the positive electrode has a loading of 9 milligrams per square centimeter. And you can clearly see that we have 100% Coulombic efficiency already from the third cycle. In the first 2 cycles, obviously, we have a kind of a lower Coulombic efficiency, but not too much lower, considering that we are going from 80 to 100. Okay? And we can get very stable performance and also with lithium metal anode. And with this, I want to conclude my presentation. Yes. So saying that ionic liquid-based electrolytes not only are not flammable and not volatile and can be recycled entirely at the end of the life of the battery, but they actually can work pretty well in combination with lithium metal anode. Okay. And then making possible the use of such anode toward high energy batteries. The room temperature ionic liquid electrolyte can stabilize the interface of lithium-rich and nickel-rich layered oxide, enabling long-term cycling. And then for specific application where high temperature could be hit during the life of the cell, phosphonium-based ionic liquid electrolyte are offer tremendous advantages and keep the stability of the cell. And with this, I just finish my presentation, acknowledging the funding institution, the Helmholtz Association, for giving us this nice building, the German Ministry of Education for funding in several projects. Some of them actually, Lilith and Lizzie, also involving Carl on the American side, and the European Union for funding. And obviously my group for the work, because they do everything, I only present most. And thank you for your attention.
Yeah, thank you so much, Stefano, for this outstanding talk. Really appreciate it. So as I said in the beginning, we're going to entertain a few questions from the audience and also from the prospect speakers of today's workshop. So I do have one question from the audience that I would like to ask you, Stefano. Of course, he give you a lot of credit. Thanks for this great talk. He said, is there any relationship between the stability of cathode materials and the concentration of the ionic liquid? You know, as you know, in the conventional electrolyte, when you increase the concentration of the salt, you can see some stability at high voltage. So is there a similar trend here?
Yeah, practically there are no solvent molecules in ionic liquid-based electrolytes. So the neutral molecules are not there, and they obviously do not react. And this is also kind of giving this is also the reason why we don't get much organic compound in the CEI or the SCI, because there are no solvent molecules. On the other end, we are working with practically about 3 molar. The equivalent concentration is 3 molar, and this is obviously boosting the cost because the anion are actually the most expensive component.
And also the viscosity, actually. So
and the viscosity, yeah,
which is a big problem. Yeah. So another question is, why the SCI formed using the ionic liquid is more stable than the carbonate based? I think you have touched on that on the SCI and XPS, but yeah, please go ahead.
I practically mentioned that the XPS shows that what we get is mostly an inorganic rich SCI and CEI, actually, in both cases. And this is these layers are much more stable than the mostly organic based layers. And the reason is that there are no solvent molecules to form the thick organic layers. Okay.
Yeah. Good. So I have actually a couple of questions and maybe a suggestion to you that could be a source of potential collaboration. The first one is you showed that your electrolyte is stable and you do a CV, which is fine, especially with the carbon. That really shows the minimum of the maximum voltage stability versus nickel or platinum. But I would say maybe you should do a floating test of a real cell and look at the leakage current, because you can also look at the impact of the oxidative power of the cathode. Like if you take, for example, a nickel rich with carbon, and then you start it at different voltages, maybe that will give you a real estimate of the stability of your electrolyte.
Yeah, that's definitely a measurement that is frequently done for supercapacitor, actually. So keep the cell on constant voltage. But for lithium-ion batteries, this is quite risky, right? It's a quite risky test also on commercial lithium-ion batteries.
Yeah.
Because sooner or later some reaction will occur. Yeah. Okay.
Yeah. So well, you're right. No, we do have actually a high precision equipment where you use very small, very tiny batteries like a button cell, and I don't think so there is a major risk when it comes to small tiny batteries in this case. Just to look at the chemical stability, if you want. Exactly. So the other things, I do agree with you. Let me see. I need to. Okay, it's interesting. We can take our time. There's only two talk. So I'll say this, and then I will come back to the audience for a few questions that they have. I do agree with you that the interface reactivity is first happening in this material, and we did actually recently quote the material with a PDOT. It's a polymer that is both ionically and electrically conductive. And we've seen some results similar to what you've seen. So I was thinking maybe investigating the combined effect of a coating like this one, because this one coat the whole particle, because you start with the gas phase and you polymerize the whole things and your ionic liquid. Maybe you can even add some conventional electrolyte in a hybrid to enhance the conductivity and reduce viscosity and come up with a system that may work. So that's something you can think about it. Maybe we can offline we can discuss it as a potential collaborative work. So let me go back to the questions. Okay, in your opinion, this comes from Mohammed Akil. He has a couple of questions. Could a polymerized ionic liquid be used in a solid polymer-based electrolyte? Can you polymerize it and use it as a hybrid system, or as it is?
Yeah. The point is that there are efforts also in this direction of using polymerized ionic liquid. The point is that the conductivity goes down substantially, and also the lithium mobility is not that high. Okay, so not only you're losing conductivity, but you lose also in transference number. So it's borderline, but there is still a lot of chemistry to be explored. Okay, I remember a few years ago we could never get a cell cycling at room temperature with like 9 milligrams of active material per square centimeter. Now we can. So there is space for improvements. Okay.
Okay, a final question. I think this is you can answer easily. This: what is the best way to synthesize a stable lithium-rich manganese, lithium-manganese-rich active material? Obviously, this is not related to the synthesis. It's basically what is happening once you make the material.
Exactly. Yeah, there are many different approaches. We don't really work much on the synthesis. What we are doing, we are working more on what happens at the interface during the life of the active material, rather than try to make a stable forever lithium-rich or nickel-rich material. Okay.
Yeah. Good. Well, thank you, Stefano. I think you can stay put because we will have an interesting discussion after this. Again, I would like to,
I'm trying to stop sharing. Yeah.
Yes. So as I say to the audience, please ask general question for the panel discussion. It is again an opportunity to discuss all aspects of batteries, not just today's topics, which is electrolyte, but cathode, anode, electrolyte, solid state, lithium air, lithium sulfur, whatever. I think we can cover all between the speakers and myself. Okay. All right. So it gives me a great pleasure to introduce my friend Shakir. I know him for his time at Enodel. Shakir, he's an expert in all solid state battery, Renault. So this presentation is from the OEM. He received his PhD in 2003 from the University of Casablanca, and then he did a postdoc in Bordeaux. And after that, he joined Enodel in the United States as a scientist and engineer, working on real world, which is lithium ion. I remember LTU as well. After that, he returned back to Renault to join the solid state battery program. And he will be, can you share your presentation, Shakir?
Yeah, good morning. Good morning, Mr. Khalid.
Yeah. So he will be talking about slurry coating process, effect of solid electrolyte purity on the fabrication of all battery.
Right. Just a few seconds. Okay, this one. You can see my screen?
No, we don't see that at the moment. No, okay, hold on, let me see.
No? Okay. Maybe I have a lot of slides, a lot of files.
No, it's something wrong with my computer because I don't see your, I see crystal clear audio. I don't know what that means. What did you do, Stefano? Learn more about it.
I am out, right? I'm no longer sharing, I think.
Okay.
It's okay.
No.
Yeah, so Shakir, please try to share the PPT. Not the screen.
Okay, now I guess.
Yeah. You share with us your screen.
I cannot hear you.
Yeah, there is a problem here. Okay, well, please bear with us. I think we will fix it. The other things, okay. Okay, I can see now. Good, excellent. You can put it on a presentation mode, maybe. Yeah, he's gone.
You can.
No, I think it come in and then he's gone.
You can see my
no,
screen.
It goes for a brief time. I saw your screen, but then it's no more there.
Okay, it's working or not? Because I cannot hear you.
Maybe one thing you can do is you can disconnect and connect back.
Yeah.
Can you do that, maybe?
Okay. Let me do that.
Just disconnect and connect back and see how it goes, huh? Again, my apology for this little technical problem. I think we'll definitely resolve it and look forward to hear some exciting work from Renault and their perspective on solid state battery, which is very hot topics now in pretty much everywhere.
Yeah.
So I think he's logging in again. So just give him a few minutes. As I said, we have only 2 speakers, so we have plenty of time.
May I ask Professor Stefano?
Yeah, please go ahead. Yeah,
Yes.
while waiting for
As usual, we learn a lot of things from Professor Stefano, and my question about the anion FSI and TFSI. So here, in the ionic liquid, you select the FSI, and then you selected TFSI in the salt. So there is some combination between them, FSI, TFSI, FSI, FSI, especially
Yes.
FSI is little expensive compared to TFSI.
Yes, I mean, mixture are very important. And actually, we know this, but only by trial since many years, okay? So having about 10-20% of, I see Mohammed is back, 10-20% of TFSI and ion makes everything working better. And actually, but this is usually more on the lithium metal. Okay.
Perfect. So I think we can continue this discussion at the panel discussion, and I can see the screen. Don't do anything. Check it. Oh, what happened again? We just seen your screen and then it's gone again. I think
it's okay. No.
Shakir, you share your screen, not the PPT file.
No, share the PPT.
Share the PPT. Yes, not the screen.
Yeah, that's the trick. You have to share the PowerPoint, not the screen.
The PPT
because...
It's okay.
Click on
If
your
he share the screen, he can switch to the PPT file. Maybe he used an external camera.
Yeah, I think you did at one point. Look at the PowerPoint. Yes, click on there and then find the presentation and click on it. You have too many presentation in maybe the one on the right, totally on the right. Yeah.
Yeah, sorry, see it again, Mr. Kelly. I don't hear anything.
You can hear us? Can you hear us now? Yeah, I think there is a problem.
Now, yes.
Yeah, okay. So what you do is you share your presentation, not your screen. Just say share screen and then go to presentation and click on it.
That's right.
Yeah, that's what you need to do.
Okay.
Yeah. Just go to your presentation and click on your presentation and it will come out.
Yes.
Can you share the screen with me so I can see what's
Yes, exactly what I am. Yeah, I'm sharing screen.
No, not okay. You click on share screen.
Okay.
Open your presentation and then click on share screen.
Now it's okay.
Okay, good. Don't do anything else. Just go to the presentation mode now.
Yeah.
All right. Good.
Yeah,
good.
I'm sharing the screen. This is the problem. I have to share just the file.
Yeah, the file. Yes, that's what you need to do. Now, good. Now we can see your presentation. Can you go to the presentation mode so you can have a bigger? Yeah.
Right. Okay. Thank you. Let's move. Now
Excellent.
It's okay.
Perfect.
Should be okay.
All right. So now again, the floor is yours, Shakir. Go ahead.
Okay. Thank you. Thank you. I'm sorry. Yeah. Thank you, Mr. Khalid, for your introduction, and thank you also, organizer committee, for the invitation, of course, to discuss with you during this conference. My talk will be related to all-solid-state battery with more focus on solid electrolyte, especially electrolyte, and its stability in weight process using solvent. Okay, as content, of course, I will start with a small introduction. I will talk a little bit about solid-state battery, and the focus will be on electrolyte, solid electrolyte synthesis, and some characterization, and in aim to talk about and to understand why the stability of electrolyte in wet process coating within solvent, especially ethanol solvent. And I will conclude by summarizing what I will share with you. Okay, let me first talk about Rono, of course. Just here one small slide. Renault, today Renault Group includes many brands, as you can see here. Okay. Renault, of course, Dasha, you know that, Samsung in Korea, South Korea, Alpine for more sport car, and also Lada in Russia. And also we work with Mitsubishi and Nissan in alliance. Okay, this slide, the idea is just to show you how our energy, especially the pack energy, is moving from the first generation to the last one. Here we are using, I am talking about EV car named Zoe. Of course, is our best seller car. Of course, is our first car. Here we start from this pack with 22 kilowatt hour as energy density in 2012, and now today we are using this one, using the same casing, the same volume, just optimizing the chemistry inside the pack and also some engineering, and the energy density was increased from 2012 to 2019 up to more than 136%. This is more important. Just if we take a look at the market, our competitors, of course, the same energy density or autonomy progress is also shown, as you can see on this slide. And the question today is: did we reach the limit of the limit capability of conventional lithium-ion battery in terms of energy density or not? To answer to this question, here I am just going back to cell energy density in terms of watt-hour per liter, of course, because it's more important for car makers, not only gravimetric one, but volumetric energy density. Here I am comparing, for example, the energy density at cell level, of course, from 1990 to today. During this last 25 years, this energy is increasing 3 times, as you can see. But today we reach the limit in terms of what we can do. Of course, Stefan will talk about high capacity materials, but we know the problems, as we discussed a little bit about it. And we think in this way to go up, or to increase more this energy density, we have to go to the next generation of batteries. Here I'm talking about, for example, also solid-state batteries. In terms of calculation, as you can see here, we can reach more than 1,000 watt-hour per liter. Of course, this is kind of calculation using or combining different things like using lithium metal or and also some high capacity cathode materials. Let me just, okay, sorry. Yes, talking about solid-state battery, the first question is, what is solid-state battery? Yeah, it's simple for more people. We just replacing in conventional lithium-ion battery. For example, here on the left, we are replacing the liquid electrolyte, both liquid electrolyte and separator by solid electrolyte. That's why here everything is green everywhere. Meaning, for example, in cathode side, in anode side, and also in separator part. And solid electrolyte is here we can call it catholyte, and in anode side is anolyte. The possibility to use, for example, as I mentioned before, the lithium metal is the main say advantage of this new technology. Not only the lithium metal, because for example, you know also that cathode materials named also 5-volt family or LNMO spinel materials. We cannot use it today because the stability of electrolyte, liquid electrolyte, I mean, it's not there. That's why, okay, we know these materials long time ago, but we cannot use it today. and we think using solid state battery or solid electrolyte, the door will be open to the application of this kind of materials, which belongs also to the cobalt-free materials or family. In terms of solid electrolyte, different candidates today exist. Of course, there is inorganic one and organic one. In organic family, we can talk about sulfide family, oxide family. Here I put some advantage and also disadvantage of each kind of solid electrolyte, and also we can combine, for example, oxide and sulfide or oxide polymer, or we can combine different families. This is the literature and what we have today. But okay, in the lab we can use this kind of electrolyte, but in terms of application, we have to think about many things. For example, the stability, the practicity, let's say, because the process is the big issue for this kind of use. The use of this kind of materials, especially oxide and sulfide. I talk about the practicity, but I have to talk also about the cost and also the performance. Here I am talking about ionic conductivity at different temperature, without forgetting the stability. This is also a big issue in application. Yeah, what is the ideal solid electrolyte? Okay, here I tried to combine or the requirements of solid electrolyte. For example, the conductivity, of course, I talk about different families, but in terms of conductivity, if I take oxide one, the conductivity is around 1 millisiemens, but compared to liquid electrolyte, which showed almost 10 millisiemens per centimeter. That's why we have to think about the conductivity, stability, of course, stability, chemical, thermal stability, electrochemical stability. Also, in order to use different materials, nickel-rich or 5-volt family, mechanical also properties, without forgetting also the practicity, which is related to the cost. Here I am talking especially about the process. And if we combine everything, our ideal solid electrolyte should be here. In the literature, of course, if we talk about one point here, ionic conductivity, a lot of families, solid electrolyte families exist already, and here just an example. And two promising candidates are available today. I'm talking about sulfide and oxide, especially Garnet family. The conductivity is here. For example, for this sulfide, especially LGPS material, the conductivity is huge. It's at room temperature, which is around here, 3.4, somewhere here. The conductivity is higher than liquid electrolyte, but conductivity is necessary, but it's not sufficient, of course. Why? Because this kind of issues here, this slide, it's from this reference, summarize different challenges to overcome if we need to use this kind of electrolyte in also this battery. For example, here, interface stability versus lithium or versus active materials, of course, dendrite management, as you can see here, and also the big problem related to the pressure, the process, how to make the tin, for example, tin separator with this electrolyte, the pressure, because we have to apply a huge pressure to keep everything with good contact inside the cell. According to what I mentioned before, and this lot of challenges, we think that the choice of solid electrolyte is crucial for next generation solid state battery. Okay, in this study, I have to discuss about one composition, which is argyrodite solid electrolyte with this chemical composition, Li6P5Cl. This study belongs to PhD program in collaboration with French lab LRCS. We just published this study in Solid State Science. Okay, sulfide electrolyte, as I mentioned before, there is a lot of families here. The more interesting one, it's a LPS system, AGPS, as I said before, and also argyrodite. In terms of conductivity, LGPS is more interesting one, but the germanium is very, very high, very expensive material. That's why for commercial application, it's not the good choice. That's why in this PhD program, the choice was argyrodite family. The conductivity it's acceptable around 1 millisiemens, and also the synthesis of this material it's fast and it's easy. Only ball milling, sometimes with or without aniline step. Okay. I talked also already about the synthesis here. For example, different ways can be used to get these materials. We can ball milling. We can synthesis, solid state synthesis, or liquid or co-precipitation one. As I said already, okay, with and without heat treatments, we can get this material. Okay, the conductivity, it's around 1 millisiemens usually, but this ionic conductivity, it's related to the structure, of course. Usually in this kind of material, the structure is more important. But we can play with for example, the vacancy in the structure to increase or to decrease the conductivity, also by substitution of some element with other cells, sulfur by chlor, or for example, phosphorus by germanium. We can get different composition with different properties in terms of ionic conductivity, of course. Yeah, an example of what I am seeing here. This study is our study, and this one is from the literature. Here, for example, just changing the composition, as you can see here, we can increase the conductivity from around 2 millisiemens to 10 millisiemens, according to the substitution ratio in this composition. Here, in the left, I am showing the heat treatment effect after ball milling. Without ball milling, as you can see, whatever the composition, the conductivity is very low. But after heat treatment, for example, at 450 degrees C, we can increase the conductivity, of course, and also it depends on the composition, as you can see. Okay. The first step, of course, in this thesis was the synthesis of this material. We start with 1 gram, just lab scale, argyrodite synthesis, the condition as you can see here, and we check the purity, of course, of our material by XRD and Raman analysis, and these techniques confirm, as you can see here, the presence of argyrodite. The main phase is argyrodite, as you can see, with small impurities in the materials. But for our process, we need more high quantity, let's say high quantity of material. That's why the next step was to increase the quantity from 1 gram to 100 gram. And during this study also, because we are talking about high quantity, we buy, of course, another two grades And the idea is to compare the performance of our grade versus commercial one. Here the ECM of different materials. Okay, EBM is just it's here. Okay, I put 100-gram materials. The batch, this batch, just after ball milling, this one. After heat treatment, 5 hours at 550 degrees C, and commercial grades from MCRAN, Japan, and the NEI. Okay, 4 samples. The study, as I mentioned before, the goal of the study is to check the relation and to understand the relationship between the material purity and conductivity, and also electrochemical stability of each material. The first step here we compare the XRD characterization of different samples, our samples, EBM and E, and commercial samples. As you can see here, in terms of crystallographic point of view, the ACL parameters is it's in the same way. It's comparable, let's say. In terms of crystallite size of crystallite is different, of course, because with and without heat treatment can make a big difference. For commercial one, we don't know anything about the synthesis method and also what happened after the heat synthesis. That's why, okay, here we have only this data, but we cannot go in deep understanding this commercial grade, of course. Yeah, the first result here, as you can see, the BNEI is pure. Here, pure material. But in our material EBM, just after ball milling, we still have Li2S and LiCl precursors. But these precursors we can reduce the ratio after heat treatment. Here we call the sample A. Okay. In terms of Raman spectroscopy characterization, what is important here is in ABM sample with XRD we cannot see, for example, the presence of this species, but in Raman we can see it. This is the first surprising result for us. But for others, we can see the presence of pure geodite, let's say, vibration of PS4 3-. Okay, in NEI, we also show the presence of S8 impurity. Okay, according to these results, we check also after this characterization, we check the ionic conductivity of different materials, and this table will compare it, as you can see, at room temperature around 20 degrees C. The commercial BNEI, the commercial NEI sample, which is pure in terms of XRD, present the higher activation energy, as you can see here. High activation energy, meaning low ionic conductivity, of course. And the second observation is the conductivity increase with the heat treatment. From our EBM to E after treatment, ball milling here after 550 degrees C calcination. The last sample from Amsera presents high energy, high conductivity, and the question is why this one presents this conductivity. The question is the conductivity is related to purity or not. Okay, here just I summarize everything: XRD characteristic results, Raman results, ionic conductivity. High ionic conductivity is related maybe to the purity. Okay, if we think about this one, yeah, small Li2S content, but in Raman it's pure. Maybe that's why the conductivity is higher. we try, according to this result, we try to synthesize pure argyrodite without heat treatment. For this, what we do is to change the method, and we use Li4P2S7. Observe what we observe by Raman characterization. We use this one, and the reaction, as you can see here, the result is surprising because okay, the sample here we call it CBM. The result, why is surprising? If you can see here, there is no impurity compared to other one. The first one we use LiCl and Li2S starting materials. Okay, here is some comparison in terms of EC parameters, cell parameters. In terms of conductivity, both materials was prepared by ball milling without heat treatment, but the purity is different, and this results is affect, of course, the conductivity. The Raman spectroscopy showed no absence of Li4P2S5, and we get high conductivity. And now, what is the electrical stability response of this material? Here, okay, the slide is a little bit full, but what is important here is the comparison of the oxidation part and the reduction part of different materials. As you can see here, for oxidation, we get low capacity, even at up to 4 volt, meaning that there is limited degradation of these different materials, the oxidation part, but in the reduction part, we get different results, and different results, and also large capacity. Theoretical capacity, as you can see, is around 460 milliamps per gram, but in our side we get less. And the stability or electrical stability windows for the argyrodite is as you can see here, between 0.8 to 2.7 volts versus lithium. The question, okay, we have some results, but it's not. I will not share today about the understanding what happened. For example, at different using different cathode materials. Meaning the interface between the oxidation, meaning the interface between solid electrolyte and active materials. It's another study, but I will not share today. Okay, the target for this talk is the wet process, and how the argyrodite is the behavior the argyrodite in this media. Okay, the idea or the approach is it's simple. Just the first step is dissolution of solid electrolyte in the solvent. Here we are using ethanol, and the idea behind this is to try to coat active materials particles with solid electrolyte. Of course, after drying everything, and then we add, for example, carbon and the binder in order to make slurry or to make electrode. What we get is the problem is after drying the electrode, the crystallization of argyrodite is at low temperatures. It's more difficult. But before to talk about the electrode itself, we investigate more what happened for solid electrolyte, argyrodite. I mean argyrodite after dissolution and also after drying at around 40 degrees C. Here we are comparing XRD results for two samples. Okay, here ABM is our sample after ball milling, and BMCR, it's a commercial one. The first step is dissolution in ethanol and evaporation at 40 degrees C, as I mentioned before. We get other samples named here, just the name E2, B2, and another step just to check if we still have archaeotite structure after drying at high temperature. Under vacuum also, of course, and we get E3 and B3 samples. Okay, to make it simple, here, okay, we have XRD for the initial ABM material. It's our material, of course, with impurity. You remember, this one is not pure. After dissolution and drying at 40 degrees, we still have archaeotite structure. And after 100 degrees C, of course, we still have, we maintain the structure of archaeotite. But what is surprising is for the commercial BM Sera, here the XRD for initial material, after its dissolution and drying at 40 degrees C, we lose the structure of archaeotite. And even at 100 degrees C, 150 degrees C, we still not have the archaeotite structure. Okay, the question is, what happened in this step? What happened in this step of dissolution of this archaeotite? Because this step is more important, is very important for a wet process coating. That's why we try to understand what is happening during this step. And also the next question is even we start from archaeotite and we lose the structure, the conductivity is still here or not? Okay, before to show the conductivity results, this is the Raman spectroscopy characterization of different materials. It's exactly the same as previous slide. Here on the left we have ABM, and on the right we have a commercial sample. The Raman spectroscopy before dissolution, after dissolution and drying at different temperature, we still have the same thing. And this result confirm what we get from XRD analysis, as you can see. But for this one, what we show here is the presence of new elements, especially at this part, which is related to thiol species. Of course, for Raman spectroscopy, we still have archaeotite, according to this band, not in XRD. Okay. Yeah, sorry, I forget that we do also NMR characterization for commercial grade for our materials. What we saw is for we have kind of decomposition of commercial grade. As you can see, there's a lot of peaks related to lithium, meaning that we have other phases containing the lithium. But for our sample, we still have the same let's say the same environment of lithium. Here's some TGA, but TGA analysis. What we can see in the beginning, it's kind of organic species evaporation at around 100 degrees C, but we still have some peaks. Right now, we try to understand these peaks to index these peaks. Right now, it's not finished yet, the study. Okay, this just summarizing what I showed before, but it's not more important. Now, yeah, sorry, I lost something. So let me go back. There is no conductivity. Something happened. Sorry. Okay, the previous results from the previous results, we get some hypotheses. The first one, why do our materials, not pure materials, the materials after just ball milling, is conductive? The conductivity is still good, still conducting even after evaporation, after dissolution and evaporation. The commercial one is not conductive. the question is why this material with initial impurity is good. And to confirm this, the idea is to add these impurities to pure argyrodite and do the solution and drying. That's why, okay, we took OMSIRA sample and we add 10% of P2S5 and 10% of Li4 P2S7, the impurity that we have and we detect by Raman spectroscopy in our sample. Okay, the result is here. Of course, the initial spectra is without dissolution, and here after dissolution. The result is surprising because when we add the impurities, we get the, as you can see here by the triangle here, we maintain the argyrodite structure after dissolution and drain at 40 degrees C for both, as you can see, for both, meaning for two different impurities. And the next question is with this mixture adding impurities, we can keep the ionic conductivity after dissolution and drying. Okay, the result is here. We are comparing the different conductivity of different materials. The four materials are ball milling, OMSIRA plus Li4 P2S7 and OMSIRA plus P2S5. Of course, the conductivity is comparable, let's say. And we dissolve and we dry these materials. Pure OMSIRA, the conductivity is bad. And after adding these impurities, we increase the conductivity. Okay, I put here clear improvement of conductivity thanks to additives. Okay, this is the result that we get. In conclusion, argyrodite electrolyte was prepared, of course, at different scales. But the main message is adding impurity in commercial grade can protect the structure of argyrodite, and we can improve the conductivity after dissolution or after, for example, with process coating. And these results we get patent for this. And now, in terms of mechanism, we try to understand also. We still have some experiment to do because the mechanism, to be honest, it's not yet clear, but we have some idea about it. Okay, I need to thank my PhD students, Xavier, and also my colleagues from IRSEC', Mathieu and Virginie, for this collaboration. Thank you.
All right, thank you very much, Shakir. Very interesting talk, and how the impurities can improve the conductivity. That's pretty new to me. Yes, so I think what we're going to do is we're going to blend the questions as part of the plenary session, So I would like to invite Stefano, Moad, and Shakir, and who, all the students who are participating as well to this discussion. So we're going to start by asking, if there are any questions for the speakers from the audience, and eventually we will start a general discussion. As I say, this discussion, I know the time is really short, we don't have much time, is not only on electrolyte, but also on any topics within the battery. So anyone who has questions, either he's doing something in his research and has some question, this is an opportunity to ask. So let's start first with the audience for question for Shakir. I have two questions so far. The first one is how the preparation temperature of the solid electrolyte can affect the interdiffusion between the electrodes and the electrolyte. This is a little tricky because you prepare the electrolyte totally separately from the electrode.
Right.
Remember, you have, yeah.
Yeah, this is the answer. We separate. Of course, we have another topic, but it's not this electrolyte. I used LZO garnet electrolyte, and we try to understand the question, of course, what is the stability at high temperature? Because for this, okay, here I am talking about with process, but for other topic, it is you. For example, if we just high press with high pressure with at high temperature, for example, SPS. And the answer is the active material is not stable. We try with LNMO, NMC, LMO, decomposition of these materials at around 700 degrees C. But the surprise was LCO is more stable. But you know, we don't need LCO now for for our application.
It's interesting. I think maybe there are some reaction at high temperature, obviously, between the two. Yeah. Okay, so that's the answer. The other question from Jamal, he would like to ask you about the sample ABM. In the Raman spectra, there is the presence of two groups, PS4-3 and P2S74. My question is how these two functions can affect the electrochemical performance of your solid-state electrolyte.
Yeah, no big effect on conductivity, because you know the ionic conductivity depends on the structure. The main structure of the materials are geodite, and others is just kind of impurities. There is no big effect on this.
Yeah, another question from Yusra. Basically is asking if your solid electrolyte, is it possible to obtain this solid electrolyte using only conventional manual grinding, or maybe using acetylene during the process at the lab scale?
Yeah, we can even just manual grinding. It's okay. Yeah,
I see. Okay, so these are the questions from the audience. I didn't see any general question from them, but we're gonna ask question. You know, obviously, Stefano, you can step in and ask any question. I actually have one question which is really important. Conductivity is important. You know, some of the solid electrolyte has even higher conductivity than liquid electrolyte, as you know. The biggest problem is manufacturability. How you can make pinhole, zero pinhole, no grain boundaries. You know, film that can be used as a separator. That's a huge challenge, because some of the work's been done at Argonne and others shows that you can have dendrite actually going through the pinholes and even through the grain boundaries, and eventually you end up with a short, and the battery diet may not have a safety issue because solid electrolyte is fairly robust and stable, but it will kill your battery. So are you or Stefano, this is also for you. Do you guys are working on this? What are the, you know, the possibility of overcoming these major issues? My thinking is you can go to glass, but most of the glass doesn't have a great conductivity. So that's an open question to the audience and to the speakers.
Yeah. I talk about ELZO. The first target of this study of ELZO is to stop the dendrite growing, because you know that's why we choose ELZO, because it's stable. We try to make it to make pellets. What we do, we make pellets, and after centering at high temperature around for example 1000, we decrease the green boundary, of course, because the dendrite is growing between particles. And even with this, what we found that even the dendrite sometimes it's growing inside the particle. We don't know why, and this is a big issue. That's why I am talking about this just to say that even with glass, maybe it's not the good solution today. And I think the solution is to check to find another mechanism to make the morphology of your dendrite different than what we have today, because you know the dendrite is going down to up. But if you have maybe with kind of chemical other chemicals in your cell, you can form your dendrite kind of with different morphology, and you can go in two directions, not just only in Z direction. And okay, there is startups in Boston area, okay, showing this kind of proposal. I think we have to think about it, because I think it's a good solution, because you don't try is here.
Yes, yeah, I think it's a good. There are actually some work that's being done using additives to create more of like a spherical shape, or round edge shape. That can maybe a potential solution, as you mentioned. It's a good idea. Stefano, you want to add to that, or?
Yeah. I mean, okay. We have proposed these interlayers between the solid electrolyte and the electrode interfaces to kind of minimize the problem of dendrites, and also to solve the problem of pressure. So if you have these kind of interlayers, soft interlayers, then you don't really need to apply much pressure to the cell anymore. But actually, I have also experienced in a rather different system, and so this is why I still have hope. And maybe you didn't hear about it, but these are the sodium seawater batteries, in which we have nasigon in the middle, obviously to separate sodium from seawater. And in this case, we can grow, for example, sodium metal on one side, and we never experienced sodium dendrites growing through this nasigon-based material. And also, there are no pinoles, because otherwise the water would move into the sodium. So I'm not making these electrolytes. I'm getting this from my Korean friend at UNIST, but they are clearly capable of getting 100% pinole-free solid-state electrolytes. And I don't know how they do exactly. They never disclosed this to me, but clearly this helps. Maybe for the solid electrolyte, especially LLZO, I mean, we are going too much toward perfectly crystalline materials, rather than try to glue well together the crystallites. Okay, so this is a feeling. As I said, we are not specialists in synthesize compact layers, but I know for sure that somebody can do, because we can make this solid seawater cells.
So how about a hybrid system? Sorry, go ahead.
Yeah, hybrid system, I think right now I'm just correcting another manuscript. So this was my work before the meeting of a student. We are definitely hybridizing systems in order to get the best from everything. At the very end, if you think about a lithium-ion battery, is a very hybrid system. I mean, if you don't get the right SCI, it's not going to work. Okay, and what we have to do now, we have to find the equivalent but opposite SCI in a sense, right? So in a conventional lithium-ion battery, we have a liquid electrolyte. We know that this liquid electrolyte is not going to be stable with the electrodes, but we get the right SCI in the middle. And right now we need to do the opposite. So we have a solid electrolyte, and we need to get the right layer between the electrodes and the solid electrolyte.
Now I was thinking of a hybrid system polymer. Solid side. So because you can easily process for manufacturability, that's something that is interesting to look at as well. The only problem is you don't have too many polymers that are stable at high voltage. The PU, which is the commercialized one, can operate using LFP maybe, but beside that, you don't have any others that are really exciting that can be considered. Okay, so we have a question from Akil. This is for you, Stefano. He said, please comment on the effect of ionic liquid cation group, and what are the criteria to select a good electrolyte, ionic liquid electrolyte?
The cation group can be important. I mean, it depends. It is very much related with the thermal decomposition, especially, okay? Because this is the, let's say, weaker component from the thermal point of view. So, for example, if you want to go to high temperature, then you have to use phosphonium cations rather than pyrrolidinium. On the other end, you always need to balance everything. It's a rather complicated system. Okay.
I see. Yeah, this question is from Yusra. She's talking about the use of monocrystals, solid state, would be help to reduce the lithium dendrite growth between the grain boundaries.
Yeah.
So
yeah. Stefano talk about it, and people also talk about this. Single crystal, but it's on the paper it's easy, but how?
Yeah, but even though you'll have grain boundaries between, well, you're right, because you have a single crystal,
Right.
so you don't have any big boundaries. But when you combine the powder together, you'll create interfaces and gap for the dendrite too. I really think the idea of shaping the dendrite in a way that are using like Syria, these one additives that PNNL have done, that shows that the morphology of the dendrite changed completely using this additive, and that could be actually the solution to preventing the dendrite. There is another very active Akil when it comes to question. He said recently some companies are working on anode-free lithium-ion battery using solid-state electrolyte to improve the energy density, obviously. Could you comment on this one? Is that something that is could be there?
I think he's talking about Samsung. I know this paper, and I studied this paper because the concept is very, very interesting, and the reach 1000 cycle life at room temperature. We think about it because we don't need lithium in anode, but as Stefano said, we have to manage the interface between lithium or just current corrector and solid electrolyte. This is the key. And in this paper, I don't know if we are talking about the same paper. And the idea is to use mixture of, for example, of carbon and silver. And during charge, the lithium goes to the anode side, not as the lithium, but as alloy. The lithium form alloy with silver. That's why you don't have dendrite, but you have, the mechanism is different than what we have if we just only do lithium. And the idea is very good, and I said before, the results are very, very good.
So just to follow up on what Stefano mentioned about the sodium ion conductor with your friends in Korea. We don't know what are the sodium dendrite is not as well studied as lithium, so maybe there is something there that may have helped. But a general question is, there are more opportunities on material side on a sodium ion conductor than on a lithium ion conductor, as you know. Nasicons, for example, are very attractive. We don't see much of that in lithium. So can you comment on the prospect of solid electrolyte for sodium battery? This question comes from Abdul Wahid Shari. So I think it's a very relevant question about maybe enabling high energy sodium ion using solid state electrolyte with the anode free, for instance.
It's for me.
Yes, for you or for the audience. For the everyone.
I mean, we are working with solid electrode for sodium-ion batteries. I mentioned this Nasicon material, which is very interesting, but the conductivity is not as high as the solid electrolytes, the best solid electrolytes for lithium, okay? So you really need to go extremely thin. But for sure, as I said, it is possible to get 100% phenol-free layers. We are also working on polymer electrolyte-based sodium ion for sodium ion, and again, it's interesting. But dendrites for sodium, to the best of my experience, dendrites with the sodium metal electrodes are growing even faster than for lithium. So it is even more challenging to make a dendrite-free or to get dendrite-free cycling out of sodium metal with polymer electrolytes or liquid electrolytes.
I see. I was thinking of like the morphology of the dendrite. That's very critical. Are they needle type? like the one we observe in lithium. That's my morphology is different. Then you can overcome the issue of potential short using dendrite.
Well, let's say that most of our, for sure, there is a huge formation of like sodium dust, let's say. So very frequently, if you replace the sodium metal electrode in a cell, then your cell starts working again pretty well, okay?
Yeah.
But many cells tend to short circuit for dendrite formation.
Yeah, no, I'm going to switch to have a general questions. I don't see any, so I'm going to step up and ask. This is an interesting question. We know that the biggest challenge, is the cost in the battery, and way to address it is to increase the energy. So unfortunately, most of the material on the cathode side, at least, that shows very high energy at high voltage are cobalt and nickel based. Sivan will touch on at least an interesting material, which is a manganese based. But there is also a path of fast charging that is happening, and there are a lot of progress at the moment, using, for example, I think Porsche has actually announced that they can fast charge in 15 minutes. Recently, Ford, in collaboration with one of these universities in Indiana, they created a fast charge where they can fast within 5 minutes. So if that is happening, I mean, I think the LFP could be a better choice for electrification, especially electric vehicle. If you can charge, at the moment you can achieve maybe 180 miles with the LFP. If you charge one time, you get 360. It's cheaper, it's sustainable, and it can last longer because it has great calendar life. So what do you think about these two parallel paths? High energy, there is an impact of cost and sustainability, and safety, versus medium energy with sustainable material and fast charge.
The question for me?
For whoever. You go ahead. You are in the industry. I'm pretty sure you did the study.
Yeah, there is, maybe before to answer to your question, talking about, for example, Porsche or other car. When we talk about 15 minutes or 10 minutes, we have to think about what is behind this time, because the battery is huge. For example, if you have 100 or 150 kilowatt hour, okay, when you talk about 15 or 10 minutes, the people are talking about, for example, you talk about, I don't know, 100 miles or 150 miles. Of course, in 10 minutes, you can charge this autonomy, or this, because the battery is huge. You don't charge 100% of the battery, but you charge only 50% or 40% of the battery. You know that, because the voltage, the limit is the voltage from 0 to 50%. You can charge by, for example, 3C, 4C, or 5C, no problem. But at 50%, you have the big problem, which is the voltage limitation. You polarize, you get, and you have some polarization. That's why you cannot go more. If your battery, the pack is very huge, of course, you still have a lot. You can charge 10 minutes for the people, customer. Okay, they are happy because you can go for 200 to 150 miles. That's it.
Yeah, what I'm referring to is we're talking about the conventional system now, which is NMC or NCA. I agree with you, but if you move into LFP, the situation change. You don't need to go to 100 kilowatt hour. You can go to 80 or 70. That material are known to charge with the very limited impact on life, pretty fast, huh? Yeah, so that's why I'm saying the people are trying to stay away from nickel and cobalt base to an iron base, and there is tremendous amount of news, like Tesla is using it now. Some other companies in China are basically dominating it because of this capability of fast charge. And when I talk about the fast charge of Ford, they actually create a system where they can cool the cables during the fast charge very quickly. That's the technology that they come up with. Yeah. which is actually very, yeah. So I think my feeling is that there is a good chance for this concept to take over.
Yes, I agree with you, but okay, it's kind of economy. Yeah. You know that LFP, we cannot use LFP in Europe because we have, Stefano talk about it, okay, in regulation, whatever. We have to recycle LFP, but it's, we need a lot of money to recycle. LFP is cheaper. That's why in China, the big markets of LFP is in China. They don't care about recycling LFP.
So what is the issue of recycling of LFP? I mean, you don't need to recycle it. Phosphates are abundant everywhere. Morocco is the largest.
But the cost.
Iron is everywhere.
We have to reduce the cost. Yeah, for us, it's, we have to pay to recycle the LFP packs. That's what,
So in Europe, you must recycle anything you produce.
Right,
okay.
Everything.
Or you can send it to China to be recycled. You don't have to do it in Europe.
We have to prove that we are recycling. I mentioned that the regulation in Europe are extremely strict, so it's going to be a big problem in a few years, actually.
Yeah. So talking about recycling, Stefano and Shakir, can you comment on the activity of recycling? What kind of concept they use? I know there are at least 3 concepts: regenerating the cathode without decomposing it, for instance. So it's like a treatment. There is also the full recovery of the metals like cobalt or nickel. I know that Europe, because of this strict requirement, I'm pretty sure companies in Europe are, especially in Germany, actually, is a tremendous amount of activity on recycling. You want to comment on that, Stefano?
Yeah, recycling is growing. Actually, I'm collaborating with a couple of institutes in Europe, one in Germany, one in France, and we are recycling the graphite anode, to give you an idea, because this is going to be the future. I mean, you cannot trash anything. I mean, one of the concerns they have in the European Union, the Commission, is actually how to recycle the separator. I mean, it's really crazy, okay? And we are working on graphite. For example, graphite is not too bad. Actually, we can recycle about 85% of graphite with like 98% of the performance of the pristine one. So this is also possible. And if you recycle graphite, for example, as well as LFP as such, so without burning, then it can be also economically convenient. But I mean, this is demonstrated at the lab level. We can do it now. It needs to be scaled up to the large scale.
Yeah, well, in the US, a business that does not make sense, people don't touch it. Recycling materials that are abundant is going to be costly and nobody will buy them. So I'm actually very surprised that the European Union is putting this strict requirement for recycling everything, because very few people will get into the recycling business if they don't make money. Obviously, if you recycle nickel or cobalt, you're going to make a lot of money because those are valuable commodity, and you understand the situation. Or your government has to subsidize the recycling, because honestly, recycling graphite, there is tons of graphite everywhere in the world, or recycling iron or phosphate, there are tons of them. So I don't see the economic advantage of doing that. But that's actually very surprising to me that the European Union is pushing all these companies that make batteries to recycle. They're going to be a major issue because it will add a lot of costs that they have to absorb.
Yeah, but this is the trend. I mean, we also want to get full decarbonized Europe in 30 years, 29 years, okay? So you can imagine, I mean, on the other end, we had some bad experiences. I don't know how you solved in the US, but for example, since a few years, China is not getting our plastic waste anymore. And in Europe, we have serious problems now because we cannot burn it, because we don't want to produce more CO2. And so, I mean, it's going to be a big problem. So it's clear that we cannot rely on China anymore for these things. And I think it's also correct. But we need to recycle. I mean, there is a big push that would be very soon, I think, be Shakira knows better than me, but I know that at the European Commission, they are working with all the battery companies and also the user of these batteries, and they are setting, very, very strict constraints, forcing recycling as the material as they are and not burning and just taking what is good.
Yeah, I think the reuse is the most important. Yeah, recycling, reusing the material by treatment, whatever. Maybe it's economically is attractive, and maybe that's where the Europeans should focus on. Yeah.
Because synthetic graphite, which is in the Panasonic cells, let's say, this is almost 20 euro per kilo. It's not that cheap, right? Then you can kind of consider that maybe it is economically convenient also to recycle graphite. This
Very
is
good. Okay, so is there any other questions from the? I don't see any question from the or discussion from the participant. So
maybe small question for Stefano.
Yeah, go ahead.
Regarding low temperature performance of liquid electrolyte, did you check if your system is working at low temperature?
In some configuration, I can work at like minus 10 degrees centigrade, which is also the limit of graphite, let's say. But still, we have to work on ionic liquids. We do not have the full solution yet, although I know that there are some companies getting more and more interested in. Okay.
Very good. Mohamed, do you have any questions?
Can I ask a question to Shakir, actually?
Yes, go ahead.
Because we are also working on the RG rhodite and similar electrolyte, and you show that actually in your process, you kind of dissolve the sulfuric electrolyte and then you recoat it on the cathode particles, right?
Right.
Which we are also doing. I mean, we are also dissolving the sulfuric electrolyte. But when you coat it, when we do coat on the cathode material, actually the cathode material gets completely isolated, so there are no electrons moving anymore. May I ask how you solve this problem?
Yeah, the problem is the porosity. This is the big problem because your electrolyte is the conductivity is still there, but
the ionic conductivity is okay. The problem is that we cannot get electrons into the active material.
No, just if you get less, because as I said, the K is the porosity. You have to reduce your porosity because when you coat, you get 50%. You know that.
Yeah.
But the idea is to go back to go down up to 0, but it's not possible. I know that, but
the minimum we got is 27%. So
but you need less. You need at least 5%. 5% it's working.
Okay.
Okay, Moad, you have to ask. I think you asked a question before.
One question about for Stefano about the kind of separator you use in your ionic liquid with your ionic liquid.
There are a few different, but just for the basic investigation, we just use a glass felt. But we can also use let's say a polyethylene or polyolefin separator. Okay.
And it is reported that we didn't indicate for ionic liquid, especially for fast charging. So we didn't observe any dendrite formation. Is that true?
You can forget about. What do you mean with fast charging?
It's like we charge it. We put a high current density with graphite with ionic liquid.
So you did.
Yeah, so from the literature, so they say that's about there is no dendrite formation with the ionic liquid at a high current density.
Yeah, because the high current density for the electrolyte, it is actually not very high for the electrode in most of the cases, okay? So the lithium mobility, the lithium is limited by the diffusion into the electrolyte, and not by the charge transfer at the electrode interface. You get the lithium metal dendrite on graphite when the limitation is on the charge transfer, right? From the electrolyte to the graphite particles.
Okay.
Okay, great. Excellent. So I think Shakir has one more. Yeah, let's
maybe
the
one
last
more
one.
question for Stefano. Sorry,
I forgot.
Yeah, the cost, yeah. Did you calculate, for example, if you replace a liquid electrolyte, I mean conventional one, by liquid ionic liquid, what happened? Because you know,
I mean the cost. He's talking about the cost.
Yeah, the cost. Yeah, I'm talking about the
cost goes up. I mean, definitely ionic liquids are more expensive right now than conventional electrolytes. Okay, and also than sulfidic electrolytes. Sulfidic electrolytes are also cheap. Okay.
Well, I would say I have a second answer to that, Stefano. If the ionic liquid can enable much higher energy, because you can go higher in voltage, you get much higher energy, the overall cost may go down.
Yes, sure.
Maybe you should do that calculation, because you're calculating only the cost of the ionic liquid, but the benefit of the energy is not included. So
yeah, this is actually the reason why we are keep going in this. Okay.
Okay.
Because it's also clear that the ionic liquids are not produced on a very large scale, so price reduction are still possible.
Okay. All right. Well, I think we come to we have a great discussion. We went over by 30 minutes because we have a glitch, but it was very animated. I really am very happy that we have this session. Now we come to the end of the keynote talks and the question and moderation. The next chair, my co-chair, Muad Dahbi, will take care of the short presentation from young students. I would actually recommend that Shakir and Stefano to stay, because it would be really nice to look at what they are doing and give some input. Unfortunately, I have a meeting at 15 minutes. I will stay for 15 minutes because I have a meeting with BMW that I cannot miss. But the folks at Muad will definitely take care of this session. Muad, the floor is yours.
Thank you, Mr. Khalid. So let's start the second part of the presentation given by students and PRC students. So the first presentation is given by Coach Khadija. So she's a Master 2 student, and her talk is about sol-gel synthesis of nanoparticles as anode material for lithium-ion batteries.
Hello everyone, I'm Khadija Kouchi. I recently graduated as a master's student in chemical engineer and material science at the Faculty of Sciences and Technologies of STAT. My presentation is entitled Sol-gel synthesis of nanoparticles nickel magnesium iron manganese oxide as anode material for lithium-ion batteries. As you know, lithium-ion batteries are an invention that has provided enormous benefits to society thanks to their high energy density, high operation voltage, and no memory effect. The initial challenge for lithium-ion batteries was to define a suitable cathode material facilitating the lithium intercalation disintercalation. But actually, huge interests have been oriented to the development of an anode material meeting the requirements of high energy density and high safety. Since their development, the anode market has been dominated by graphite. However, the graphite suffers from its limited theoretical capacity of 372 mAh per gram, which barely satisfies the needs of large-scale applications. And to overcome these limitations, the development of some alternatives is required. Here, the transition metal oxide are a promotion class of material, especially the nickel magnesium iron manganese oxide. Our spinel-based material was synthesized using a sol-gel method. Firstly, the following raw materials were mixed, then the citric acid that was used as a complexing agent was added into the solution. The mixture was stirred and heated up to 90 degrees C until the gel formation. The resulting residue was heated at 160 degrees C overnight and calcined at temperature between 250 and 800 degrees C. Now let's move to the characterization of our material. The X-ray diffraction pattern of the nickel magnesium iron manganese oxide material show us that the metal cations converts completely to pure spinel structure of the nickel magnesium iron manganese oxide material. The Raman spectroscopy was carried out to confirm the results of XRD analysis. The Raman spectra of our sample shows the presence of 6 vibration peaks, which could be attributed to the symmetric deformation, rotational and translational movements of the oxygen anion. Evaluated as anode material for lithium-ion batteries, the nickel magnesium iron manganese oxide displays interesting electrochemical performance. From the galvanostatic test and after 10 cycles, the electrode material can deliver a reversible capacities higher than 700 mAh per gram with a capacity retention of 83%. In order to understand the mechanism of this material, the voltammetry test was performed. This figure shows us the cathodic and anodic peaks at 0.66 and 1.9 volts respectively. Generally, the iron 3+ and manganese 3+ goes to their metallic form during the discharge. The peaks at 0.66 volts could be also attributed to oxide formation. In addition, no large difference in the position of anodic and cathodic peaks was noticed, suggesting similar kinetics open charge discharge. More than that, the material exhibits excellent rate capability performance. Where the current rate has been increased to the highest value, specific discharge and charge capacities higher than 500 mAh per gram have been obtained. In order to improve the stability of the material, the carbon coating process was done under argon atmosphere at 600 degrees C using sucrase as the carbon source. This slide shows two figures, the first one without coating and the second one with coating. With coating, the material are more stable and the capacity retention was increased to 100%. So we can conclude that the carbon coating stabilizes discharge charge capacities and give us excellent electrochemical performance. As a conclusion, this work consists of taking advantages from the electrochemical performance of the nanoparticles nickel, magnesium, iron manganese oxide and its use as anode material for lithium-ion batteries. So we have managed to obtain good electrochemical performance. Thank you for your attention.
Okay, now let's move to the second record video given by Hasna Karim. She is a third year PhD student, and she will present the performances of half-cell sodium vanadium phosphate, a half-cell in ionic liquid based hybrid electrolytes. Please, Mr. Youssef. Yeah, okay.
Our team of PhD students at the University Hassan II Casablanca, Morocco. In this presentation, we will talk about the performance of carbon-coated MPPT in ionic liquid hybrid electrolyte. So, compared to the lithium-ion battery, the sodium-ion battery is considered as an expensive alternative energy storage system due to the large abundance and low cost of sodium raw compared to lithium, their chemical property which is close to lithium, and also fast charging. The sodium-ion battery, in a simple way, is composed of an anode cathode separated by an electrolyte, where the electrolyte is the key element of good work of battery, which is responsible of sodium-ion mobility. Generally, the liquid electrolytes based of carbonate solvent are the most used due to their high ionic conductivity, low viscosity, electrochemical stability, and easy to prepare. But on the other hand, these electrolytes suffer from their high flammability, toxicity, and thermochemical instability, and their decomposition, which allow to form of unstable layer solid electrolytes interface onto the electrode, which reduce the safety and electrochemical performance of battery. So, as solution, some additive can be used. In our study, we have used ionic liquid as additive. So, what means ionic liquid? Ionic liquid are organic salts with omitted queen, below 100 degrees Celsius, and are composed of big organic cation, which is responsible of decrease of metal point, and inorganic or organic anion. And compared to the carbonate, ionic liquids are not flammable and thermal strong, and also show a no volatility property, and have a high electrochemical window with high ionic conductivity. In our city, we have synthesis or ionic liquid by two steps. The first step is based on alkylation reaction to obtain desert cation with halogenated anion. The second step is the metathese reaction, which allows to change the bromide anion with the hexafluorophosphoric anion to get a hydrophobic property. Then we prepared our electrolyte by mixing propylene carbonate with sodium PFSI salt, and we added 10% by weight of prepared ionic liquid. As expected, the prepared ionic liquid showed a good thermal stability and discharge decomposition at about 300 degrees Celsius, and compared to the propylene carbonate, the ionic liquid was unflammable. And when it was added to the net electrolyte, a significant increase in the thermal property of electrolyte have been observed. Then after, we prepared a coated carbon MVP by a Solgen method, and we studied its electrochemical behavior in the hybrid electrolyte based in ionic liquid and in the net electrolyte. So as we can see in the charge-discharge curve, the cathode have an excellent cycling performance in the ionic liquid electrolyte and exhibit a reversible first discharge capacity of 123, which was higher than this obtained for the net electrolyte. Also, the MVP cathode have exhibit a high Coulombic efficiency up to 90% and show a reversible capacity and cycling, stable cycling after 30 cycles, with the formation of large plateau between 323 volts and 325 volts, which correspond to the redox reaction of vanadium ion. So to investigate the reason of the increase of cycling performance in ionic liquid, non-impedance measurement was realized, as we can see that addition of 10% of ionic liquid to the net electrolyte have significantly decreased the real resistance of the net electrolyte, and that means that the ionic conductivity of electrolytes have been improved, which means that the mobility of sodium ion was increased by the presence of ion species of ionic liquid. So we conclude that addition just of 10% of ionic liquid have significantly increased the electrochemical property of the carbon-coated MVP half cell. And thank you for your attention.
Okay, so the audience are encouraged to put the question on the chat and discussion. So now we have the third speaker, Asma Kafeh. She's also third year, and she will discuss or present a new electrodeposit sodium vanadium phosphate materials as a cathode for high voltage sodium ion batteries.
Hello everyone, thank you for this opportunity to present my research work. My name is Asma Kafih. I'm a PhD student in Material Nanotechnologies and Environment Laboratory at Mohammed V University. The title of my today's presentation is a new electrodeposited sodium vanadium phosphate material as a cathode for high voltage sodium ion batteries. The outline of my presentation will begin with an introduction, then I will present the experimental approach, I will discuss the results, and finally we conclude. In recent years, the production of electric vehicles has been increasing rapidly due to high energy density offered by lithium-ion batteries, long cycle, lightweight, and safety. Sodium-ion batteries have attracted increasing interest due to their advantages. Sodium is the second most abundant element among the alkaline earth elements, providing a cost benefit. Sodium-ion batteries show the same basic redox chemistry as lithium-ion batteries in numerous characteristics. However, it confronts a series of critical obstacles to a concrete application. Among the reported cathodes, vanadium-based phosphate cathode material have attracted more attention due to their high operating voltages, theoretical capacities, and energy densities, as well as their rich electrochemical reaction with sodium-ion. In this presentation, I will report to the first time the electrochemical properties of the sodium vanadium phosphate hydrate. The main goals of this study are to explore and find a new optimal electrode materials and a new manufacturing processes methods. Most of today's electrode materials are made with high temperature solid-state reaction due to the low diffusion coefficient in solids. The traditional solid-state reaction require high thermal activation, which make the ceramic approach energetically demanding. For energy-saving reasons, there is a growing interest in electrode material prepared with eco-efficient processes, which has led to the resurgence of low-pressure temperature electrochemical processes, which we are going to use in this study. Sodium vanadium phosphate material was obtained by the electrochemical oxidation of vanadium ion in acid phosphoric solution in a 3-electrode cell connected to the computer-controlled radiometer. The working electrode was 1 centimeter square of platinum plates. A saturated calomel electrode was used as the reference electrode, and the counter electrode was a larger area platinum grid. NaOH was used to adjust the pH of the solution to obtain a pH equal to 1.9. In the parameter setting, the first step is to record the cyclic voltammetry of the mixture at 25 degrees Celsius in order to localize the voltage range of vanadium 4+ oxidation to vanadium 5+. The second step is the use of the chronoamperometry with the constant voltage of 1.5 volts at 70 degrees Celsius. Green deposits occurring from the electrochemical oxidation were picked up at the working electrode, washed with distillated water, and then dried for several hours at room temperature. So, the electrodeposited sodium vanadium phosphate hydrate phase was confirmed using powder X-ray diffraction. All the peaks in the pattern can be indexed to the atomic structure. The EDX confirmed the ratio between all the precursor, and the calculated particle size was 35 nanometer. The scanning electronic microscopy test shows a 15 micrometer thick deposit which is homogeneous and pinhole free. It shows too an image of the surface which shows that the deposit comprised small crystalline plates. The transmission electronic microscopy image shows a hydrated material well layered. The synthesized sodium vanadium phosphate hydrate was tested in a sodium half cells. Cyclic voltammetry demonstrated a good reversibility of the electrochemical process. Two broad anodic and cathodic peaks were observed. And in the cutoff voltage, the optimization of the potential windows was conducted here. We have better reversible capacity was reached in the potential range between 2.5 and 3.8. The galvanostatic charge-discharge profile of the first cycle show a discharge and charge capacity of 88 and 96.7 milliampere per gram respectively. The sodium vanadium phosphate hydrate cathode provide a high average potential of 3.54 voltage. Finally, galvanostatic charge-discharge profile for the 21st cycle exhibits a reversible capacity of 90 milliampere per gram, the potential range of 2.5 to 3.8 volts, a high initial Coulombic efficiency after 20 cycle, more than 97%. And to conclude, a thin film sodium vanadium hydrate was successfully synthesized using the electrode deposition. The electrode can deliver a high voltage of 3.4 voltage, show a reversible capacity of 90 milliampere per gram at 0.1 C after 20 cycles, have an excellent long-term cycling stability more than 97% after 20 cycles. Thank you for your attention. I will be glad to answer any of your questions.
Okay, let's move to the next speaker. Is also PhD student Abdulwahid Shari. He will discuss a comparative study on the effect of different coating of cathode materials for sodium-ion batteries.
Hello everyone, I'm thrilled to be presenting to you my research work focusing on the effect of two kinds of coating on the electrochemical performances of sodium vanadium phosphate. Let's start by the context of my study. You can't imagine that more than 7 million people die from air pollution every year, according to the World Health Organization. To solve this problem, we synthesized the MVP material using Sol-Gel method, and we performed two kinds of coating. The first one using saccharose as carbon source, and for the second one we coat the material using aluminum oxide. The three materials are obtained that will be studied: the MVP bar, the MVP coated with carbon, and the MVP coated with aluminum oxide. Let's move now to the structure characterization. Analysis by X-ray diffraction showed that we have well-crystallized samples with rhombohedral symmetry and space group R3C with the following cell parameters. And from the XRD result, we confirm that the coating process doesn't affect the structure of MVP materials as clearly showed by the Richfield refinement. Concerning the Raman spectroscopy, we observed for the three samples the presence of bands characteristic of phosphate. We note also the presence of D and G bands characteristic of carbon. Now let's discuss the electrochemical characterizations. The cyclic voltammetry curves of the MVP materials show excellent reversibility of the intercalation process, with mainly two pairs of redox peaks located at 3 volt and 3.6 volt, which can be attributed to the oxidation reduction of vanadium. Concerning the charge-discharge profile, the three materials exhibit excellent reversibility, two flat plateau at about 3.4 volt, and a high discharge capacity. However, the coated materials present best performances compared to uncoated material, and we observe the efficiency of the aluminum oxide as coated material with the increase of the discharge capacity and low hysteresis, which indicates the increase of the energy density. The long-term cycling show high structural stability of the three materials after 5G cycles, with excellent Coulombic efficiency. It's about 80%, and the comparison of the three samples confirmed that the sample coated with aluminum oxide present best electrochemical performances. According to the race capability test, the three materials display a good high race performance as well, and the coated materials show better race performances than no coated material. Furthermore, the materials coated with aluminum oxide exhibit excellent race performances compared to MVP bar and MVP coated with carbon. And for example, if we compare the discharge capacity at C/4, the MVP bar and MVP coated with carbon deliver a capacity of about 80 mAh per gram. However, the MVP coated with aluminum oxide is able to deliver about 90 mAh per gram. To understand why MVP coated with aluminum oxide exhibit best electrochemical performances, we performed cyclic voltammetry at multi-rate in order to calculate the diffusion coefficient of sodium-ion. we observed that the coating process increased coefficient diffusion, which accelerates the diffusion of sodium during the intercalation and the de-intercalation process, and the NPP coated with aluminum oxide shows the higher diffusion coefficient, which can be explained by the increase of the electron conductivity. Conclude, the coating process doesn't affect the cathode material structure as confirmed by relative refinement, and also the three materials exhibit high discharge capacity. However, the materials coated with aluminum oxide exhibit better electrochemical performances, which can be justified by the increase of the coefficient diffusion as confirmed by the cyclic voltammetry. As a perspective, and in order to understand what happened exactly and to understand deeply the mechanism of the intercalation, we plan to perform XRD operando and Raman operando, and also to characterize the cathode materials by TEM in order to verify the quality of the coating, to characterize the cathode materials with XPS to confirm the oxidation degree of vanadium, also to perform DFT calculation, and to investigate the ionic electronic conductivity of the three samples at room temperature. And thank you for your attention.
Okay, last presentation given by Shaima Hamdoushi, second year PhD student, and she will discuss titanium oxyphosphate as a high performance electrode material for sodium-ion batteries.
Hello, dear audience. I'm Hamdoushi Shaima, a PhD student in chemistry research and development, and I'm pleased to present you a part of my work about a sodium titanium phosphate as high-performance electrode material for sodium-ion batteries. As we all know, the very rapid development of onboard devices in electric vehicles, portable electronics, and also alternative energies, such as wind and solar power, has created a very high demand for lithium-ion batteries. The cost of these elements is constantly increasing, and its low availability around the planet creates great challenges. The use of another alkaline element such as sodium has therefore been considered for some years. Indeed, sodium is abundant, distributed all over the planet, inexpensive, and has a lower environmental impact. The working principle of sodium-ion batteries is similar to lithium-ion batteries, in which sodium ions get released from negative electrode during discharge, move towards positive electrode through electrolyte, where it recombines with just arrived electrons that have come through external circuits. On charge, this entire process is reversed. And recently, the development of new electrode materials for this new generation of batteries, especially polyanionic compounds, has attracted the attention of researchers. The synthesis of our sodium titanium phosphate was done by the Soldier route by mixing a stoichiometric amount of disodium hydrogen phosphate dehydrate dissolved in distilled water and titanium isopropoxide. After the addition of titanium isopropoxide, we have obtained the gel, which was dried at 100 degrees for 5 hours and then annealed under air at 600 and 950 degrees for 6 and 10 hours, and by the end, we have obtained a white powder. As we all know, the phosphate-based materials have poor electronic conductivity, so for that, we proceeded to carbon coating process to enhance the electronic conductivity. Our composite material was prepared by mixing 85% of the resultant powder and 15% of sucrose using pure acetone as solvent. The mixture was calcined at 600 degrees for 5 hours under an argon flow, and by the end, we have obtained the black powder of the composite material. Now let's move to the structural characterization of our material. The XRD analysis shows a pure and well-crystallized material which can be indexed into a monoclinic system with P2C space group and the following cell parameters. As we can see here, the structure of the sodium titanium phosphate consists in the arrangement of titanium oxygen octahedra sharing oxygen and linked 2 by 2 by phosphor oxygen tetrahedra to form chains, and the sodium ions are located between these chains. The morphologies of our uncoated and coated material were examined by scanning electron microscopy.
As shown in the images of the uncoated material, the particles are agglomerated with an irregular shape and have a smooth surface, while from the images of the coated material, we can see the fine carbon granules deposited on the surface. Raman spectroscopy was performed to investigate the carbon content in this coated sodium titanium phosphate. As the results shows, two additional broad and overlapping bands are observed, the D and G bands characteristics of carbon. And also, thermogravimetric analyses were investigated to estimate the carbon amount in the composite material. As we can see in the results, the amount of amorphous carbon is about 3%. Concerning the electrochemical tests, we have tested our material as an anode for sodium-ion batteries in a half electrochemical cell within the voltage window 0.01 volts until 3.0 volts in a current rate of 0.1 C. From the cyclic voltammetry tests, we can see a large primary cycle indicating the electrolyte decomposition and the formation of a solid electrolyte interface layer. The two main anodic peaks observed at 1.55 volts and 1.42 volts are assigned to the oxidation process of titanium from 2+ to 3+ and then 4+, while the cathodic peaks observed at 1.3 volts and 1.1 volts are assigned to the reduction process of titanium. The following tests are galvanostatic and long-term cycling tests. As we can see in the figure of the galvanostatic test, our material exhibits an initial charge capacity of 160 mAh per gram at a current rate of 0.1 C. Also, one reversible plateau during the charge and discharge between 1.54 volts and 1.1 volt is observed, which is in good agreement with the CV results that we saw before. Also, our material shows an excellent cycling stability after 20 cycles and excellent capacity retention approaching 99%. After that, we tested our material by increasing the rate up to 1 C during 50 cycles, and it maintained the high charge capacity about 112 mAh per gram and excellent cycling stability and the capacity retention approaching 99%. More than that, the material exhibits an excellent rate capability performances, even if the current rate has been increased to its highest value. Moreover, when the current density returns to 0.1 C, our material recovers the same initial capacity of about 160 mAh per gram. To conclude this presentation, I will make the highlights on the main axis treated. A pure sodium titanium phosphate has been successfully synthesized via solder route. The carbon-coated sodium titanium phosphate presents an initial charge capacity of 160 mAh per gram with excellent cycling stability after 50 cycles and excellent capacity retention approaching 99%. As perspective, we are looking forward to perform in operando XRD analysis to investigate the structural evolution and the reaction mechanism during the charge-discharge process. We have reached the end of our presentation, and thank you, dear audience, for your attention.
Yes, so that was the last presentation. So please, I'm asking the keynotes, Professor Passarini and Dr. Shakir to join me in this panel discussion, and also the students and PhD students. So we don't have a question for audience. So we may start by Professor Passarini if you have any comments, recommendations, or questions to the students and PhD students.
I mean, all the presentations are very interesting, actually. With respect to the last presentation, I was wondering, I mean, is Morocco a producer of phosphates?
Yes, so Shayma, can you answer to this question?
It's for everybody, I would say, because I see that you are concentrating quite a lot on phosphates, right?
Yeah, so I can answer this question. I'm here as associate professor in Mohammed VI Polytechnic University. So we are funded by the OCP. OCP is the company of phosphate. So we want to make this they support us financially in order to make added value for phosphate-based materials. It has the biggest serve on the phosphate. Actually, is the first producer or the fertilizer. So yes, so we are working on the phosphate-based material, LFP, and all kind of the phosphate for sodium and lithium-ion batteries. Yes.
Okay. I was just wondering, because I've seen that there were these 3 presentations. They are all making use of, let's say, non-aqueous electrolytes, right?
Yes.
But these phosphates, maybe is a question for the last 3 speakers, let's say, or even 4 speakers. Have you tried to test these phosphate materials with non-aqueous, with aqueous electrolyte, with concentrated aqueous electrolytes?
So, Abdullah Shali, can you answer to this question?
Yes, sir. Thank you so much for this nice question. Yes, we test the materials using 2 kinds of electrolytes. The first one is NRPFCs and the NaCl4. And we try also to change the concentration using 1C and also 0.5C. But we didn't try with a high concentration.
Yes. So maybe Hasna, she can answer to the question. So she's mainly focusing in ionic liquids for solid batteries. Hasna, can you turn on the microphone, please?
Connection problems?
Yeah, we cannot hear you, Hasna.
Yes, switch on your mic.
Can you hear me now? Can you hear me now?
Yes, yeah. Go ahead, yeah. Little. So some technical issues. So
yeah,
we can't
so
hear
as
you.
I say, can you hear me now?
Yes, yeah. Go ahead.
So we have tried and tested this cathode integrated in the ionic liquid electrolyte by addition 10% of ionic liquid in the propylene carbonate solvent and has shown of cycling performance and current rate of 100 milliampere per hour.
Okay, but none of you has tried aqueous-based electrolytes.
We talk just about the conventional electrolyte. Yeah.
Yes, so maybe some technical issues. Yeah, so did they use only so they use organic the standard electrolytes, use the NPPTs and the propylene carbonate, and in case for Hasna Karim, she used mainly the ionic liquid mixture with the propylene carbonate. But yes, for aqueous, I think it will be interesting because this kind of material didn't show the high voltage and they can use it by aqueous. Yes, yeah. So maybe you can try this.
Because one of the major costs of I mean, sodium-ion batteries, I'm just working on the cost analysis. Actually, still the electrolyte, the non-aqueous electrolyte, especially the sodium salt PF6, is very expensive, right? So we have been exploring the use of highly concentrated aqueous electrolytes with the sodium vanadium phosphate and also the sodium titanium phosphate. Since at the very end, if you combine the 2 electrodes together, the voltage is not too high, and aqueous electrolyte can manage it. I mean, this could be maybe a line of activity that you can investigate, explore a little bit. That's a suggestion from my side.
Yes, yeah, it is well noted, Professor Kassan. So, yeah. So if Shaima, you want to say something about Professor Passarini comments? I will check if we have questions.
Yeah, small question for Khadija Kouchi.
Yes,
yeah,
please.
I guess it's not. Yeah, Maad, you can hear me?
Yes, we can hear you. Please go ahead.
Yeah, I guess it's not oxidoreduction reaction what is happening in your cell, right? It's a kind of conversion. Yes or no? Anyway, the question is, what is the mechanism? If it's conversion, what is the mechanism? What you form during the first discharge?
Yeah, Khadija, can you hear us? So turn on your microphone, please, and answer to the question. Even she is not in the police.
Okay.
Yeah.
Yes, Professor Shakir, we can predict that. Yes, I'm answering because I'm working with Khadija on this work. That's why we can predict that probably we have the reduction of iron during the first discharge. Yes, from iron 3+ to iron 2+. But probably we can have, at the same time, the intercalation of lithium and enter the structure of the materials at the same time.
Yeah, you mean it's pure oxidoreduction mechanism, right?
Yes, yes, yes. But we have to complete analyzing the materials because the work is ongoing, and we have to do more analysis to understand deeply what happened.
Okay, okay. Yeah, this is the okay. Thank you.
You are more than welcome.
So just to continue on this material, I mean, in this compound, in this mixed quaternary oxide, the active material, the active metal is iron. Nickel is not active.
Yeah, it should be iron because the voltage is low. Yes.
Yes, because we are working on low voltage. Yes, probably we have just iron. It's active in this case, but as I said before, we have to check with Zaft to be sure which materials will change the oxidation degree during the intercalation, de-intercalation.
Okay, because the lithiation at very low potential of nickel oxide was actually the subject of my PhD thesis.
Oh, nice.
Very long ago, and I think I was the first demonstrating it. So maybe you should take a look, because just by chance, lithiating nickel oxide at very low voltage is a good electrode for electrochromic cells.
Yes,
and
it's great.
And it's complementary to tungsten oxide. So this is why I was working on it. I mean, I was working not on batteries, but on electrochromic windows at that time.
Yes, sir. It's a great chance for us to give us more insight about the mechanism of this materials, because we are just beginning studying these materials, and if you have more insight about the mechanism, it will be great.
Yeah, you should try.
Yeah, okay, go ahead.
Sorry, you could try maybe to coat a thin layer of these nanoparticles on a glass electrode, an ITO electrode, and see if you have also a color change. Because I expect this to be opposite to tungsten oxide, and then you can work on these windows that change in color when you apply electrochemical potential.
Okay.
These are becoming common also in the rear view mirrors in car. You know, there are some cars that have these mirrors that becomes dark when somebody is shining the light. So this could be also of interest. Huh?
Yeah.
And right now I have to excuse myself, but I need to leave.
Okay, thank you. Thank
Because
you, Professor. And hope to see you in person next year in next edition, in person, not virtually. So hope to see you next year in Morocco with us.
Yes, I've never been in Morocco, actually. I'm supposed to come since 2 or 3 years. Carl always invites me. But so far with the COVID, I didn't manage. So it will be a pleasure whenever it's going to be in person, okay?
Yeah.
Very good. So thanks a lot and have a nice evening. Bye-bye.
Okay. Thank you so much. Thank you so much, sir.
Thank you. So, Mohammed, do you have any question or suggestion to the students?
Just to complete this question because it's interesting material and the capacity is very huge. I'm just wondering did you make calculation? What is the theoretical capacity? Because before to make your characterization with the Mosby or whatever, you can guess something just by calculation. What you expect? Yeah, you have a lot of. You can, for example, put some hypothesis. For example, here you see that the iron is active element, and if iron is active element, what is the capacity expected? And if, for example, Stefano said the nickel goes to nickel metal, I guess. What is the theoretical capacity? You can make this kind of calculation, and you can expect the mechanism or the reaction before to make your experiment.
Yeah, thank you. So here we have another question from Lubna Hidou to Khadija. Thank you for your presentation. You mentioned that you have the reaction of Mn and iron, but what about the nickel and magnesium during the first discharge, how they react? So it's a difficult question to answer. Even Khadija, she's not with her, but now we are trying to make some X-ray operando and also Raman operando spectroscopy in order to see what happened exactly, and also yes, mass power. So we can do with our colleagues this kind of measurement in order to understand and also to prove the convection. Yeah. So if no question, because we are behind the time, 14 minutes, we expect 4:30, 5:30. So if no questions, so hope see you next year in person. All of you, with more interesting and exciting results. So thank you very much. Thank you for all panelists and also for our friend Mohammed Shakir. Now I give the mic to Professor Yusuf Znaz and thank him for this outstanding organization of IRSEC. I think we are the last today, or yes, you have still presentation tomorrow.
Okay, thank you so much.
Thank you. Thank you.
Thank you very much, Dr. Muaddi. Thank you very much for all keynote speakers, Mohammed Shakir and Stefano, Professor Stefano, and all attendees of this workshop. I hope that it was very, very interesting and fruitful. Thank you very much, and I ask attendees if they are interested to certificate, they can use the link on the website to ask for certificates, attendance certificates. Thank you very much, and see you in the next edition of IRSEC. And also tomorrow is still other sessions if you are interested to themes of tomorrow. Thank you very much, and bye-bye.
Thank you. Thank you.
Thank you. Thank you so much.